your soul, but just stay true. Sometimes we just don't know. The light shines through. Sometimes you have to go, and I'll go too. Sometime real soon you'll glow. You'll shine bright through. Take you, but the light is there to hold you down. Take you, but the light is there. You're bolder now. Wake you, but the light is there to show you how. Break you, but the light is there. It's over now.
Living in the dark, I feel so alive. Still remember. Candlelight has gone out. Some will win and some will lose. Nothing much else to say. Thought I was searching for something. Door has closed, not a sound. Take a look as I am now. Still I smile and don't speak. Will you please slow down? Slow down.
Hey, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Hey, 2, 2, 3, 4. Hey, You got it now? Hey. Hey, it's on manual. 2, 3, 4, 5, 6, 7, 8, 9, 222.
And on the levels here.
Hey, hey. 222. 12. Let's see if we go to auto. Oh, there you go.
What was it? Just, I need
It
to
was
get
on
an
my
auto.
level, but on mic level. Hey, hey. 1, 2, 3, 4. So I have you on auto and line level. I mean mic level. -10. I cranked it because you said you couldn't hear, so I can bring it down now.
What was it?
I turned it up because you said you weren't hearing it, but I can bring it down now.
Okay.
Okay, let's try this. Tell me when it's good. 8, 5, 6, 7, 8. Okay, thank you.
Close your eyes, only got one night. Just put your trust in me. Give me everything. I need your love tonight. So baby, please don't fight it. Put your trust in me. I'll give you everything. So hold on to me. Never let me go. Right here in your arms is where I wanna be. So hold on to me. So hold on to me. So hold on to me. Never let me go. Right here in your arms is where I wanna be. Close your eyes, only got one night. Just put your trust in me. Give me everything. I need your love tonight. So baby, please don't fight it. Put your trust in me. I'll give you everything. So hold on to me. Never let me go. Right here in your arms is where I wanna be. So hold on to me. So hold on to me. Never let me go. Right here in your arms is where I wanna be. Where I wanna be.
Two.
So hold on to me.
Two.
You've got the fire, let the flame burn high. You're taking me over. You've got what
Two.
I'm looking for. You've got desire, hold me tighter. You're taking me over. You're all I want and more. Don't let go. Don't let go. Say you'll stay with me in the shadows. I'll be your light in the dark night. Till you feel the spark deep inside. I'll be your light.
Hey. Two. Hey. Two. Ha. Good. Hey. Ha. Two. Ha. 1, 2, 3, 4. Two.
Caught in a crossfire, a love
2222. Hey, hey.
Till you feel the spark deep inside. I'll be your light in the dark night. Till you feel the spark deep inside. I'll be your light if you need help to find. There's hope in your heart, 'cause it's who you
Hey, hey.
Does it get easier?
It gets easier. And the more you know who you are and what you want, the less you let things upset you.
I just don't know what I'm supposed to be.
pressure. A prisoner, but please don't set me loose. 'Cause I never felt such pressure. And you said you feel it too. Harder than those nights in summer when we fall. When we fall into each other. When I fall into you. Yeah. When I fall into you.
say I'm running out of breath. I don't know what to think, what to feel. You're so far away, but I still feel you here next to me. You can hear a single word I say. You took all of my pride away. And now that you let me down, I'm falling on the ground. On the brakes with a separate sound. I'm screaming out loud. I'm lost in your empty words and empty promises. I'm so sick of listening. I'm so sick of this. You keep telling your lies, and I'm still here willing to sacrifice 1,000 fires running from my mind. You don't deserve my love, but we both know that I don't have the power to let you go. You can't hear a single word I say.
All right, everyone, we're getting started, so please be seated. And we'll start the event now. So, hi everyone, welcome to the BAS EthDenver version. My name is Kun Peng. I'm the founder of Stanford Blockchain Accelerator and also founder of this BAS conference series. We did one at Stanford Blockchain Week and also another one during the Istanbul Dev Connect. This is the third edition. I'm also an instructor of 2 blockchain entrepreneurship course at Stanford University and also partner at Blockchain Builders Fund and also a master degree in management science and engineering from Stanford University. So BAS is a spin-off of Stanford Blockchain Conference and got inspired by all the wonderful work that Benet has done organizing the amazing conference back in Stanford. And this is the intention is very similar to SBC, a gathering of the top and the brightest minds in the industry to share the latest developments in the research and technology, and also some of the best startups from the Stanford blockchain ecosystem. So that being said, welcome everyone to BAS, and I'll pass on mic to Gil.
Awesome. Thanks, Kun. Yeah, we're excited to have you guys here today. We're excited to have BAS here at EthDenver today. At Stanford, we've got an amazing ecosystem of 27 courses, 2 research labs, an incredible blockchain club, an alumni blockchain club, and the Accelerator that Kun mentioned. I co-run the Accelerator with Kun and Steven, also co-teach the course with Kun and Steven, and also run the fund with Kun and Steven. My wife thinks that I spend more time with them than with her. But we're excited to bring kind of that rich ecosystem that we have kind of out to the world and to share everything that we're excited about with you guys. Couple last minute notes at like the Accelerator itself, we've had over 50 teams go through it, 35 have launched with like users and revenue. They've collectively raised over 150 million from like the leading funds in the space, and we've got 5 of them that are going to be speaking here today, including Zero Gravity, Exhibits, Nexus, Modulus, and Oxpath.
Awesome. I'm Steven, MBA, class of 17. Love working with these guys. I won't give you my full background. I do want to say a couple thank yous as we get started and also do a couple housekeeping asks from y'all. First of all, this event is free to you and is run at cost thanks to our very generous sponsors, many of whom are in the room. If you want to put a hand up, great. You don't have to, but thank you a huge amount. We'll make sure to give you a lot of airtime today, so thank you, thank you, thank you. Also, this is an interesting space. You are now the veterans, so you get to help new people navigate the space. So throughout the day, make sure if someone looks lost, help them find the right spot. Also, this room is pretty full now. It's going to get fuller later. So, be good about scooting in and making room for folks. Finally, I wanted to say thanks. We've given some micro grants to some Stanford students, 2 of which have made it here this early, which we appreciate. So hands up. Everyone make sure to say hi to them and thank you. And we'll be highlighting them a bit more later today. Did I miss anything?
You did the sponsors, right?
I did the sponsors. I did the micro grants. All right. Well, thanks to all of you. Also, if you find yourself having a conversation and this room is full, we have an overflow room. It's a very good loungy vibe. We will be putting a broadcast up of all the content here. So if you want to see the content and this room happens to be full, please check out that other room. We also have some of our sponsors with booths there, so say hi to them. Now I think that's it. Thank you, Gil. All right, without further ado, we'll bring up Juan Benet, founder of Protocol Labs.
Great. Thank you. Thanks so much. Yep. Great to be here. Thank you for coming so early. Stanford always making me roll out early in the morning. How many people are here from Stanford, just so I get a sense of the distribution? Very few. This is awesome. This is great. This is like the first Stanford event I go to that the distribution is like actually more broader. So that's great. Insular communities sometimes get disconnected from the real world. Great. How many people here work at a startup in crypto? About half. How many people are like thinking about getting into crypto but are not yet in crypto? Cool. How many people are like builders? Okay, awesome. How many people are like, what are the other people, like investors? Some amounts. Okay, wow, that's like a half. Cool, actually, I have good stuff for you. Not things to invest in, but about how capital is going to change. And how many people here are like trying to look at the next like 2 to 5 years of like what's coming? versus say like the next 10 years? So who's more interested in the next 5 years? Who's more interested in the next 10, 15 years? Cool, that's great. I'm glad. You should be thinking long term. Great, so let me see the list. Well, my guess is probably in the whole list. I'm one of the earliest people in crypto here. I tend to be pretty early to things, and so I want to talk to you about some things that are pretty early right now. You will hear about them and you'll be like, is this really going to be that significant? But that's the point. It's I'm trying to give you some like things that will matter longer term, more than what you think might matter right now. This is probably not what's going to be like super hot or whatever, but this you might be hearing about it. It's definitely not secret or new or whatever. But it's what I think is going to matter much more than the other stuff. I'm also going to make it highly interactive because it's early in the morning and I want to keep you guys like awake for, if I just start blathering at you, you're just going to tune out, fall asleep, and so on. Cool, so a bit about me. I built a lot of things in the crypto space. I got into crypto in 2012, 2013, built IPFS, built Filecoin, built WP, now working on a thing called IPC. Big part of the Ethereum community, the public goods funding community. Worked on a ton of, PL is now this startup network, so it's not kind of like a single company, but it's now a network with hundreds of startups and hundreds of projects. I advise a lot of companies and invest in a lot of things and so on. The way that I think about it is we have a super powerful set of tools in the blockchain ecosystem. We get to create incentives, which means you can program humanity. So don't think about the blockchain space as programming computers. Think of the blockchain space as programming humanity. And that includes organizations, people, nations, whatever. Like that's what you get to play with, which I think is one of the most important things going on in the species right now. So a lot of people got into the space because of this. There's like a super problematic security picture where the digital systems that we've built over the last 20, 30 years can radically create some like really bad outcomes. And so a bunch of the people that built the Web3 space from the beginning have been trying to establish a whole bunch of digital rights in the world, bake them into the underlying stack, and we do that by creating a whole bunch of systems. So we build large-scale distributed systems, things like IPFS, things like Ethereum, things like NIM, and so on. And through those things, we can build secure systems to give us digital rights that we can embed into the network. There's tons of people working on this. Of course, it's a major part of the Web3 movement. So I could spend a lot of time talking about this, and because I said I was going to make it highly interactive, I'm going to move to Q&A relatively quickly. So happy to spend time talking about any of these kinds of projects, any of these kinds of things. I kind of pulled a set of people coming to the event. People wanted to know about ZK, people wanted to know about AI, and so on. But the thing that I want to give you the most alpha on, in a sense, in the long term, is this second thing about the blockchains that we have can help us upgrade our entire economies and our government systems, and that's way more important than the cloud stuff. The cloud stuff is really critical, and we have to kind of like finish that mission. And so a lot of us spend most of our time on that. I spend most of my time on that. But I want to kind of like alert you to the fact that there's a major other opportunity, and you should start spending some fraction of your time on that. And you should be encouraging a lot of people to spend your time on that. And that's around kind of economies and governance systems. Kind of like setting our bearings straight. This is what I call the R&D pipeline. Can you see that well? Kind of. This is what I call the R&D pipeline. You have research here that's kind of like academic research funded by primarily public goods funding in terms of nation states. You have corporations building technology over here, and that's primarily funded by like investment capital, financial capital, kind of like public things are over here. This is mostly kind of the realm of VC. This is kind of where startups start. Here in the middle, this section, going from basic research into things that are startup worthy, is tragically underfunded. This is where the best startups are built. So this is where your SpaceX's, Tesla's, Apple's, like the Google's, the best things are kind of like here in this environment. So for all of you investors out there, look for things here. Usually, they'll look like science projects. When I went around pitching Protocol Labs and IPFS and Filecoin to people, I also had to pitch like Ethereum along the way because people like didn't know what it was. So many VCs at the time were like, Ethereum is a science project, never going to work. And it's like, man, if we're starting there, like, then probably don't want to tell you about all the other stuff that we're working on. But like unfortunately, that's what it looks like. And so most of VC kind of exists here, where it's kind of obvious things are working and so on. This is where the really valuable stuff is. Unfortunately, most VCs can't afford to invest here because it's very expensive. Like this is extremely, extremely expensive to do kind of like the technology translation piece. There's a bigger hope that I have that we can create better incentive structures to actually make this financializable. There's reasons why there's no good investment assets here. Usually a lot of the teams that build here are not the same people that build the startups and grow. It's very rare that you find those kind of startups that can take something from early R&D all the way through that. And so this requires a lot of, probably on the order of 10 to 100x more capital and effort to turn a science project into something that can become a startup. And so this is extremely expensive, underfunded, and so on. If we can find a way to financialize this, then we can create like very strong incentive structures that can then make everything go way faster. So look for the things in the space right now that are thinking about incentive structures to financialize this part of the pipeline. This is before there are startups. This is before there are products. So these are kind of like new forms of IP, new forms of like grants that might turn into some kind of investable asset, and so on. Things like hypercerts, things like spreading money through credit distribution graphs, so like drips and so on. That's the kind of thing that I think can be super valuable. If you're not paying attention, in the last 80 years, the world got totally transformed by computers. That's accelerating. It's going to get like way more intense. And like the next 80 years are super crazy, right? Like the kinds of things that are going to happen with BCI, AI models, AGI, and so on, totally going to rewrite how the species works. So get ready for that. And think of like, how is the world going to start reacting to these things? We have a super deeply inadequate government systems that can't really cope with this sort of thing. And at the same time, we also have like super inadequate economic systems, right? So like, this is the total R&D budget of the US spent in kind of non-defense things. This yellow part, this is why we have, this is why we went to the moon. This is like the amount of capital spent in the Apollo program and related programs. This is why we got to the moon. This part, when Congress was like, whoa, this is way too expensive. This is why we don't have the space industry today. This is why we never went to Mars, and so on. This green one is energy. This part here is why we have fission, and this part here is why we don't have fusion. And so this is about, I kind of like always ask, how much money do you think this is? How much money do you think the US spends yearly on R&D, kind of non-defense R&D? Just any guesses? 1 trillion. 12 billion. Oh, that's very low. More?
It's actually 980 billion.
That's including corporations. This is just the government. So 60. You were very close. 60 billion. For 60 billion a year, you could fund all of the R&D that the US does. What's that? The defense R&D is probably 2 to 3x this, and so a lot of it is kind of defense technology and so on. The bigger problem is that this is just so small, right? So this is kind of like cures to cancer. This is like early tech like the internet. This is like all the NSF grants. Like this is what builds the future. So everybody knows that science and technology build the future. If you could just do a lot more of it, then everything would advance faster and the world would get better, and so on. And yet, most of our money does not go to that. This is how much money you needed in fusion, according to like most of the plans that people came up with. That's how much we spend yearly on Netflix. Not just Netflix, but like the Netflix type of products. So this is abysmal, right? Like this, as a species, when we look at this and we're like, how are we okay with this? This is like totally a mismanaged civilization. So crypto gives you the tools to like get out of this trap. So very quickly, I want to talk a little bit about non-zero sum games. So most people, when they hear about non-zero sum games, they kind of picture something like this. If you collaborate, if you compete and so on and fight, then you're going to lose out. So everyone kind of like knows that. And so sure, you should collaborate and kind of like improve your gains and so on and grow the pie. Unfortunately, that's not really how it works. It works more like this. If you collaborate, you can create orders of magnitude more value. This is science, this is technology, this is like penicillin, this is like cures to cancer. Like you create orders of magnitude more value. So like the current model of the world is not oriented towards this. Does not really truly understand how this affects everything we do. So this landscape of being able to kind of be in this highly collaborative environment that is non-competitive, that is trying to like go as fast as we can to kind of realize the gains, is what some great philosophers call Paretotopia, because these are Pareto improvements. The point is, how do we get there? How do we kind of coordinate the whole species to do these kinds of things? This is where crypto can help, right? So crypto economics can give you the tools to incentivize the world to be able to get there. I mentioned that this is software eating kind of incentive structures, mechanism design, and so on. Think of Bitcoin and Filecoin as like the product of two incentive structures that got released out into the world and then just assembled massive amounts of hardware and just are powering these huge supercomputer clusters. Now, unfortunately, the Bitcoin one is like wasted. The Filecoin one is useful. But this is like crazy powerful, right? Like a couple incentive structures with a currency, like reorganize the entire world to do this. You could do this to carbon capture. You could do this to increasing more solar. In fact, Glow is a project that is working on this to increase the amount of solar on the planet by just releasing a couple incentive structures into the world. So this is kind of like the background of what I think is one of the most important things happening in the entire blockchain space, which is how do we use these incentive structures to rewrite our economies, our governments, and so on. There's a whole movement called Greenpilled that you should go check out. There's a great book. There's a podcast. Highly kind of recommend you go down that rabbit hole. But the core of it is like you're shaping incentive structures. You're shaping the landscape on how people are, what they're choosing to do. And so think about how to use that to coordinate lots of people to get to this kind of Pareto-topian outcome. And so think of blockchains not as kind of like just improving the cloud stack, which a lot of us have spent a lot of time on and will continue to do so to kind of land that mission, but also think of them as a way to rewrite how all of civilization works. And you have to start small. So whenever you have some super ambitious thing, you have to break it down into small components, test it out, make it work, and then scale it. But this is some of the most important stuff that's happening in the entire space right now. These are things like, I'll give you some like examples. The last thing I'll kind of mention, because a lot of you might be like, man, this sounds like pretty cool, but like, really, is this actually going to work? Crypto is just so small relative to the rest of the world. So this is kind of like a total crypto market cap. For the people that are like kind of skeptical about, is crypto really going to be like so significant? This is kind of crazy, huge ups and downs. Here it is in a log graph, kind of like a steady pathway this entire time. We're probably the only industry that uses log graphs to look at market caps. That should tell you something about like how weird this place is. But what I think is more interesting is to look at all of the money in the world. So this is a great visualization from the Visual Capitalist. They make great graphs. Here's crypto in 2021 top, which we're kind of like near currently. This is military spending. This is just currencies. This is gold. Gold's cool metal, but like, come on, like programmable digital incentive structures and like way more valuable than gold, right? Like if people think the cryptocurrency is overvalued, like just show them this graph. This is central bank balance sheets, the S&P 500. There's a lot of value here, a lot of technology and so on. Global money supply, stock markets in general, debt. Real estate, oh man, like our house is really worth that? Like, oh man. Yeah, the weird thing is like you can't really bet on these kinds of bubbles because like the world can stay irrational for centuries. This is like derivatives. It just keeps going and going and going. So these are all the outstanding bets through all kinds of like Wall Street. So, and people tell you that like crypto is full of scams. Even if this was like 50% scams, which is absolutely not, like just compare it to any of this stuff. Like all this other stuff is full of scams. Like just this derivative stuff, like just 0.1% of that like is bigger than all of the scams in crypto, right? Like this is crazy. And so, when people doubt crypto, just show them that graph, and then remember like that you're building programmable economies and programmable systems and so on. So, if we can create our economies, these blockchain weird things, and start orienting them towards solving large-scale problems and routing the incentives for solving large-scale problems, as these things get more valuable, you start reaching levels of capital routing that starts rivaling not corporations, but nation states. That's super crazy, right? So we're talking about potentially being able to fund what the US does out of blockchains. Like imagine a world where blockchains suddenly outperform the US in funding R&D. Like that's possible. That's possible within like 5-10 years is like the optimistic case, probably more like 15 to 20. But this could be tremendously significant. And you can do that by just taking a blockchain network and dedicating a portion of its supply to public goods funding in some set. I've been spending a significant fraction of my time in the last few years convincing a lot of groups to do this, to allocate a fraction of their monetary supply for their economies to public goods funding, broadly defined. Sure, oriented towards your network and what's valuable to it, but broadly defined, so you can spill over to a lot of other things. If we can do this right, like we get to rewrite kind of like how the world works. Just remember these things are not static. A lot of people talk about economies and systems and governments as like the way things should be. In reality, all of these things and all of these structures and so on just were invented by people and were systems that got designed, deployed, and kind of worked and scaled. A lot of inventions didn't work, didn't scale, broke down, or whatever. You know, the history is littered with inventions of human systems that didn't work. You know, this part at the beginning that I talked about, you know, in terms of R&D funding, this didn't exist 100 years ago, right? Like, governments didn't do this at all. This looked like almost no basic research was happening. And so it's totally plausible that we can bridge this gap using crypto, or you know, convincing governments, or you know, financializing it so that investors could invest. So that's just a few inventions away. VC didn't exist 50, 70 years ago, right? And so this entire part of the pipeline got built out in the last 70 years. So I want to like maybe land some examples of the kinds of things that you should be like looking at. Optimism's RetroPGF, super interesting mechanism. Not because it is novel, but in fact because they made work a lot of things people were talking about before. So people have been trying to make the retrospective funding work for a while. Optimism just find a really good way to scale it. They just reward retroactive impact. They've had a series of rounds. They're now funding every 6 months to the tune of like $100 million worth of value flowing to all the participants that contribute to that ecosystem retroactively, after the fact, based on like community-oriented agreements of like what could be valuable. There's DRIPs, which is like funding, you know, dependency flows in GitHub. You could do this for the publication graph. No one's stopping you. Today, you could like grab the entire publication graph, wire it up with money flowing through it. That's like a few months project. And like you could totally rewrite how capital works in science. There's all kinds of other super interesting incentive structures. There's hypersets, which let you take impact and bottle it the same way that currency bottles utility, and then you can sell around impact. Think of it like a generalized carbon credit, but you can apply it for all kinds of structures. You could take, you know, the funding staircase of VC that works really well. And by the way, VC is kind of a neural network. I won't go into that, but you know, teaser. Funding staircases in the impact side, like in nonprofit, are super lopsided. If we can make this kind of smooth like VC, all kinds of things would get drastically better. And again, if we can like financialize impact capital, that would be pretty good. So I have a minute left, and maybe I'll finish with, we should make a crypto-powered ARPA, which I think would be like an extremely powerful thing. And yeah, come join in the public goods funding landscape, because that's super valuable. And for a lot of you who are working on like that first part of Web3, which is kind of securing the internet and establishing digital human rights, super valuable, super important. I devote most of my time on that. But this other stuff is like what I think, you know, 20 years out is probably going to have been more significant. And so we should like, you know, start spending some amount of your time in both, figure out how to use incentive structures to coordinate lots of people along the way, and so on. Cool. I'll have like a few questions, and then I promised that I would make it interactive, and I didn't. Sorry about that. Just a few questions, and then we'll go. All right. Any takers? Yeah.
I'm curious how you see Filecoin contributing to the Ethereum roadmap.
Great question. So Filecoin and Ethereum have been collaborating since before either existed, which is kind of a funny story. But we help. Filecoin already helps a lot of Ethereum applications and so on. Data availability networks make a lot of sense around Filecoin. So there's a set of us working on DA layer type stuff. All of these chains are going to get highly integrated. Right now, they kind of feel like different islands. That's just a passing phase. We're going to get the calling conventions between these things like super nice, kind of like the internet. And so you'll be able to call from any contract to any other chain like really easily. We're working on one scalability tech called IPC. That's one of the things I'm spending a significant fraction of my time on to just scale up what blockchains can do. Blockchains right now are like super rate limited. They're kind of like very, very small throughput relative to the cloud. If we do that scalability stuff right, then we can like help scale a lot of the Ethereum applications and so on. Yep. Yep. Great. Out of time. If you, I'll stick around later at the break, and happy to chat with more people. All right. Thanks.
Hello? Yeah. All right, thank you. Thank you, Juan, for the awesome talk on public goods. So next we have Brian Retford, co-founder and CEO of RISC Zero. So let's welcome Brian.
Check. Hello, everyone, and good morning. Yeah. So today I'm going to be talking about ZK at the limit, and specifically, we're going to be talking about proving entire optimism epochs. So I want to give a quick intro to the RISC Zero ZK VM. Hopefully, everyone here knows what ZK is. Is it good? Maybe. Okay, I left the ZK intro out of this deck, so I guess you'll just have to keep up. So RISC Zero is a zero-knowledge virtual machine, which means that it proves the correct execution of any program written in Rust right now, but really anything that can compile down to RISC-V. So in the ZK context, the circuit is the RISC-V chip, and the inputs are whatever your inputs are, and also the program that you're running. And run all this through the RISC Zero ZK VM, and you get a nice, succinct proof of correct execution that you can do things with. So it's pretty easy to get started with RISC Zero if people haven't actually played around with it. It's not much harder than cloning a repo, running a couple cargo commands, and then you can really start proving anything that exists in Rust. So let's see, how long ago was this? 6 months ago, I think Optimism put out a mission request, an RFP effectively, for figuring out how to ZKify Optimism. We submitted a response for that, and were selected to actually build this. So what this looks like from our perspective is actually taking existing Rust code, proving it, and then extending that to also prove all of the additional semantics of Optimism. So yeah, with Zeth, the first Type 0 ZK EVM, it was actually the first Type 1 ZK EVM that I'm aware of. We actually just built this on top of, as you can see, REVM, Alloy, and Ethers. What this actually let us do is, build an entire ZK EVM with only about like 5% of the additional sort of code change over the existing code base. So, building on top of that, Optimism is like quite a bit more complicated than ETH. So, we, as part of this mission, we ran a bunch of Optimism blocks through this OP Zeth process, and you can see there's a whole bunch of interesting metrics, such as the number of ZK cycles per gas, which is something that varies up and down as you'd expect, but is also kind of more consistent than you'd expect. We'll get into sort of how all of this works in a second. So anybody can check out and use Zeth. You just got to clone the repository here. And it's pretty simply laid out, and we're going to go over just a little bit of how all of this works. Zeth has this very handy CLI that you can use to build blocks, run the blocks so you can actually create the blocks that you're about to prove them, and then verify them. And we support Ethereum optimism and the optimism-derived network. So if you just want to play around with Zeth to actually build these blocks, you can use the CLI to connect to an RPC provider, and it will go through the modified Zeth code and spit out these blocks for optimism or for Ethereum. The code for these sort of bits of block building are pretty simple. We had to modify several parts of the actual Reth system in order to make them ZK friendly. But once that was done, you can see that there's not really a ton of code that actually has to run inside ZK in order to build these ZK proofs of correct Ethereum execution. So the OP architecture, it's obviously a full L2 on Ethereum. The DA ends up on ETH proper. So every transaction on OP can actually reference DA from Ethereum, which greatly complicates the process of proving any of these sort of optimism blocks. Rather than just needing to look at the transactions on ETH, you actually have to effectively build a coprocessor that can look at these transactions on ETH, prove things about Ethereum, and then roll them up into a single proof for optimism. Yeah, so the core architecture is pretty simple. We just use these existing crates that I mentioned earlier. There's a custom Merkle Patricia tree we had to write in order to sort of get the data flow between the host of the ZKVM and the guest to be a reasonable size. So this is just a bunch of code that one can look at to see how this sort of all comes together. Effectively, a lot of this process of building these optimism blocks has to be coordinated across several actual simultaneous ZK programs that are running at the same time. So the block proving flow for optimism, effectively, you build the blocks natively, not using any ZK, just talking to a regular RPC node. We log everything that happens, and then get storage proofs for all of the actual access to the L1, retrieve the historical block headers. We build this new in-memory DB, and then we actually build the block in ZK and produce the proof of correct block construction. Yeah, and I guess the one, let's see, is this going to go back? No. Yeah, the one detail there is that we use the RPCs to sort of build up this memory database, and then inside the ZK VM, obviously we're not making network requests, we're just dealing with this database that we've already built up. So the L1 to L2 derivation process is how Optimism scans these L1 DA transactions and then is able to use that data to prove the correct execution of the Optimism transactions themselves. So the RISC-0 ZKVM, two of the, I would say, major innovations we made over the last year was recursion. I mean, this is not that major inside the ZK space, but our recursion is very fast, and we also added the ability to chunk up an arbitrarily large proof into many small chunks so they can be parallelly proven in parallel. Separately, you can also take a proof that has been generated and verify that inside a new guest program. This effectively allows you to, you could think of multi-thread your ZK program. So in the context of Optimism, we can start proving one block, and then we can launch a bunch of threads that will go out and separately prove all of these bits of Ethereum DA, and then we can use composition to bring them all together. So this is just a visual example of the way the sort of continuations process works. So if we're just building an Ethereum block, you know, we might split up the proving computation into about, who knows, like 4,000 segments. We actually can vary the sort of size of the segments based on the memory available on a particular machine. So you can tune the size of these segments that you then use recursion to collapse into a single succinct proof using recursion. And then, of course, once you do that, you can also have all these programs that are also running massively in parallel alongside each other that then all get combined using this guest mode composition, resulting in one final proof. And then you can do this, of course, Optimism has this concept of epochs, which are a whole bunch of blocks that eventually get posted to Ethereum. They usually, I think, contain about 1,800 blocks. So we then again use composition to create these proofs of epochs. But as you can see, the guest code for doing this kind of composition is also pretty simple Rust. There's a little more of color there. Obviously, if you're interested in this, checking out the source code repository and playing around with it is the best way to actually understand what's going on. Yeah, and summary from this sort of OP mission, we were able to actually roll up 180 Optimism blocks correctly, and I think this is probably the biggest general purpose ZK program that's ever been run, clocking in at about 190 billion cycles. As you can see, the times are not like the most encouraging, let's say, but there's a ton of optimization to be done there, and we really expect these times to dramatically decrease over the next couple months. And we could go into a lot of detail about how exactly that will get done, but there's inefficiencies across the entire system, but certainly adding acceleration circuits for things like Ketchak will be a big part of doing that. Yeah, so what are we going to be doing in the future with Zeth? We're going to make it faster, more chains, and full validity proofs for entire rollups. An exciting aspect of this approach is that you can, rather than, Polygon built an amazing ZK EVM, spent a lot of money on it, but say upgrading to Dankun is going to be complicated. So when you're building ZK EVMs by using the source code that already exists, you have the ease of keeping up with what's going on in Ethereum in general. But then if you actually want to experiment with changing how some of these VMs work, this framework gives you a way to do that, and a way that we've effectively proven can scale to the most complicated kinds of VM transactions in the space. Yeah, that's actually all I have. Do people have any questions? Yes, sir. Yeah, there's no reason. So the RISC-0 ZK VM is completely zero knowledge. So you could build an EVM. Like you could actually prove, if this were efficient enough, you could actually prove to Flashbots that you had some bundle, for instance, that contains certain properties without revealing anything using this exact same kind of code base. Yeah. Yes. Yeah, so let's see. The number of transactions, it varies widely based on how many GPUs you're using. Right now, these numbers were all from like 300 node cluster, but there's, yeah. We're expecting like a 10x improvement just because we really focused on trying to get the broad set of parallelization done. So all of this composition and recursive systems rather than the exact nature of the hardware acceleration. So yes, there's a lot of room for improvement in the GPU kernels, and yeah, we expect to see that pretty soon. Our goal, I think, is to get to somewhere where we could actually be proving these roughly in real time by the end of the year. Oh, prove, well, you can definitely prove some things on a phone. But I mean, like if you wanted to prove, so say like passports and everything now have these, you know, digitally signed identities in them. If you wanted to scan that and create a proof that, you know, I don't know, you were a Capricorn or that you're over a certain age or something, you could do that on your phone, and I think that would, yeah, minute, 30 seconds. So pretty practical, I think. Yeah, so that's actually tunable by this sort of segment size parameter that we have. So we tend to set it to just 1 megacycle, so 1,000,000 cycles is a segment, but the memory requirements are directly influenced by how you set that. So at 1,000,000 cycles, I think we're at like 8 to 12 gigs of memory. So you can readily target consumer cards, but if you do want to scale that down, you can. You're just inducing more recursion overhead at the end of the day. Yes? Yeah, I think just anything that you would normally need to run a validator node is nothing beyond that. So you just, oh, that's a good question. I don't know. Rami, do you know? Yeah, like how long does it take to get all the data to do this? I assume it's pretty quick from whatever RPC provider you're using. Oh, I see. I think I misunderstood what you were saying. Yeah. Yes, yes. Whatever. So the final succinct proof that represents all 190 billion cycles is milliseconds to verify. And actually, I mean, we spit out a Stark proof, but we also have a system to take that Stark proof and convert it into a Snark proof, which you can then post on Ethereum mainnet, and that will, well, it's on Sepolia right now, but we will be launching it to mainnet very soon. Yes. There are, I think there's some recent papers that came out that show that if you rely on certain conjectures that you can have some compounding effects there, but generally no, if you construct it right, yeah. Yes. Yeah. So I don't think the forks were too. I think Rami actually did most of the work here. So. Right, but I think we did end up building this custom Merkle Patricia tree, and that mostly has to do with just making sure that we can get memory over from the host side to the guest side in the most efficient manner. Like, I think it's used like a 0 copy structure. Right, yeah, everything expected to talk to like an RPC node or something like that. Yeah, you should generally, like I think the development flow we have in mind is you just start with the program that you actually want to run, and then see if the performance is acceptable. And then if it's not, we have a bunch of patched crates that use the sort of big int accelerators that we have, and we'll have more and more accelerators available, and the ability to write your own accelerators in the future. So you can, go as deep as you want to on the optimization front, but the idea is you should be able to prove out like the possibility of what you're doing, yeah, in a day or whatever. Yes. There's been a couple. We actually have proven bootstrapping for TFHE, and that takes about 1 billion, I think, cycles right now. Although that could be pushed down a lot. So Similarly, we just did a proof of speed run of Doom that I think, about 30 frames a second if you don't render, actually. So it's actually pretty close to being able to prove the state transitions of Doom in real time. I don't know how much of a use case that is, but yeah. What's that? Yeah, so right now, the way floats are supported is through, so we support the one flavor of RISC-V right now, RV32IM, which is integer with a multiplier unit. So all of the float is soft float put in by LLVM. So it's not great, but it does work. But the next version, we have a much fancier mechanism for doing this. All right, I don't see any more hands. So thank you, everyone.
You can pass on the mic. Yeah. Okay. To the stage.
Thank you, thank you. All right. Excellent. Yeah, so this is a project that started at Stanford. It's we're essentially like a team of 10 cryptographers. You should check out our website. We had recent new announcements, like an open source of our CKVM and some other things. Huge fan of the work of the people that spoke before. I think that work is great. This work is very preliminary, so not recommended for production use, but you can actually use your product today. It's fully open source, MIT license. So so for context, I'm Daniel, founder of Nexus. I studied at Stanford, cryptography. Been at this project since I was a student there, and does that work?
Yes, and I'm Jens, chief scientist at Nexus, and been working in zero knowledge for more than 2 decades by now. Probably most of you know.
Yeah, exactly. So we were excited to tell you all about our project, which, as I said, went live like a couple of days ago. So our project has a noble purpose. It's about human cooperation, about uniting the world's computers. And we want to get the computers of the world together for a single purpose, and that's essentially for all of us to come together and cooperate in the proving of just arbitrary computations, which has been a topic discussed in this event. So here's just like a weird question, let's say. Is there a way that we can unite every single of our computers, right? Let's say your phones or computers, data servers, whatever, into a single CKVM, one CKVM. So you can imagine all of these dots as computers and all of them working together to compute as a single machine. In other words, can we build a global verifiable supercomputer that is powered by large-scale proof aggregation, such that the total computing power of the system is proportional to the collective computing power of all of its nodes? And, well, the reason we would be interested in that is to reach a massive scale in the compute power available to be designated for proving, right? So, after many months of work, we're happy to open source the first versions of these two systems, which is the Nexus CKVM and the Nexus network. And they're actually essentially the same systems, but at different scales. The Nexus network is an instantiation of the Nexus CKVM in a distributed computer network. And so, yeah, this is fully free for everybody to use. You're invited to fork it or whatever you want, MIT Apache 2 license. You can see our website, nexus.xyz. And you will find a white paper there as well that explains all of our technologies and implementation. So, as it was being discussed in the last talk, right? It is an interesting problem, that of like accelerating CKVM computations, right? So just a really big goal. Is there any way we could reach 1 trillion CPU cycles proved per second, let's say within 2024, right? That's a huge number, and I'm going to put it into scale. So before I move into the next one, the cost of CK, as in measured as the relative cost of proving versus the cost of computing something without proving, so the cost of verifiability. Well, there are many numbers. Some people here might disagree because it depends on multiple things, but we're talking about CKVMs. It's usually between 10 to the 9 to 10 to the 6 in the cost, right? So what I mean by this is that the cost of verifiably computing something is around 1 million to 1 billion times more expensive than just running the same program, right? And so we can do many things, right? We can grab a snark and combine it with a circuit, and maybe run it on a CPU, maybe you run it on some GPUs or FPGAs, and maybe you get to 10 to the 7 or to 10 to the 6. But to get here for the cost of CK, to decrease by, let's say, 5 or 6 orders of magnitude, it's not enough to just throw GPUs at it, right? GPUs or FPGAs are going to give you some 10x, 100x in performance. So we're interested in the problem of achieving order of magnitude reduction for CKVMs and zero knowledge in general, but specifically for CKVMs. Another way to phrase this problem is on the side of the speed of a CKVM. And here, hertz, as was mentioned in the last talk, right, is CPU cycles proved per second. So current CKVMs exist in this bound, 100 kilohertz, 100 CPU cycles proved per second. There are many details about it, but let's say that to achieve 10, 100, 1,000, a million X, to get to 1 trillion hertz, that's a gigantic jump. So the question is, how can we make this jump? And well, we care about it so that we can actually get to the next level of Ethereum, right? We believe that there will be millions of CK rollups all running in parallel. So we want to support that future for Ethereum. And so, for context, I made these slides. Jens didn't make them. He would disagree with some of this history, right? I put it here in a way that it looked convenient to explanation, right? So you have IPs, the creation of zero knowledge proofs, PCPs, the famous snarks, then the starks. Then you have Halo 2 that innovate on this for using accumulation. And then in 2022, we saw a new type of accumulation system, right, which we call folding, right? And it was Nova by Srinath Sethi and Abhiram Kotapalli and others. And we've seen an explosion of many theoretical papers on folding and folding-based incrementally verifiable computation, that's IVC, and folding-based proof-carrying data, which is a generalization of IVC to the distributed setting. But all of this here is actually theoretical work. There exists an implementation of Nova from Microsoft Research, from the original author, and our friends from Lurk have been working on a fork of that, which is very good. I invite you to check it out. We have essentially done from the ground up our own implementation of Nova, which is now open source as of 2 days ago, along with other of the elements here, for example, CycleFold, and soon to be released, probably within the next week, an implementation of Supernova and many other things. So the point is, this type of folding schemes have very nice properties that essentially have to do with proof accumulation. I will talk a little bit more about this, but essentially reaching the next 1 million X, or orders of magnitude improvement in CKVM speed, requires new cryptography. Like GPUs and FPGAs is not enough. To get 1 million X, it's a totally different question. So now we're going to talk about the components that essentially allow for something like this to happen. And this is the scientific part. So Jens, want to chat about it?
Sure. Okay. So part one is that we're not going to achieve 1 trillion hertz without doing some parallelization, right? So we are building a CKVM network where you have like multiple layers of this construction, right? So there's a sort of like an execution layer, there's IVC, there's compression, there's a lot of tools that go together. And we think a big part of the solution that we have to provide is actually providing that structure, right? So whereas you could sort of like have a lot of those layers by themselves if you do smaller proofs, but when you want to prove something really big, then we need to think this layer through.
Yeah, I can talk about it. So the traditional CKVM architecture is conceptually simple. You grab a snark or a stark or something like that, then you grab some circuits for a virtual machine, and then you combine the two, and then you prove them. And yeah, maybe you have some more structure than that. Maybe you have multiple layers of recursion, but it essentially looks like this. And it hasn't changed in a lot of time. What has changed is the different types of snarks or how to arithmeticize things. We believe our CKVM is the first one to present additional structure. Like the step is only seen at the top. We have multiple layers in the machine with multiple parts of the architecture, individual components in a, let's say, highly modular fashion that are supposed to essentially contribute to this goal of having a really, really powerful prover mechanism. So a way that we like to think about it is an analogy with artificial intelligence, right? In 1962, you would have 1 or 2 layer neural network. But then in 2012, actually what we see are convolutional neural networks that have much, much more structure and architecture to them because, well, that's what's required to get to the next level. Of course, the analogy is not direct, and it doesn't have to be true, but, well, at least we think that's the direction in which we are going. So CKVMs need more structure than what currently exists to reach the next scale of compute that we are thinking about. So as mentioned, right, this is open source under MIT license. As I mentioned, first from the ground up in ArcWorks, open source implementations of folding schemes. By from the ground up, it's like we didn't take code from anybody else except ArcWorks. So Hypernova, that's an asterisk, that's not public yet. But you will find the other things there. Spartan and Zeromorph are not folding schemes. Zeromorph is a PCS. Spartan is a modified snark. But essentially what I'm trying to say is you can find all of these building blocks of folding schemes to build whatever you guys want, totally free. It took us many months to engineer these systems, to benchmark them, et cetera, et cetera. But they're free to use for everybody here. And so, yeah, you can find them there. Once again, not Hypernova, that should have had an asterisk.
Yeah, okay. So this is like an inside view of what does the system look like, right? So we have like this massive parallelization. We need to reach the goal of a terahertz network. We're using a 2-cycle of elliptic curves. That's part of the cycle fold scheme, right? And then we're using these folding schemes, Nova right now. We're looking at supernova and hypernova, so that's upcoming work. And you have like proofs that sort of like both live in one curve and the other curve, and you sort of like aggregate them up across the tree, right, to get a combined proofs for everything. So you basically have folding steps all the way up through this tree.
Right, but so here's the important part. Each node in the tree of the folding process is part of this incrementally verifiable computation. So it can be performed by untrusted parties. So that's the important part. Each node here can be a different computer that doesn't have to be trusted. And we can all come together into building this tree and generating a proof. And you can verify each point there. Then from taking this from theory to actual practice, there's a lot of engineering involved, and of course. But I mean, like this doesn't come as magic, right? Like we are making trade-offs here in order to be able to achieve this. And you have the really tiny proofs, for example, from Groth 16 or other snarks like Halo 2 that fit it within Ethereum very well. You have Starks, which are asymptotically and concretely larger in terms of proof size. Well, folding, those are gigantic proofs. Those are like megabyte type of size of proofs. But having really large proofs allows us to do all of these nice things about recursion and PCD and all those sort of things. I know some of you might have some questions about communication latency on such a network, but that's a different discussion. You can compress the proofs, you can do some nice tricks with subtrees and all those sort of things. Jens, maybe you want to chat about the proof compression?
Sure. I guess the slide in some sense says it all, right? So, so the idea is basically that you do composition, right? So you take the large widgets you get in Nova before you send it over the network, right? You would want to compress it first, so that layer you can put in snarks to compress it, and that gives you more efficient communication in the network. And also when you have you're through with the whole proof, right? Then you would want to compress, so you would ultimately want to compress down to something. If you want to use it, for instance, Ethereum, you would want to compress it down to something that you can put on the blockchain.
Yeah, the compression is very tricky because you have to handle a 2-cycle of curves. So for example, for this step, we use a modified version of Spartan. And then for the next one, we use Halo 2. And then we have to emulate the secondary field on the primary field. And then there's many more details. What you will see in the open source is this step completed. We will soon have the next step completed. And there's many details, right? But this diagram is just a simple version.
Okay. So we are also building a virtual machine, and the idea is that we want to optimize it for proof of performance. And it looks a bit like this. So it's not RISC-V, but it's sort of like inspired by RISC-V. So it's a 32-bit structure. It has a program counter. It has 32 registers, and then input-output behavior. So you can give it input, you can give it auxiliary data, right? So a witness can be both something you want to keep secret to have privacy and zero knowledge. It can also just be for scalability, right? So something that's auxiliary data, just that the proof the verification complexity of a proof should not depend on that input.
Right. So our CKVM supports any sort of like LLVM target specifically, or as well anything that compiles to RISC-V. What we do is something relatively simple. We translate from RISC-V to NVM. And the translation is simple because actually NVM was inspired by RISC-V. And so further improvements to the NVM are expected. But the two main benefits of the NVM is one, well, prover performance. The NVM is way simpler, way smaller than RISC-V. And number two, security. By just having a smaller, simpler to understand machine, it is easier to audit the circuits. And the circuits are actually totally public. You can go and check out the circuits for the NVM right now. The circuits are fairly large in terms of number of constraints because we haven't taken any smart optimizations, but those are in the works. In particular, the NVM is also designed for this idea of a precompiled system that is allowed by the non-uniform IVC property powered by Supernova, which allows you to have essentially like custom instructions in your instruction set architecture that are accelerated. So you can inject custom circuits as additional instructions in the CPU architecture and, well, essentially build your own CKVM system without having to, I don't know, depend on our choices. For example, this instructions are like SHA-256, KICHAC, ECDSA signatures, and importantly, because right now Nexus is based on Nova, which supports R1CS. Soon we'll move to Hypernova, which supports CCS. And so that means that your custom instructions in the virtual machine can be written in CCS. Okay, so for context, CCS is a constraint system that generalizes R1CS, Plonkish, and AIR. And so essentially, if you have your circuits for your custom instructions in any of these formats, you can just plug them into the CKVM and build your own CKVM. You have anything more to say about it? No? Okay. Okay, excellent. So just in terms of user experience, we think this shouldn't be a big deal. It should be extremely simple, right? It should be as simple as creating a new Rust project and just doing Nexus proof, Nexus verify, and then you as a developer should not know anything about all of the cryptography that we are doing, and it should just run, right? And actually, this is the case. You can just try it out. It will run. So I have to say the CKVM is still very slow for many, many reasons. When you will run it, you will see that it runs at about 100 cycles per second, depending on your machine. But at least it runs. So, right. So yeah, fully open source, usable today. And the Nexus One has many of these components already built in, right? The Nexus virtual machine, the Nexus proof compression system, an IVC and PCD system that allows you to compute this in a distributed manner, the memory checking mechanism that uses Merkle trees, a compiler or transpiler from RISC-V to NVM, weakness extraction system, and many expected upgrades. So we're running out of time. We had a demo here. And actually, let's finish it like this. If you go to proof.nexus.xyz on your device, on your phone, you will see a little bit of how this looks like in real life. So proof.nexus.xyz. Yeah. Oh, I see many of you there. Yeah, so if you click connect, what you can see is you can see your peers, the speed at which they're producing proofs. So this is computing ArcWorks, MSMs on your web browser. And you can see the total throughput of the network and how the total throughput of the network at the top center is equal to the addition of all of these systems. And well, I'll be honest, this system is not very efficiently distributing proof generation. It's just doing something very naive. But it is already, oh, too many people. Yes. So yeah, we're very excited to launch this fairly soon. But what we just did is we united all of our devices to compute tiny portions of the proof together and then accumulate them all and build a single gigantic machine with, I don't know, like 50 people or something like that. So yeah, you know, any device, almost any device can supply compute from your laptops, your tablets, your phones. The idea is that we'll have proof mining, right? You will earn some, I hope the SEC doesn't get at me, right? But some Nexus tokens out of it, right? As you supply compute and as we all come together to computing and producing proofs for Ethereum. And well, we think this is like there are some nice values with this, right? Human cooperation. We can all come together to have a future powered by truth, right? And so it's the coming of science together, the coming of engineering together, of open source software, and of human cooperation. And so, yeah, thank you very much. This is totally free, open source, Rust, MIT license. Please feel free to use it. We're out of time, right?
We have a break now.
So. Oh, okay. No, yeah.
Yeah, we've got.
me. Feeling it tell you the truth. Your talk is cheap, but your words cut deep. Don't you understand that you're bringing me down till I'm stuck on the ground? I need to turn on the noise so I can make the right choice. I need to know, can't this be different? Or should I let this go? I want to leave this all behind. Can we close this door for peace of mind? 'Cause I'm not the one to scream and shout, and you don't want to talk this out. And I don't want to lose me, so I need to choose me. Choose me. So I need to choose me. Choose me. I'm feeling it and I don't want to lose me, so I need to choose me. I've let you cross me. My mind shuts down and I can't compete. My body's shaking and I'm scared to say just how I feel. Gotta turn on that noise so I can make the right choice. I need to know, as if you won't listen, I might just have to go. I want to leave this all behind. Can we close this door for peace of mind? 'Cause I'm not the one to scream and shout, and you don't want to talk this out. And I don't want to lose me, so I need to choose me. Choose me. So I need to choose me. Choose me. I'm feeling it tell you the truth. Your talk is cheap, but your words cut deep. Don't you understand that you're bringing me down till I'm stuck on the ground? I need to turn on the noise so I can make the right choice. I need to know, can't this be different? Or should I let this go? I want to leave this all behind. Can we close this door for peace of mind? 'Cause I'm not the one to scream and shout, and you don't want to talk this out. And I don't want to lose me, so I need to choose me. Choose me. So I need to choose me. Choose me. I'm feeling it and I don't want to lose me, so I need to choose me. I've let you cross me. My mind shuts down and I can't compete. My body's shaking and I'm scared to say just how I feel. Gotta turn on that noise so I can make the right choice. I need to know, as if you won't listen, I might just have to go. I want to leave this all behind. Can we close this door for peace of mind? 'Cause I'm not the one to scream and shout, and you don't want to talk this out. And I don't want to lose me, so I need to choose me. Choose me. So I need to choose me. Choose me. I'm feeling it tell you the truth. Your talk is cheap, but your words cut deep. Don't you understand that you're bringing me down till I'm I'm stuck on the ground. I need to turn on the noise so I can make the right choice. I need to know, can this be different? Or should I let this go? I want to leave this all behind. Can we close this door for peace of mind? 'Cause I'm not the one to scream and shout, and you don't want to talk this out. And I don't want to lose me, so I need to choose me. Choose me. So I need to choose me. Choose me. I really need to, and I don't want to lose me, so I need to choose me.
Espresso doesn't have a mic. Oh.
Hi everyone, we're going to get started again, so if you could make your way to your seats. We've got Benedikt from Espresso speaking soon.
Awesome, thank you. Do you need a clicker, right?
Yeah, a clicker would be good.
Here's a clicker. Yeah, sure. All right. Please be seated. So give like a minute for people to get like seated. I would start the. All right, let's get started. So next we have Benedikt Bunz, Chief Scientist and Co-founder of Espresso Systems, and also Assistant Professor of New York University, and also a PhD graduate from Stanford. I actually used to take a course from him as well. All right, let's welcome Benedikt.
Thank you very much, and yeah, thanks for putting this event on. Yeah, so today I'm going to talk about why sharing is caring, and in particular why sharing a sequencer is caring about interoperability. So rollups are this beautiful technology, and what they allow you to do is they allow you to horizontally scale Ethereum. So I have an application layer service that executes transactions and proves state. So I have a bunch of rollups here. Each of them has a bunch of transactions. They execute them, and then they prove that they executed these transactions correctly. And this has several advantages. One of them is that it can shard the computation. So each rollup can process a different set of transactions, and the computational load for each rollup is completely independent of what the other rollups are doing. The other one is that powerful nodes can help weaker nodes verify the state. So the rollup server, a powerful unit, can basically prove that it did the computation correctly, either through ZK proofs or through fraud proofs, and then weaker nodes can assert that the computation was done correctly without having to redo the computation. So that's another scaling benefit. And then the third one that sometimes maybe is a little bit underappreciated is that you can have, or maybe it's not underappreciated, but you can have totally different types of computations and types of VMs. So you can have EVMs running on these rollups, but you could also have a RISC architecture or some application-specific rollup, and so these systems can get significantly more parallelized. Unfortunately, though, these systems also have a significant downside, and this is mainly due to the fact that they're run by isolated sequencers. So the sequencers are the ones that choose what transactions get included into the rollup and in what order. And this has several drawbacks, and one of the main one is that the interoperability between apps across the rollups is limited. You would have to bridge assets or bridge things from one rollup to another first, which has some cost and latency. And this basically gives you a significant loss, and this loss is that you lose synchronous composability. So unlike on the layer 1, you cannot have one smart contract that calls the next smart contract that calls the third smart contract if those smart contracts run on different rollups. It also fragments the liquidity. So some funds that are used on one rollup, you first have to bridge them over to be used on another rollup, and this is bad in many DeFi applications in general. And this is incredibly problematic, especially if we think about what Ethereum and blockchains are really about. They're about their unity, not their fragmentation, right? The idea and the power of blockchain comes from the fact that everybody can use the same system and seamlessly interoperate on the system, and I can build a smart contract without knowing what all the other smart contracts are out there, and still users can use them together, they can chain transactions and all of that. So seamless interoperability of applications is the promise of trust minimized infrastructure, and what really differentiates Web3 from Web 2, where I have these isolated walled gardens. So what is this? So let's dig a little bit deeper of why this is and what the roll-up sequencer actually does. So in the roll-up sequencer, we have a bunch of users that submit transactions to the sequencer. Then the sequencer summarizes these transactions and produces state update plus a proof and posts that to Ethereum onto a smart contract, which checks the proof, or there's some fault-proof mechanism. It doesn't really matter, and basically accepts the state update. So the sequencer determines the rollups blocks. You can think of these things as blocks, and in particular, it determines which transactions are included and in what order. So the sequencer could also outsource this job of selecting the transaction to some other party or to a mechanism. So for example, an auction. So it could, for example, have an auction mechanism where it basically says, I'm going to build the block that the highest builder, so-called builder that builds the block, I'm going to propose the block, or I'm going to post the block that the highest bidding builder is running. We can think of this as an auction, and this actually even happens within Ethereum itself, where this is called the proposer-builder separation. So there is this proposal, or there's been this proposal, it's been actually around for a long time, but it's sort of recently gained a lot of attention again, of base sequencing. So if you look at the first Arbitrum paper, for example, the original Arbitrum paper, it didn't have some separate sequencers. Users would send their transactions directly to the L1, and then the L2 node reads the transaction, the finalized list of transactions from the L1, and executes them to determine the state transition. And then the rollups would basically read, so the rollups would read from the L1, and then basically just post the proof to the L1 that the state update was done correctly. So this has some advantages, this old sort of original version, which is that, first of all, it inherits the security properties of the L1. So we believe the L1 is incredibly secure. So this system should also be secure. It should be, for example, much harder to censor transactions using such a based rollup versus a centralized sequencer. But it also can have improved interoperability, not just between rollups, but even between rollup applications and the L1 applications. Why is that? Well, the person, now the L1 leader, the L1 proposer, gets to post these transactions to the L1, and it could sort of interleave them with other L1 transactions. So it could, for example, say, okay, I'm only going to, it could give a user a guarantee that here this rollup transaction will execute if and only if this other L1 smart contract transactions will execute. However, so why did we move away from that? Well, let me first talk about this. So ultimately, users want a secure, convenient, and low-cost experience, right? And satisfying the user's intents will be the most efficient across contract of L1. So this based sequencing is really, it seems like the goal, right? So why do we move away from this idea? Well, well, we'll get to that in a second. I just first want to talk about, how a proposer can promise user atomicity. So this is the concrete example. So user says, I want my transactions on 2 rollups, or a rollup and an L1, to be executed atomically, right? I want, to buy one asset on one rollup and sell another asset on the second rollup, but they only want these things to happen at the same time, not one or the other. And the L1 proposer can promise this. It says like, I will do this. And then it creates this super block, it signs it, posts it, and posts it to the L1. And it can even economically stake funds behind this promise. So it can back up its promise. First of all, it could put its reputation behind it. Maybe that's not that useful, but it could even say like, I promise you this, and if I don't do this, I will get slashed, okay? Because you can afterwards verify whether both transactions actually executed at the same time. And this is how this shared proposer can give economically backed promises to users. It can satisfy users' intents or back them up economically. And the user knows that, well, the proposer likely does not want it to get slashed, so will honestly execute this transaction. So what happens in a scenario where we have these shared proposers? So say we now have a builder that wants to try to satisfy some promise over 2 rollups that have different sequencers. Well, now it can promise that, and if not, it still says the same thing. I promise that, and if not, you can slash me. But the problem is that now it builds 2 blocks. It builds a block for rollup A and a block for rollup B. But the problem is maybe rollup A accepts its block, but rollup B doesn't. So even without any fault of the builder, one block got accepted and the other one doesn't. So it couldn't satisfy the promise. And then it will get slashed. So to be honest, no rational builder would actually try to provide this, because it simply cannot give this promise, right? Even if everybody is honest here, it cannot give this promise of atomic execution. So this leads to this topic of proposer promises, or pre-confirmation, which is that a shared proposer for a bundle of multiple rollups can do a bunch of things. It can provide these fast pre-confirmation. It can coordinate message passing between ZK provable chains, something like the Polygon ACK layer. And yeah, it can do a bunch of really cool things. And all of those have one thing in common, is that if it fails to achieve its promise, it will get slashed. So these are all economically backed promises. It can also, there's a bunch of other cross-domain user intents. One of the simplest one to think about is just sort of bridging funds from one chain to another. This is, like there's much cooler things you can do, but even just sort of fast bridging between one rollup and another. So I send some funds on a bridge on one rollup, and I want to receive them on another. That sort of, already captures a lot of the power of these cross-rollup intents. So why aren't we running base sequencing yet? What is base sequencing missing? Why were external sequencers introduced? Well, one of the main reasons is for efficiency. It has, so if you remember the base sequencing, the original base sequencing proposal, every single transaction needs to get posted to the L1 and as an individual transaction directly by the user. External sequencing has much better data compression, so significantly lower DA cost. In external sequencing can collect transaction, it can strip the signatures over time, and can optimize it when to post them to the L1. It also can give fast, low-risk pre-confirmation. So L1 block proposals risk being dropped or reorged before the 15 minutes have elapsed. An external sequencer can pre-confirm pure L2 transactions by just saying, like, yep, I included this, and if you trust the sequencer, then you know this will happen. And it can include these transactions, especially the ones that do not depend on unfinalized L1 transaction. So is there a middle ground? So can we basically achieve basically the benefits of base sequencing, this shared proposing, while still having the nice data compression properties and sort of the nice pre-confirmation properties that an external sequencer gives you? And the answer is yes, base sequencing 2.0 with an external finality gadget. So the idea is that we put something in the middle here between the layer 1 and the layer 2. So now the users will submit their transactions to the L1 proposer still, but the L1 proposer doesn't post it on the layer 1. It instead posts it to a fast finality gadget where L1 validators can opt in. So this has much faster latency, so something like less than 5 seconds. And once the transactions are included on this finality gadget, then you know the order of the transaction. So all the finality gadget does is it agrees on the order of the transactions. But once I know the order of the transactions, the state transition is deterministic, right? If I know the order of the transactions, everybody can just execute them and knows exactly what the list of transactions is. So roll-up smart contracts on the L1 need to require that the transactions are first confirmed by this fast finality gadget, which is just a BFT consensus protocol operated by, and you can have the, you can have it be operated. Well, I cannot go back. One thing, you can improve the power and the security of this L1, this fast finality gadget by having the L1's validators participate in this finality gadget. So they also sign off that they've seen this order of the transaction and they agree on it. And you can have L1 composability. So if the L1 proposer still proposes this block, they can then build L1 and L2 blocks at the same time, right? So they can give satisfy user intents both over L1 transactions and a bunch of L2 transactions. You also have something called conditional finality. So the finality of any L2 transaction is conditioned on the finality of the most recent L1 blocks. It depends on. So if the last, if the L1 block forks, well then you need to fork also all the L2 transactions. But if the L1 block becomes final, then you already know the next set of L2 transactions because they were confirmed by this finality gadget. Okay, so what else is base sequencing missing now that we're used to roll-up sequences? One of the important things is the MEV capture for rollups. So enshrined rollup sequencer have additional revenue beyond the gas fee in the rollup, which comes from tips that users pay for intent satisfaction. So even just wanting to be first in the block. So they pay these priority tips. So vanilla-based sequencing is not economically aligned with the rollup. So in vanilla-based sequencing, the L1 proposer gets to order all of the transaction. So they get all of the MEV fees, right? Versus the rollups now get none of this. So what we're proposing is a mechanism to redistribute the sequencing MEV back to the rollups. So how do we do that? Well, what we're going to do is instead of saying instead of basically saying the L1 proposer directly gets to propose this block, what we're instead going to do is run this auction mechanism. So we run some public auction where basically we auction off the right to create the super block for the shared finality gadget. So there's multiple proposers that compete for getting the right to update all the rollups or a subset of them, right? You could bid on, say there's 5 rollups or 1,000 rollups, but let's focus on 5. You could bid on I want to build the block for 3 of them because I know that I can satisfy user intents over 3 of them, and then someone else bids on the other 2, or people bid on individual ones. And this shared revenue, so what we're proposing here is having one auction for all of these rollups, where you can, so basically a marketplace to become the shared sequencer for all of the rollups or a subset of the rollups. And this can actually be better for everyone involved than what we have than having separate auctions for all of the rollups. Why is that? Well, the problem with having these separate auctions is that as a proposer, I don't know whether I will win, I cannot satisfy these users' intents because I might win one of the auction, but not the other auction. Here, the shared auction mechanism allows me to bid higher on bundles of rollups because I know that I can extract or I can provide more value for a bundle of rollups. So how do we do this? There's many analogies to this. You could think of this as a music festival. I've heard that, so say we have a music festival and we have a bunch of bands, and the question is one challenge with this shared auction is how do we now split the revenue amongst the different rollups? So say we sell all of them together, how do we split the revenue amongst all of these rollups? Well, the analogy of this is say a music festival where we have a bunch of bands, right? And the music festival makes some money, but how does it split the revenue amongst the bands, right? How does it know, this one band was sort of significantly more important than the other? You could try to figure out some custom backroom deals, but you could also run a so-called combinatorial auction. So the way that a combinatorial auction works that basically proposers can bid on any combination of specific rollups. So they could, for example, bid on the individual rollups or the bundle, and then using this combinatorial auction, we can actually figure out how much each rollup would have gotten on their own, right? Because that's just the bid on, people will still bid on the individual rollup, so we know exactly how much a rollup was worth on their own, and we can use that to distribute the revenue from the entire combinatorial auction. But wait, how is this based sequencing? What about the L1 proposer, right? Like, so here we have this auction, a bunch of people participate there, but we've completely sort of lost sight of the L1. This sort of allows you to bring shared sequencing to all of these rollups, but we wanted base sequencing where we can even have interoperability with the L1. And the idea is that after we run, so the idea to bring basically the L1 proposer back, so base sequencing 3.0 sort of, is that after we run the combinatorial auction, we allow the L1 proposer, so we run a combinatorial auction, let's say sometime in advance for some slot, let's say tomorrow. And then the L1 proposer, there's some look ahead in Ethereum, so we know exactly who's going to be the L1 proposer for that time period. And what they can do is they can purchase the proposal right for any bundle at the winning bid, at the winning price. So say a bundle costs, 10 ETH, then they can buy it they can pay 10 ETH plus some premium, so maybe, 11 ETH, and for the winning bundle. So they can basically buy it back. They uniquely have the right to buy it back, which allows them to guarantee that they can build these shared blocks that include both the L1 and everything else. So what is shared sequencing after all? A marketplace, you can really think of shared-based sequencing as a marketplace. It's a marketplace where proposers can buy and sell block space on different rollups and the L1 itself. And why would they do that? Well, because buying this block space and buying these proposer rights allows them to satisfy user intents across many different rollups, which is both better for the users, but it's also better for the proposers because then they can charge fees for satisfying these intents. Okay, so thank you very much. That was the talk, and yeah. The egg layer, no, I think that, for example, the egg layer is actually incredibly compatible with this marketplace because it allows you, so first of all, what you could do is, you could say the Polygon chains, want to be always sequenced together, then they could enter the market as one unit, sort of saying that, all the Polygon chains are going to be, always sequenced together, and they get, you can only bid on all the Polygon chains together, and this actually makes it very compatible with something like Egg Layer, and also Egg Layer, sort of Egg Layer allows this shared proving, right? Which is sort of on a different layer. It's on a different level, and it becomes actually more useful when there's a marketplace where you can buy the proposing rights for many rollups at the same time. So, but yeah, I mean, I think that's. I think what's more important is having one marketplace. Like the fast finality gadget, it's more useful to have one fast finality gadget because then if I have one fast finality gadget, I know that the transaction is final on 2 rollups at the same time. So I can, for example, then immediately accept some bridging transactions, right? Because I know that, like, even if the finality gadget reverts, it will revert on both of them. what is more useful is, yes, to have one marketplace. I do agree that one marketplace is better, but I think that, I mean, maybe, there's like, as I said, you could have sub marketplace and then sell the super rights, but yeah. Yeah, thank you.
Yeah, thank you, Benedikt. I think my mic. Hello? Yeah, sorry for interruption, but we have a tight schedule, so I want to make sure we're on time. So next, thank you, Benedikt, for the awesome talk. And next, we have Irene Wu, Head of Strategy at Layer 0. Let's welcome Irene to the stage.
Hi guys, can you hear me? Perfect. My name's Irene. I am head of strategy at Layer 0 Labs. And today I'm going to be talking about, in the first ever talk on this, Layer 0 v2, which went live on mainnet about a month ago. And we'll be going through the design principles and how we achieved modular security through this. Okay, so for starters, a little bit of history here. Our founders, they all actually met in university about 15 years ago and were doing research in a Web 2 interoperability center and have built projects together over many years. One of them was a professional poker player, 2 others did AI research, and finally came back together around 2020 because they wanted to create a game. This was around the time BNB Chain had just launched, and what was fascinating was that there was actually usage. There were developers and users. It was the first time there was a chain outside of the immediate Ethereum ecosystem that had this kind of cachet and real adoption. So as lifelong gamers, they wanted to create something that allowed for gameplay on both of these chains. You look at all of the bridges that existed at this time, or anything that was empowering interoperability, and it was very, very primitive. These were wrapped asset bridges, which many of you may be familiar with. How wrapped asset bridge works is you have a smart contract, which is owned by some third party, and as a user, you deposit your funds into this smart contract. It's locked in there, and a synthetic asset is minted for you. It's a synthetic IOU. Essentially, should you cross this bridge back and we don't get hacked, you trust us, fingers crossed it's all good, you'll get your real stablecoins. But in the meantime, it has some representative meaning in this ecosystem. As developers, they would never have trusted this. And many of these early bridges were also run by very tiny multi-sigs of maybe sometimes the same people. And we've seen that, I'll get to it later, with hacks like the multi-chain hack, which then really ravaged, unfortunately, ecosystems like Phantom and other ones which were dependent on these wrapped assets. So they set out to create their own bridge. And as they were doing that, which was V0 of Stargate, which is a bridge that our team created, they realized what was a lot more interesting was the layer below bridges. Bridging is just one use case out of thousands for arbitrary message passing or sending data between smart contracts and disparate systems. Below that, you can do arbitrary contract invocation. You can do a lot more than just moving assets. And that was what led to, well, here is the hacks portion. I think I actually have updated slides rather than the PDF. I just want to make sure we're using the updated slides. Gil. One second. But anyways, you guys can take a look at this here. All 3 of these hacks were due to upgradable smart contracts. The multi-chain hack was also one in which the multi-sig was compromised, and the first hack and the last hack there mentioned were wrapped asset bridges. And understanding what the actual reasons are for hacks in cross-chain is incredibly important. Rarely are they because of a validator set and an issue with the decentralization there. It's most often because of the design principles which found the actual architecture of the bridges. Let me see if they're going to update the slides. 1 second. Okay, no worries. While we're waiting here too, a little bit of background. Part of what got me interested in interoperability is that I spent several years doing research in anti-surveillance technology. I studied computer science, and a lot of my interest was within the United States, how our governments, police forces, all of this use technologies to surveil and potentially enforce particular ideologies or particular disenfranchisement. And at the time, I was looking specifically at machine learning being layered over things like body cameras. But it led me to get more interested in the ideals of censorship resistance. And it's something that stablecoin issuers, many DeFi protocols talk about a lot, but we rarely talk about in the cross-chain context. So what would censorship resistance look like in a cross-chain context? It would look like not being able to reorder messages. So as a message passes across, it's first submitted on the source chain and then delivered in a particular order. If you're trusting a service for this, a team that has built a messaging service but can reorder these messages, it means they can extract more MEV, for example. If they're attached to a high-frequency trading firm, there's more value there that they can extract from your users. If you are a government, let's say 10 years from now, and you're conducting votes on-chain, you have everyone voting from different L2s, you want to be able to ensure that it's not possible to withhold a whole slate of votes. If it is, the entire integrity, the entire thesis of what we're all doing here around blockchain technology being adopted at large is breakable, it's corruptible. And that's a tenet that matters quite a lot to me. And in V2, we really enshrine into the protocol. Thank you, Gil, for making this work. There's a slides link that you should be able to use. I can also, while we're waiting, talk a little bit more about V1. There would have been a slide on this in a moment. V1 launched just about 24 months ago. And the hypothesis we had for this, as we were creating what was meant to be a response to this design question of how might you build both an evergreen and evolvable interoperability infrastructure protocol with research and time. Given that we're at this event and it's hosted by Stanford Crypto, I'm assuming that many people here come from an academic research background or have a lot of reverence for what comes out of academic research. The belief is what people use today. Gil, you actually might want to just pull up the slide link. Oh, okay. Okay. Give me one moment here. Thank you guys for bearing with us. It's all good. Which email is it supposed to be shared to? Okay. Dom, if Lexi's there, can you have her share it? Okay, awesome. Yeah, what I was saying about academic research is if you look at 2 years ago, ZK proofs weren't performant yet. But now, today, there are teams like Succinct, there are teams like Polyhedra, RISC 0, who have proven that it's possible to build tooling so that it's much easier, for example, to build a custom ZK-like client. And so when you're creating an infrastructure protocol that you're intending for people to use to secure, say, $1 billion worth of value or $2 billion worth of value, it's incredibly important that it's designed so it can evolve with better practices. And that means if, for example, there's now a ZK Oracle that you could leverage, how can you do that in a way that enables modular security, meaning I can select that, I can even propose a DAO vote and it can trigger it and add this change. And at the same time, the immutable components, where there could be a vulnerability in a smart contract, are preserved. The integrity of that is still there. That's a really important piece, and it's what informed how we designed V1, but even more importantly, how we designed V2. Hold on. I think I might be able to help with this. Okay, you should have access now. If you go to your drive and you search for it. If you go to top right slideshow, or view slideshow, yeah. Okay, amazing. Thank you guys so much. And for everyone in the room, thank you for bearing with us. As I talked about, that was the scene for 2020. The bridges that existed were highly insecure. We set out to build our own bridge. As we did so, we realized what was much more interesting was the layer below it, in which you can enable arbitrary contract invocation and a lot more. But the design question then is, how might we design an infrastructure protocol that is both evergreen and evolvable with research and time? And this is very much rooted in just belief in science and research. And why I emphasize protocol is because there are services. Services are products which require the liveness of the creator company to maintain the integrity of the product. That's, for example, like AWS. There are outages with AWS, and that causes real issues with DeFi protocols, causes issues with relayers, causes issues with many other key components that right now limit the mainstream adoption of what we're creating in this space. It also requires that that team has venture funding, that they're alive. If something happens, a horrible accident, or they run out of funding, your Slack connect with them is gone. That's not DeFi, that's not crypto, that's using some service. A protocol is something that is immutable. You can use it forever, in perpetuity, without trusting that I'm alive, without trusting that I'm still raising venture funding. It's something like TCP/IP or the underlying protocols that have allowed the internet to scale and allowed people to build whatever they would like with it. And so these are the three design principles that came out of that design question. First of all, immutability. Why is this so important for infrastructure? If you can change the underlying infrastructure, that means these subsequent two tenets are breakable, they're peachable, and that's incredibly important to look at when you're choosing your stack for infrastructure. Immutability means that when you choose to integrate Layer 0 for interoperability, there's nothing Layer 0 labs can do to upgrade it and introduce new vulnerabilities, even if there is good intention here, and I'll talk about some notable hacks that have been caused in this way. Then permissionlessness. You should be able to use the protocol without having to engage with the developers in some BD contract. You should be able to run your off-chain components or choose the validation methodology on your own time, rather than delegating trust into, say, Layer 0 labs to tell you what that should look like. And you should also be able to run one of these components yourself, and it should be easy to do that as well. Censorship resistance I spoke about. For messaging, that means if we have governments that are doing voting on chain from many different L2s, you should be able to trust that you can't remove packets of data across chain. So we launched V1 24 months ago, and we're incredibly proud of the fact that we achieved 90% market share. There was product market fit around our omni-chain fungible token standard, more than 600 applications that integrated it. But there were some really key pieces of feedback, particularly ones that for me caused us to go back to those original design principles. The first one there is, in V1, we used this model for off-chain entities that validated messages that used oracles and relayers. And the concept was that any entity that could retrieve and submit a block hash, that could be an oracle. Any entity that could retrieve and submit a transaction proof, that could be a relayer. Now, in practice, the relayer was handling both validation and execution. The challenge of that meant to build a relayer, you had to have wallets on all the chains you were supporting. We were paying for 80 million RPC calls a month, so we were always in the DMs of Infura and Alchemy and at their whims for downtime, uptime. It meant that we had to balance the gas tokens on all of these different chains. When we spoke to other teams asking them if they would build their own relayer, they tried, even teams like Gelato, some of the best in the relayer space, and it was very complex. So when you have this hypothesis that teams are actually going to build their own components to decentralize themselves, to own their security, what we found was nearly every single team settled for what we called defaults. Defaults were these test settings, and it used one oracle and one relayer. And the relayer it used was the Layer 0 Labs relayer. If the relayer ever had any downtime and you were on defaults, that meant your messages would halt. There wouldn't be any vulnerability, but it meant that there was a liveness issue. And on the Oracle side, even though there were client-diverse oracles, Polyhedra launched a ZK-Lite client, Google Cloud launched their own custom oracle, Chainlink spent a year and several $1 million building one for Layer 0 as part of their business. In practice, it was very difficult to build one yourself. So once again, on a spectrum of centralized and decentralized, if you settle for defaults because it's easy, engineers don't have too much time, you're choosing a far more centralized option. And in my mind, the product decisions you make, which are things like defaults, the settings you choose there, that's how you articulate your view of the world. Your designing technology and product decisions are how you articulate your philosophy and how you want people to use your product. And for me, when I think about who we should be building for. It's this person. I dropped out of school when I was 16. I had very little money, only a laptop, short attention span, and was at hackathons like trying to make money. And with V1, it was impossible for a student to do that. If you have $100 or very little, you're not going to build a highly performant relayer that can handle execution and validation. And so in V1, though the protocol did achieve those three principles of immutability, permissionlessness, and censorship resistance, it was so prohibitive that in practice, it actually hadn't. And we spent the last year building V2 to solve these issues. So now Layer 0 V2. It's live on mainnet. It has been since January. Testnet was in December. And what's new about V2? It still achieves these three design principles. I think it actually pronounces them even more. Most importantly, it decouples the execution and verification that had been bestowed to the relayer component, and it now makes the modularity and the future-proofing of the security layer easy enough for that college dropout to run it themselves. Unified semantics are still there. So if you're building across Monad and Barachain and also 3 different OP stack chains, all of this, you're using the same syntax, the same approach, rather than trying to, like, in a janky way, put together multiple bridges. And it's a mesh network of 50 plus EVMs and non-EVMs, many, many more to come. Here you can see a walkthrough of a message that comes from the source chain to destination. The sender OAP box you can imagine as a smart contract I'm using for, say, an Irene token, and I'll walk through that in a second. In that contract is where you have the LZ send function. Then you'll see this purple box where it says LZ endpoint. A key component to our architecture is that the protocol utilizes append-only opt-in libraries for endpoints. So endpoint V1 still exists. It secured $50 billion of value. It's non-upgradable, so we can't make changes to it. If you've pointed your contracts towards those, you can still do that in perpetuity without anticipating some sort of change to it. But now we've added endpoint V2 to the library, so you can point your contracts towards those. It's backwards compatible. We've also introduced something called lazy non-sorter enforcement. So you can see it where it says lossless channel. In V1, everything was sequentially non-sorter enforced. That meant every single message had to be delivered in the exact order in which it was submitted. That was important to achieve censorship resistance, but the feedback we heard from developers was that for 99% of use cases, that's actually not practical. Now with lazy non-sorter enforcement, messages have to be validated in the order in which they're delivered, but they can be executed or consumed in any order. And then in that central area, in between the passage from source to destination, is a major change. And we'll zoom into this. We call it the security stack. Rather than the oracles and relayers from V1, we've now separated what the relayer had done before. The executor box here, it plays a commoditized role. It's just moving the message once it's been properly verified. So that comes after the DVN component. DVN stands for Decentralized Verifier Network, and I'll walk through what can be a DVN. But the key thing here is, as a developer, when you are deploying your contracts that have integrated the Layer 0 protocol, you select your own consortium of DVNs in an X out of Y out of N arrangement. So that means, let's say today I'm launching, let's see if I can go back in a second, but I'll walk through this so you can see. Today I'm launching the Irene token, and I want it to be omni-chain. I want it to be on Barachain and Monad on day 1. Maybe 2 weeks from now, I want it to be on Base and a few other chains. Very few people are holding my token. It's not that much value. So I select for my DVNs the Nethermind DVN. It's one that uses geographically diverse validators. This is a team I really respect. And they're very Ethereum aligned. And then I also choose the Gitcoin DVN. And these are both live. Gitcoin is running one. I intend to participate in public goods funding. So this is aligned for my community. I say that 2 out of 2 of these DVNs have to agree on the validity of this message. And one of those DVNs that is absolutely required is the Nethermind DVN. For the executor, I choose to use the Layer 0 executor. And as I said before, it's a commoditized role. So Layer 0 is competing in the fair market with other executors. And it's permissionless, so I can swap it in and out. Now it's 2026, and there are 1 billion people who hold Irene tokens. We have a DAO competing with Irene DAO, and we are using an open source executor. I charge 5 bips on top of that, but because I'm securing so much more value, our protocol has grown. It's now time to add another DVN, which is one composed of all of the top Irene holders, and now it's a 2 out of 3 consortium, and I require that Gitcoin and Irene's DVN must secure and validate the message for it to pass. This is showing an example. Hold on, I'm trying to go backwards now. This is showing an example of the modularity of the security configuration. Without writing any new code, you can change that setup. And DVNs can be native bridges. They can be other bridges. They can be a ZK oracle. This is how layer 0 actually future-proofs the interoperability layer of your protocol. And what I've written there just shows how X out of Y out of N works. For the executor component, once the verification has passed, then I can choose an executor. In this case, Layer 0 Labs runs one. I can run one myself, and that's where I can charge fees. Or I can always link my users to permissionlessly execute, so they just have to pay for their own gas and move their message. Why would you want to use an executor? Because it's a commoditized role, that's where you can add some features. For Layer 0 Labs, we compete by handling something called gas abstraction. If it requires for a message to pass 2 different gas tokens from Ethereum to Solana, rather than needing both ETH and SOL in my wallet, one click, only ETH, and the executor does the quoting and exchange up front. And I pay a small fee for that service. But again, I can always opt out or run my own or permissionlessly execute. What can be a decentralized verifier network? These are baseball card visualizations of some that are live on mainnet right now. Polyhedra runs a ZK-like client. Nethermind, I said, runs one. Animoca and Blockdaemon together have. These are all the different diverse approaches to validation. And we're not opinionated at Layer 0 on what you choose for the validation methodology for your messages. In fact, we very much believe that that should be in the hands of developers. We are competing at the transport layer rather than the validation layer. You can even see Accelerator and Chainlink here, their CCIP messaging service. If you believe in the middle chain approach, you can have that as a DVN. But then say your DAO votes to add a ZK-like client that was built with Succinct's SP1. Great, you can now push that. There's no new code. It's reconfigured. What can they be? They can be, like I said, native bridges, a ZK oracle, something new, something you've built yourself, always, without having to coordinate with Layer 0 Labs. So back to this person. When I was PMing the launch of DVNs, I was still thinking very much about my college dropout self, and I wanted to be able to run a DVN in under 1 hour myself, something that involves, say, a signer from Stanford Crypto, Harvard Blockchain, Berkeley's group as well. We've now managed to achieve, through a module we created, setting up that DVN in under 1 hour. This is the example I gave. Here are 2 projects that are already live on Layer 0 v2 and are doing things that are a bit more novel than just an omnichain token. Clusters was built by Fubar, who's a security, crypto, Twitter content creator and also just incredible developer I have a lot of respect for. He's created a cross-chain name service. So now Irene / is one name for 7 wallets across different chains. He's built that with Layer 0 v2. Decent is a cross-chain swaps module and protocol. They handle full liquidity cycles for users, so you can on-ramp and off-ramp. That uses Layer 0 and Stargate. They also made a great video that gave me chills, kind of reminiscent of urine-type videos about the state of crypto today. ERC 6551 at MPC Day 2 days ago with the Future Primitive team, we announced that now they are natively cross-chain. Every single ERC 6551 token-bound account leverages Layer 0 v2 and can execute ownership of different NFTs across chains. And now restaking tokens, LRTs, are using Layer 0 to be omni-chain. So they're horizontally composable. One click, you can burn and mint from, say, base to ZK sync. You don't have to wait the 7-day bridge back period and then go to another L2. This is my build this wish list. Only a few here, but I really actually want to see one-click cross-chain borrow lend, multi-chain account abstraction but applied. Right now, wallets are basically just doing like cross-chain swaps as a widget. We can do better. We can do something different and totally remake the wheel. Omnichain LRTs as a hat tip to EigenLayer. They keep sending us really great projects that are using Layer 0 to go cross-chain. I was a gamer growing up. I played a lot of Neopets. I want to see a game that is on multiple chains and has, say, like an action on chain A triggers a mutation to an asset I have on chain B. Now it has a crown and it's my Twitter PFP and it's updated. I want to see that, and I want to see it in a low latency format. And then chains treated more as programming languages rather than as commercial real estate. We sort of look at chains like they're our landlords and we're paying some tax to be there, when different chains are actually, inherently trade-offs. And with something like Layer 0, you can now design it so almost like you have a toolkit of these different languages. I want to do settlement on a ZK L2. I want to have my DAO accrue votes on my own app chain. I want liquidity from Ethereum. You can do all of this. These are the hacks I mentioned before. you have to think about owning your own security. These all came from instances in which too many developers and too many users put their trust into a service, into something that was upgradable and could change on them. Based off of the research I've done before, you can probably assume that I care quite a bit about people leveraging real privacy tooling and doing things that are both good and bad. The internet is neutral. You can create phishing websites. You can also create really great things. And at Layer Zero Labs, we believe in that too. We shouldn't be able to censor what you do, and you should be able to run your security as you wish. If it can be corrupted, it will be, and so you should choose immutability, and Layer Zero V2 is our articulation of that. That's it for today. Thank you.
And also, I saw there's some like empty seats, so please, there's empty seats in your row, just squeezing, so people standing can sit there as well. Yeah, cool. I'll let you guys squeeze in.
Oh, thank you.
Yeah. Awesome. So next we have Nick White, COO of Celestia. He's also graduated from Stanford. So that being said, let's welcome Nick to the stage.
Thanks, Kuhn. Hey, guys. How many of you have heard of modular blockchains before? Nice. Nice. Okay, good. That's what we're going to be talking about today. I'll give them a little more time to pull up the slides. How many people are Stanford affiliated here? Nice. Cool. Yeah, I'm really stoked that BAS is taking the lead to host more events, and not just at SBC. So great work, Kuhn and the rest of the team. Looks like they're really close. Does anyone have a question about modular blockchains while we wait? Go for it. That's a great question. Oh, it looks like I have my slides. Basically, Tendermint was the most battle-tested consensus engine, and the Cosmos SDK enabled us to build a really minimal blockchain that had almost no execution, and ABCI++ allowed us to have special interaction between the app and the actual consensus, and that enabled us to do block construction with the erasure coding for DAS more efficiently. So that's why. But a lot of people think they were or people will get confused about what building on Cosmos means, and we just use the Cosmos software stack. But that's a great question. Okay, let's back up a little bit. Yeah, so the title of my talk today is Modular Expansion and the Path to 1 Million Rollups. So I want to talk about what modular blockchains are, how the modular blockchain ecosystem is expanding, and what the end destination is. So, as Kuhn mentioned, I'm the COO of Celestia Labs, and since modular blockchains are still a relatively new topic, I'm going to start by just giving a background of where modular blockchains came from. And so first we have to start with monolithic blockchains. So the idea of blockchains started in 2008 when Satoshi published the Bitcoin white paper. And what was so novel about Bitcoin was that for the first time, you could implement a system that had rules without rulers. Now, in legacy systems of cooperation, if you want to have people all cooperate under a set of rules, you need someone in power, a ruler, to enforce those rules on everyone else. And the problem with that is that a ruler can corrupt the system and abuse it to their advantage. So what's so cool about blockchains is that they remove the need for power hierarchy in systems of cooperation, and you can have everyone enforce the rules on each other as equals, as peers. And the way that you do this is you have each of the users run a node of the system. And the node has a copy of the set of rules, and it's continuously auditing the blockchain and making sure that all the transactions are valid. None of them are breaking the rules that everyone agreed to. But the problem with this is that such a system is not scalable, because if you want to verify every single transaction, you have to download all the data behind every block and verify every single transaction one by one. And so if the amount of transaction data increases, that means the amount of data you have to download and the number of transactions you have to compute and verify also increases. And so eventually, if the blocks get too big, if there's too many transactions you're trying to process, you as the user, the participant in the system, can no longer actually continue to verify the chain. And so what this means is that monolithic blockchains inherently have a finite, fixed block size. And then once that block size is all consumed, the supply can increase even if demand increases. And so the fees have to go up and the blockchain becomes less usable as a result. And this is what's led to sort of like the age-old debate about sort of block sizes. Essentially, you can choose between having small blocks with high fees, but preserve decentralization because everyone will still be able to verify the chain, or you can increase the block size, which will give you lower fees and make the blockchain more usable, but then you end up losing decentralization because users get priced out of the ability to verify the network. And this is what led to, for example, the Bitcoin Cash fork, was this fundamental debate between should we increase the block size or should we keep it the same? And so in the second sort of chapter, I would say, in the evolution of monolithic blockchains was when Vitalik published the Ethereum white paper. And what was so groundbreaking about this was that if Bitcoin is a calculator that has very limited functionality, Ethereum is like a computer where you can run arbitrary application logic. And so it blew the doors open on the kinds of things that you could build on top of a blockchain. And the only issue is that as a monolithic chain, Ethereum only supports one single VM. It's sort of like a computer that only supports one operating system. So sort of similar to the EVM, imagine if you had a computer that only ran Windows, but you're a developer who builds, you want to build a Mac app, or you want to build something in Linux. It just fundamentally cannot be supported on a chain like Ethereum that only supports the EVM. So even though it opened up the design space for decentralized applications, a developer is still kind of like caged and constrained by the execution model that's supported by the chain. And this leads us to sort of the third chapter of this story, which is the dawn of this idea of modular blockchains. And this came around in 2019 when Mustafa Al-Bassam, one of the co-founders of Celestia, published the Lazy Ledger white paper. And in that paper, he re-envisioned what blockchains could be, how they could be designed and implemented. And essentially his idea was that you could actually take the functions of a blockchain that are coupled up in a monolithic system and then actually uncouple them and decompose them into separate protocols that are each specialized for that specific function. And then you can layer those protocols on top of each other and build applications from that. And you get some really cool advantages. So first of all, in a monolithic system where you have to download all the data and you have to verify every single transaction one by one, in a modular system, if you want to verify the chain, you don't have to do as much work. And the amount of work you do does not have to scale with the amount of transactions that you process. So instead of downloading the entire block, you just sample, you take a tiny sample of the transaction data, and instead of verifying every single transaction one by one, you verify a proof that all those transactions are valid. And so in the old case with a monolithic blockchain, as the block size increases, all of a sudden your node is no longer able to keep up with the network. But in a modular setup, even as the transaction data increases, you as the user are still able to verify everything that's happening. And the only constraint is that in order to make this secure, you need to have more so-called light nodes in the network to make it so that it's safe to increase the block size. But if you have users that run light nodes in their wallets, on their phones, in their browsers, then you get this effect where even as the demand for block space increases, the amount of block space you can provide can increase as well. And so you end up being able to have a flexible amount of block space, elastic block space. And so even if there's more demand, the fees of the network can stay relatively stable. And so instead of having to worry about having big blocks, small blocks, basically you can have the best of both worlds. You can have big blocks with low fees while still remaining decentralized and verifiable. And then the next superpower of modular blockchains is that because you decouple execution from the DA and consensus layer, you have the ability to define whatever kind of execution environment you want to run. So you're not limited to the EVM, you're not limited to anything actually. You can run SVM, you can run MoveVM, Cosmos SDK apps, literally any kind of execution. It could be a totally custom execution model. It's totally up to you as a developer to define that for yourself. And so it's sort of like, rather than be stuck in Windows, you have optionality between Mac and Linux and a whole gamut of different execution models depending on your use case. And so where Bitcoin was a calculator and Ethereum is like a computer, Celestia is like a cloud computer. So what I mean by this is that in Web 2, cloud infrastructure at its root has a data center that provides raw compute resources for developers to go and launch their own virtual machines that implement sort of like custom like logic for whatever web application they're building. And then in Web 3, the equivalent is a modular stack, where instead of having a data center, you have a data network like Celestia, and Celestia just provides raw block space upon which any developer can come and deploy their own custom virtual blockchain, which is a rollup, and they can define custom execution, all tailor-made to whatever application that they're building. And so now that we covered the history of monolithic to modular blockchains, we have that background, I want to shift gears to the path to 1 million rollups. Now you might probably be thinking that, like, well, why 1 million rollups? That sounds kind of like an absurd number. It sounds very complicated and scary. And I think, I mean, the way that I think about it is that where crypto is today is sort of like the very early days of the internet in the 80s, where there was maybe a few hundred servers, just like we only have a few hundred chains today. But if you fast forward to today's internet, we have over 200 million different websites and web applications that people use on a daily basis. And this kind of just massive scale of experimentation and utility has been enabled because it's so easy for people to build new websites and web apps. And I think and if like that wasn't possible, then we wouldn't have the internet that we have today. That's been so useful and transformative for society. So modular blockchains, one of the goals is to enable the same thing. And I think that eventually, maybe 5-10 years from now, we're going to have a very diverse, rich network of different chains and applications. And it's all that experimentation that's going to yield net new use cases and enable like true mass adoption of Web3. And so luckily, that sounds really crazy, but fortunately, one of the superpowers of the modular stack is that no single team has to build all of it on their own. All the sub-problems are broken down into their own category, essentially, and there's multiple teams working to solve each one of the problems at that layer of the stack. And so it's a group effort. It's not, in a monolithic chain, it's one team who's sort of defining and making the choices and also having to basically build it all themselves. In a modular system, it's about cooperation. And specifically for Celestia, we're obviously very committed to making this whole vision a reality. And we launched our mainnet late last year. And since then, over 10 rollups have deployed on Celestia, including projects like Manta, which is the top, the third largest rollup by TVL, as well as Avo and Lyra, which together represent around 70% of DeFi options volume on Ethereum. And so the modular acceleration expansion is sort of happening as we speak. And part of what's powering it is the fact that Celestia is providing extremely cheap data availability costs. that it drops the cost to operate your rollup and to use a rollup for users by about 100x. And so, for example, Manta, since launching about 2 months ago, has saved over $2 million in fees, and they've been able to pass that saving on to the users. And anyway, I want to talk like a little bit more about just the high-level things that are necessary in order to actually enable a world, like a future where a million rollups is actually possible. And I think like this is just a very high-level sort of like grouping of different categories of problems. But data availability is sort of the layer that provides the scale and throughput and security for the system. Execution is about basically where the applications live, making sure that those are verifiable, and there's a lot of optionality for developers. Sequencing is about basically being able to provide censorship resistance and liveness guarantees to rollups. And then we need interoperability, because if you have millions of rollups, they're going to need to be able to connect with each other. If they can't connect with each other securely or seamlessly, then we're going to have an internet or like the blockchain internet that is extremely fragmented. And it's about like, the internet, any kind of network, what makes it valuable is the connections between everything. And last but not least, we're going to need really robust infrastructure. People who, when you launch a blockchain, it's not just about whether the blockchain itself works. You need to make sure that you have a whole surrounding infrastructure of block explorers, indexers, RPCs, things like that, to make it really, really easy for developers to deploy a new chain. So I'll go quickly into each category slightly to talk about where we are and then what's coming and what we need to still build. As far as DA is concerned, we currently have Ethereum and Celestia. And Celestia has shipped DAS, which is a step function change in the verifiability and scalability of DA. But we still, frankly, have pretty small blocks by the grand scheme of things. There's no way that we would be able to support 1 million rollups on 2 megabyte or even 8 megabyte blocks that Celestia can support. And so we really need to scale that. But in parallel to that, if we were to scale DA throughput, we would also need to make sure that light node adoption also follows suit. So, and in parallel to that, we're working on Rust clients that will be really easy to embed in browsers and wallets and phones. And then the very, very end game, in order to be ultra secure, we need private DAS, which protects from selective disclosure attacks. And what's really exciting is that there are a lot of new DA protocols coming to market this year, like EIP 4844, which should launch any day now, and Avail and EigenDA. And so I think we're going to see a big expansion in the DA category. In terms of execution, it's a huge list, and I won't be able to go through all of it, but what I would say at a high level is that we have really robust support for EVM rollups. So we have all the EVM, sort of Ethereum L2 ecosystem building great tech, and so that's really, really well covered. But what we need, and we have one of the first Cosmos SDK rollup platforms, Dimension, that launched a few weeks ago. But what's still missing is actually more support for just general, all the different VMs that are out there. And we need more people to experiment with custom VMs that are sort of tailored to a specific application. And lastly, I would say that we need more robust and performant proof systems, because some of these rollups are just have multi-sig bridges, or the proving system is actually quite slow or expensive to operate. But I'm really excited about this category specifically because we have all these general purpose rollups launching, like Eclipse, Movement, and Initia and Fluent, which are bringing Solana, Move, and Wasm rollups to life. And we also have teams like Argus, which are launching the World Engine, which is a VM that's tailor-made specifically for gaming. And we're having, I think, a lot of insane progress in ZK VMs, both in terms of developer friendliness as well as the proving speed and costs. And so I'm really excited for Succinct and RISC0 and Valida. And in the interest of time, I'll move on. In sequencing, I also think this is really quite a pain point currently for the modular ecosystem, because most rollup frameworks only really support single sequencer mode. And I mean, some of them do have like exit mechanisms on the L1, which is really good. But overall, there's not really good safety and liveness guarantees, nor actually it's like just safety of the bridge guarantees with many rollups. And so I think I'm really excited by the fact that there's a ton of teams now working on shared sequencing that will make it so you can easily plug into a pre-existing network of sequencers that will provide all these like good guarantees of safety, of liveness and censorship resistance. And what's really cool too is that some of them are targeting not just decentralization of the sequencer set, but also giving superpowers to your rollup, like MEV protection or MEV capture, or things like atomic inclusion for cross rollup transactions. So there's going to be really cool innovation. A lot of teams like Astria, Espresso, Radius, and Fairblock are actively in testnet, and I think very close to launching. And then when it comes to interoperability, I also think this is quite a pain point for the current modular stack. The reality is that between rollups, it's primarily just committee-based bridging, and this is obviously not very secure. And what we need is trust. We need to move to a model of trust minimized bridging. A lot of that is dependent on like better proof systems for rollups, which we are still kind of in progress of moving towards. And we also need to make sure that the user experience for people interacting with modular sort of rollups is seamless. And so I'm really excited about the work that's happening with account abstraction that enables you to have sort of like a unified account across many different chains at the same time. And also teams like Skip and Leap Wallet, who are building APIs and SDKs that make it really easy to sort of like route or like create transactions that route across multiple chains. So as a user, you don't have to worry about doing all these different hops yourself. Oh, and last but not least, I'm really excited about actually aggregation layers and proof aggregation as sort of the end game for interoperability. And last but not least is infrastructure. So in this category, there's been a sort of explosion of rollup as a service providers. And there's too many for me to actually name. But I would say the good thing is that the support for EVM-based rollups is really robust. But frankly, where we can improve is expanding support for more frameworks and actually more VMs as they come online. And eventually, also, a lot of these rollup as a service providers are still sort of like hands-on. But what we want to move towards is a fully self-service type of ecosystem where you could come to the platform and just click without interacting with anyone, click and deploy a custom rollup of your design, similar to what we have in like cloud providers like AWS today. And that even though I went through that long list of all these ingredients that we need to have for a world with 1 million rollups in it, there was one key ingredient that I left out, and that ingredient is actually the rollups themselves and the rollup developers. If we, as the modular ecosystem, modular infrastructure ecosystem, build all these components, but then no one comes to use them, then what's the point? And so I think anyone who's out there who's a developer and is interested in trying this stuff out, I think there's a massive opportunity to push the edge and the envelope of what's possible to build in Web3 by tapping into all the unique superpowers that the modular stack can offer. And really, I think of it as sort of like a candy store for someone who loves to build decentralized systems, because there's just so many cool things that you can dream up and do. And so in light of that, I'm really excited to announce that we're going to be doing a modular hackathon. The first modular hackathon, we're calling it the Infinite Space Bazaar, and it'll kick off sometime in March, and it'll last around 45 days. And there's going to be bounties and rewards for all different kinds of, using all different kinds of tools, and we're involving a lot of modular ecosystem partners. So stay tuned for that, and if you're interested, come talk to me afterwards, and I'd love to hear if you're thinking about building something. And that's it. Thank you very much. I talk about modular blockchains a lot on Twitter, so feel free to follow me and DM me, and I'd love to chat more, especially if you want to build something. Thank you very much.
Thanks, Nick. Next, we've got one of our teams from the Accelerator. Excited to introduce Michael from Zero Gravity. They are building the next generation of modular AI blockchains. So, Michael, take it away.
Just waiting for my presentation. How's everybody doing today? Pretty good? Yay. Feeling good? Feeling good? All right, let's hear it. Come on. Woo! Can I get a woo? All right, let's get some energy in this room. Come on now. As I'm saying this and waiting for my presentation to load very slowly. Yeah, back please. Cool. Well, first of all, shout out to Nick and Celestia for creating the modular ecosystem. We're truly standing on the shoulders of giants. So it's really exciting that I'm introducing today Zero G, or we've also been known as Zero Gravity. We're basically building the first modular AI chain. So we essentially help people launch AI DDApps through the fastest data availability layer. And you now know what a DA is, so I don't need to explain that, and my presentation's done. No, just kidding. We'll keep going. So let me talk a little bit about the team that's building this. So myself, I'm a serial entrepreneur. I started a unicorn company before, went through Y Combinator, summer 2016. Basically also worked at Bridgewater before, Bain & Company, as well as Microsoft, so I'm a bit of a hybrid, both technical as well as very well versed on the business side. In my company, I also drove about 100 million of contracted ARR before. And then basically through Thomas, who you see on the right-hand side, my grad school buddy from Stanford, I met Ming and Fan. He called me up late 2022 and he said, hey, I invested in Conflux. You need to chat with these two co-founders. They're the best technical co-founders I've ever met. I think you guys would be a great match. And then 5 to 6 months later, I exactly told them that these are the best engineers and computer scientists I've ever worked with. Ming spent 11 years at Microsoft Research. He wrote some of the first AI algorithms for Bing, also decentralized storage expert, and wrote some of the key papers like Tango and Curfew in the space. Fan has been a hacker since a young age. He holds 2 Olympic gold medals in informatics. Fun story behind that, once he won the second one, I think China passed a law that you can only go once to the Olympic informatics, and so he's the only one that actually holds that. He went to MIT as a computer science PhD and is now a University of Toronto professor, and then he was actually an intern for Ming, and that's how they met and then started Conflux together. And we basically came together and wanted to build something on a global scale and something that truly solves really big pain points in Web3 today. And so here's some of the key papers. So we're expert in blockchain scalability, AI. We've won a lot of top paper awards. And so just lots of brain power on this team. Super excited to work together. We've also had tremendous success on the fundraising side just because not only the team, the type of problem we're working on, and super excited to be supported by Hack, BBF, Symbolic, Bankless Ventures, and many, many other great funds as well. And so what's the problem that we're solving? So you heard a little bit about Celestia and data availability, and we're trying to take it one step further. How do we actually get to Web 2 pricing parity? Right now, storing a gigabyte on Ethereum costs almost $60 million. That's insane. Like, why would you want to store data there besides transaction data? And then if you compare it to Amazon S3, you know, it starts at 25 cents, but then, of course, you have to add all the retrievability and so on. And really, 70 to 99% of gas costs are spent on storing transaction data. And so it's really important to solve this problem to get to parity. So in a way, the analogy, it's like L2s are getting to par in terms of execution with Web 2. But then it's like having a fast CPU and really slow RAM. So we're basically figuring out that RAM part. And so what that means is if you have really slow RAM, you can't build applications like on-chain AI, on-chain gaming, high-frequency DeFi. It's just not possible. You don't have the throughput. So as an example, if you want to scale to 10 million transactions per second across 1 million rollups, as Nick mentioned, you need 5 gigabytes per second in DA capacity. No DA layer today solves this, so somebody needs to work on this problem. And if we don't solve this problem, we're also going to miss the AI boat in Web3, because every company in the future is going to be an AI company. 70% of any administrative function can be automated. It's potentially even more, given some of the recent research papers, but this is an important problem to solve. And so if you then look at the use cases, well, how do you actually deploy something on-chain AI? So there's a few frameworks. One's called ZKML, one's called OPML. In this case, OPML, so we're partnering with Aura, for example. You need to store the actual model on chain. If you're trying to store a Llama 2 model, for example, that's hundreds of gigabytes, storing that on Ethereum would be very, very expensive. Nobody wants to do that. So we have to basically figure that piece out. And then once you store the model, you also have to then serve the decentralized inference traces. And so if you have 1 million users, each doing a request of about 100 kilobyte, that's assuming some blended rate of text and video and so on, you're dealing again with a DA capacity of about 1.6 gigabyte per second. So gigabytes, not megabytes. Here's another example. Let's say you're trying to scale an on-chain gaming kind of platform. And in Web 2, like 100+ million users, very common. So imagine doing that on chain, and you've got 3% of those users saving and loading state concurrently. So then you're dealing with 100,000+ gigabytes per day. That's not something current DA layers can support. And so it's already a problem, actually. So DeFi Kingdoms is an example. With only 20,000 daily active users, they already have a state explosion problem. They have on-chain game logic, and they're dealing with 14 terabyte of data that they need to manage. They're running out of space on their EC2 instance, and so we can help solve all of this. And there are, of course, many other use cases, high-frequency DeFi, data marketplaces, large stream deepin, a lot of different applications that are really high performance that will need a really fast throughput DA layer. And so here's where we really come into play. So this is a bit how the architecture works. So essentially, we start with a client DA data blob. We have a dispersed server. That dispersed server essentially does the erasure coding. It basically splits the data into chunks. Those chunks get put onto different parts of the storage network, not all of the nodes simultaneously. And that actually then creates an aspect of horizontal scaling, the way that we do it. At the same time as that's happening, we write a validity proof and a KZG commit to prove the validity of the encoding to the consensus layer. We have a separate consensus layer. That consensus layer, as the storage chunks are coming in, is doing the data availability sampling. Once it reaches consensus, then we can also write a ZK proof to the underlying L1, let's say Ethereum or another L1, if you will. And so that's the basic setup. And with this particular setup, we can reach after optimizing a lot of integration pieces, we can reach a per node speed of 10 megabytes per second. And because it's horizontally scalable, and we will use a custom consensus that's DAG and POS based, we can scale that to 5,000 nodes. So therefore, the throughput is 50 gigabytes per second. And so that's basically 50,000 unlock compared to dank sharding. And it finally gets us into a territory where we can drive costs low enough that we're actually competitive with Amazon S3. So if you compare it, for example, against all of the other DA layers, so ones that are starting to approach this type of speed is like Solana Firedancer, for example. But then generally, if you look at the cost, you're looking at about 3,000 to 13,000 per gigabyte per month. And we're going to price at $50. So that true high-performance applications can actually be built on-chain. And so we're also not stopping there. We're going to introduce the first programmable data availability layer. So what that means is you can customize what the data type is, the number of replications, where it's stored, what the data persistence is. So you don't need to worry about data pruning after 30 days, for example. That's, you can just keep paying or stop paying, and then the data automatically gets pruned. And so that's why we started with a decentralized storage network as part of this design. And even better yet, you can actually save your entire state through a smart contract and load it later, and we deal with all the difficulty in the back end. And we don't stop there. We're also introducing today the first infinitely scalable DA. Not only have we figured out how to horizontally scale across nodes on the consensus layer, but we can also horizontally scale the consensus layers so that you have infinite DA capacity over time. So that as applications are growing in the AI space, for example, let's say you want to do decentralized training. I spoke with one AI company called Manifold, and they said, if we want to do really fast AI training, we need a 50 to 100 gigabyte per second capacity. And I said, bring it on, we're ready for the challenge. And this is how we're doing it. And we don't stop there. With this, you can also do dedicated DA. You can actually dedicate a whole consensus layer to a specific chain, let's say like Polygon or other ones, to have full reliability in terms of transaction costs, in terms of speed. So there's not going to be any spikes because you're not sharing your consensus layer with anybody else. And that's because of our design. And we don't stop there. We're going to introduce the first aggregated DA as well. So say you want to work with Celestia, but you want a fallback option for load balancing, then you can work with us. Or let's say you want to run it in high performance mode, then a lot of the transactions will go through us, but then you also have fallbacks just in case you want to work with Eigen or with Celestia. And then the benefit of that, again, is 100% uptime. You can load and save state to anywhere. And it's really the Web3 collaborative spirit that we're all here for. And so this is my attempt at a very nerdy joke. And I showed this joke to all of our some of our investors. And I got blank stares, exactly all of this from here in the room. So it totally bombed. I totally failed at this stupid joke. And I had to actually explain it. And so it wasn't funny at all. And so when you explain a joke, usually isn't very funny. So basically what this means is you add up all the consensus layers together, the infinite ones. You add the storage, you add the aggregation, and then we don't just have modularity, we have modularity squared. So yeah, it totally bombed. But luckily, we have support from our community, and I was saved. And so really thank our community for helping me out on this one. And so let's go a little bit back to the on-chain AI use case. So we provide kind of the core infrastructure. We start on the data availability side. We also help with the model and the data side, where you can actually store a model, and then serve the decentralized inference traces. And then the execution layer, currently we partner with partners to do AI agents, autonomous agents, ZKML, and so on. And so here's some of our partnership network. You've got kind of the L2s and L1s, like Polygon, Arbitrum, Fuel, Layer N. And then on the AI side, we've got Aura and Modulus Labs, also Stanford Accelerator company, eStorage and Talos, and a bunch of other AI and kind of AI gaming companies as well. And then roll-up as a service providers, of course. And then one thing I should mention too is that we will work together with Eigen and Babylon to actually secure the different and infinite consensus layers so that we have economic security guarantees that we can provide as well. And so also announcing our roadmap. This is very much a draft, so it might change in the future, but basically in 2 weeks we'll have our public testnet open. We've already been doing a lot of key integrations. Our mainnet phase 1 will launch end of Q2, mainnet phase 2 end of Q4, and the first product that we're kind of bringing to market is this AI DA concept. Then we'll work on aggregated DA, infinitely scalable DA, and dedicated DA, kind of in this order. And of course, going to support a lot of our community through social channels, major conference participation. We'll try to figure out a points program as well. So lots of exciting engagement with our community. And so if you want to get involved, definitely join our social channels, our X, our Discord. Our Discord is full of memes, so you'll laugh your ass off, just like I have. So definitely check it out. Telegram, and then our draft Gitbook is already online, so you can already start looking at some of the code, some of the deeper technical details. So definitely check that out. And so that's it. Again, introducing the first modular AI layer, and join us to make AI a public good. That's our mission. And follow me on X. Check out our website, and also add me on TG. Thanks, everyone.
Thank you, Michael. Incredibly excited by what you're building. I think like one theme that you're seeing here is that the teams that kind of we're supporting and that we believe in are those that are really building at like orders of magnitude above the current standard. So next, we have Sandeep from Polygon. I think he needs no introduction. So Sandeep.
Hello.
Actually, sorry. Just one more thing, guys. There are seats. Come, sit down. Make yourself comfortable.
Yep. Hello, everyone.
I was not told that I'm going to be presenting here, like I have to present slides. I thought this was like more like a fireside. But luckily, I have one slide one thing I wanted to, kind of discuss specifically. And I think you guys are already, many of you guys who are active in the Web3 space, is like the aggregation. Basically, I think Nick also talked about it, and then Michael also talked about it a little bit. We believe so basically, this whole blockchain scalability, industry, I would say, originally we all started with these monolithic blockchains, like Bitcoin is a monolithic blockchain. That means you have one single state machine, Ethereum, Solana, all of these are, and many kind of L1s, I think most of the L1s, few of them tried sharded, which are like basically sharded state machines. Like when I say state machine, I mean a blockchain is nothing but a state machine. It's a ledger, right? And that ledger stores who holds how many tokens, how many eigenlayer points, and things like that. And points basically, which looks like the biggest innovation of our industry currently. And airdrops, of course. So who holds what? Like that's the ledger, stores today, and that's the state machine. And these monolithic state machines, they are very good. We have the composability across these smart contracts. Like on the top of the state machine, you write these smart contracts, and then those smart contracts interact with each other. And that has always been touted as the most use case, or the biggest value of blockchains, that you can have composability between different smart contracts, which are applications. But the problem is that if you have single state machine, no matter how much optimizations you do, at the end you are hitting the same database, right? So, for example, Solana has done a lot of good work over there, and there are multiple other, like Monad is doing with EVMs, and there are multiple other blockchains who have tried to optimize the performance on one single, I would say one single state machine. Problem is that no matter how much you scale, no matter how highly performant you make it, there is always the limits of physics starts approaching over there, right? Like, like for example, some of these blockchains have 10,000 TPS. With some more optimizations, you could probably go to 20,000 TPS. But then you have you are doing parallelization, which wherever there is a concurrency, those transactions are failing and all that. So it stops, like beyond a certain point, you cannot scale those monolithic blockchains. And then, then came the modularity, like the modular blockchains approach, wherein everybody can launch their own blockchains. People can have different app chains, and people have sovereignty on what they want to choose, what kind of VMs, what kind of decentralization profiles and all that. But the problem is it leads to fragmentation. Like I think many of you guys who use blockchain extensively, you'd have seen like you have to bridge from this chain to that chain, and it's a mess, right? And the end game of blockchain is where these blockchains start feeling like internet. Like when you join internet today, you go to booking.com and you look for your flight, and then you go to the payment page, and then on the payment page there is some payment kind of engine, and that engine basically you use to make the payment using your credit card. And it's not like you have to bridge your funds from one chain to another. Like your credit card has your funds, and then you can pay it on any particular website wherever you want to pay. And this is not true for blockchains as of yet. And the aggregation thesis is actually talks about that. Like this modularity kind of takes the blockchain scalability to kind of internet level scalability. You can have hundreds and hundreds of, or thousands of blockchains, in fact millions of blockchains. And I expect, and I will argue why I feel so, that there will be 1 million blockchains in next 5 to 10 years, app chains to be precise. But they will all be interwoven together. Just like on internet we have TCP/IP, similarly on blockchains we will have one single, because this is basically about trust. So we'll have single layer of trust. And as of now, it's pretty much clear in the research circles is that single layer of security and safety is zero knowledge technology. And that's what enables aggregation. And I'll talk more about that. But before that, this is one part that we have not done a very good job at. When people think about Polygon, what is Polygon? There is Polygon POS chain, which has this massive number of users, I think in the last 2-3 days, 1.1 million daily active addresses. Even with Solana having 1/10 of that fees, I think Solana has 650K addresses daily active. So there's huge number of retail using over there. If you go to the DEX screener, you see the number of small trades that are happening on Polygon PS are a lot. And then there is Polygon ZK EVM. The ZK enthusiast here will know that there is Polygon Maiden project is there, which is basically building a custom, a VM which allows privacy on the client side for the users, and so many other things even Avail, the data availability solution that you see today. It was incubated inside of Polygon. Then we spun it off because we believe in Ethereum and Ethereum's data availability more. So many things have been there, and we have not done this good job of explaining Polygon. And to me, Polygon, what we are trying to do, Polygon, and we don't care if there's a short-term value accrual and token and these things. What we are trying, and what I started into this ecosystem and I got into the scaling side, I wanted Polygon to be a part of this new infinitely scalable, internet scale network. So that's the basic requirement for us. Whatever architecture we are working, it took us 2 years to reach there. But the architecture now we have, if you talk around research circles, they will tell you this is the only architecture which can actually scale to million blockchains. I'm actually saying very openly, the aggregation architecture Polygon is now, we launched the V1 of this. It can actually literally scale to 1 million blockchains. And that's our core goal. We want to build a planetary scale, internet scale, Web3 network, blockchain network, which can have millions of these blockchains. But for the end user, just like it feels on internet, it will feel like you are on one single chain. You have one single balance and it can move around. And that's what aggregation enables. So, very briefly, I think people, who have not been following, let's say until 2023, early part of 2023, there were primarily these, monolithic blockchains, single state machine, all the transactions happening in one place. UX good in terms of the composable smart contracts. But, again, scaling limits, you cannot scale Polygon POS, you cannot go beyond, let's say, 200-300 TPS and all that. At the peak of these inscriptions, it went to 20 million. And I think many of us, you would have seen, then when this inscriptions, tsunami came, I think Polygon POS was the only chain which was able to take 18 to 20 million transactions per day. And I think Avalanche went down, the fees, on Polygon, the peak fees went to 10 cents. On Avalanche, I think the peak fees was on the C chain was $400. Ethereum, the fees went to $600-700. And Arbitrum one went down. There's so many blockchains that went down because you have the scalability limits. And I don't know, even it was very good that Polygon POS really cranked it hard, but who knows, any of these monolithic blockchains could have faced congestion at least, if not downtimes. So then in 2024 and I think later part of 23 also, you have seen this OP stack, Polygon CDK, now Arbitrum Orbit. These kind of stacks have come up and people are launching these app chains. And now we are becoming this completely fragmented area where people have to bridge all the time. And then when you're bridging from one chain to another, you have to rely on 3 securities, chain security of chain 1, security of the bridge, and security of the chain 2. And we have all seen that, probably more than $1 or $2 billion have been lost just because bridge gets hacked in the middle, right? So having a single security zone is what zero knowledge technology can enable. And this is what we say, that the evolution of scaling, from monolithic to modular, especially building on top of what modular, kind of architecture systems provide with DAs and execution environments. Aggregation can make all of these blockchains feel like one single blockchain, and also have all of these blockchains in one single security zone. And how does it work actually? So essentially you see that these we have mentioned 4 or 5 chains, but this could be, there are already some L1 blockchains are joining in. There could be thousands and thousands of these chains. And all of them have their ZK proofs. And on the ZK proofs, we have really improved the performance of the ZK proofs. And today they are totally feasible. and the per transaction costs are like 0.000402 actually on some of the Polygon provers. And so you can have all of these chains, all of them are basically submitting their proof to this aggregation layer. An aggregation layer combines all of the proofs into one single proof, and you are into a unified bridge contract. When you have that, then what you can do is you have a transaction, let's say you have a gaming chain, let's say CDK chain 1 in this diagram, you have a gaming chain and you are playing a game there and you earn $5,000 worth of gaming tokens there. And now you want to convert that into USDT, but the markets are available on Polygon ZK EVM or let's say Arbitrum, like if assuming they are connected, or any chain which is connected, let's say Near blockchain, which is going to connect into this AG layer and other L1s also. So you can actually initiate a swap transaction there on your app screen. And for you, you simply click a button. That app actually does your let's say deposit transaction and then submits the proof, ZK proof to the AG layer. And the AG layer, the chain 2 where you are actually swapping, let's say Polygon ZK EVM, quickly sees your proof and it sees that this transaction, which is an incoming transaction from some other chain, is actually a part of this ZK proof of chain number 1. So it can trustlessly accept it. There's no crypto economic security there. There's no OP, optimistic, kind of this thing over there and all that. Although those things can be applied on top of it for, I'll come to that, like for even faster atomic transactions. But point being, this is the security, like mathematical security you are offering. There's no crypto economic security required when the ZK proofs are coming in. So basically you do this transaction, it goes to chain 2 sees that this is a part of the proof, swaps, and deposits your USD back to this chain. And now when the chain 2 submits the proof, the chain 1 sees that, okay, there's an incoming transaction, but there is a proof, and this transaction is a part of that proof, and then your money is back onto you. So for as a user, you click and you see like step 1, step 2, step 3 in like probably 10, 15 seconds, and then you have your money back on your chain. Like OKX chain, for example, is a very big example over there, which will have like, let's say, huge amount of liquidity, and you have an app chain, which is, let's say, a social chain or gaming chain, whatever, and people are, playing and earning value, and they can exchange that value directly onto the OKX chain without, having to think about bridging and all that. It all happens in the background. Like some of the technical folks here, you'll say, okay, even if there is a proof, there is some level of bridging happening here, right? So who provides the liquidity on the other side and all that? But the fun part is, because this is aggregated ZK proofs, you will have single representations of those, smart contracts. Let's say USDC will have the same, like interconnected smart contracts across the chains. So when you actually are moving your USDT from one chain to another, you're simply burning that token here and then minting the USDT on the other side, trustlessly, mathematically, because it's a part of the ZK proof. So all of these tokens are basically not like right now when we say, oh, this chain has native USDT, this chain has native USDC, or this token is native on this chain. After this architecture is like, fully, kind of blossomed, every token is native to all the blockchains, like across this, platform. And that's when it starts feeling to you like this entire network, doesn't matter which blockchain you are on, if that blockchain is connected with the ZK proofs, with this AG layer or some structure like this, you feel like you are on the same chain. The experience is like you are on the same chain. And that's the end game for us, where we call, infinite scalability. As many chains people can launch, like thousands, and at that full blossoming, it will support like millions of chains in like, let's say, in like 1, 2, 3 years of roadmap. But even now, by the end of this year, it will probably support 1,000 chains or something like that. And, it will go exponentially from there. And then those chains have that, that's why we call it like AG layer is unified, infinite scalability and unified liquidity, is because, as I said, that all these tokens are essentially become native to all the chains. So for example, I'll give you one more concrete example also. Like, let's say you are a small app chain, you launch with the CDK layer, and then OKX chain is connected to the, OKX chain already will have, let's say, withdrawals from the OKX network, or Polygon ZK EVM, let's say, is connected to Binance. And now you want your users to bridge, money to your chain directly from Binance. Today, it's super hard because you have to get your chain integrated into Binance or OKX, and they have a pipeline of 50, 100 blockchains, and it's like they have to do it very securely, so they have to take time on all of the things. There is no way to do it easily. But when you are connected to the AG layer, if one chain is connected to an exchange, all the chains are connected to that exchange for the withdrawals. Because on OKX, what I will go is, I'll just select, let's say, ag layer, and then it will show me which chain you want to transact on the ag layer, and then you can select your chain. And this is what we call bridge and call function. So it will simply send it to the ag layer, and ag layer will know that, okay, this is this chain identity, and then drop the money on your address, withdrawal address, on that chain where you are expecting it. So the kind of network effects it starts bringing in is like next level after this. And also on Ethereum, you have a unified bridge. So on that unified bridge, you have billions of dollars of liquidity. And none of that liquidity, if you want to move from chain 1 to chain 2, you don't need to go to Ethereum, because all those ZK proofs are actually constantly updating the global state root on Ethereum. So you can move the funds from one chain to another without going to Ethereum, as far as the proof has been submitted by your chain, which is like depends on which chain you are and how frequently that chain is submitting the proof to Ethereum. And the way ZK scaling is, being optimized, we feel that, it will go to like probably 5 to 10 seconds for each of the chain. And then what is happening is, as I said, unlimited scalability. On top of this, let me go back. Back doesn't work. So on the chains, okay, it went. Okay, on this chain, then you can have on top of this shared sequencing, where the shared sequencing ecosystems are running the nodes, and we call this, let's say, clusters, or like, these groups of chains which want to interact with each other at extremely fast rates, because ZK proof is still going to take 10 seconds. Like you do a transaction, 10 seconds, the proof goes, and then other chain picks it up, and then they prove 10 seconds, and then it comes back to you. So it takes like 20 seconds, which is still like Ethereum's block confirmation. It doesn't, like when you go to a payment page on any other website you use, the payment page generally when it's loading, it takes like 5 to 10 seconds or 15 seconds. It's not that bad. But if you want instant atomic transactions, so for example, I am on ZK EVM, I want to take a flash loan on OKX chain, and then use that flash loan to take a leverage position on, let's say, some lending borrowing. I take the flash loan from lending borrowing chain and do some arbitrage on some DEX. Whatever money I get back, I want to deposit back into the lending borrowing pool and get the profit back to my chain. You'd be able to do it in one single atomic transaction using shared sequencing, because in the shared sequencing, these shared sequencers are running the nodes for all the chains. And the chains who want to collaborate within this shared sequencing environment, they can actually give the special sequencing rights to them, or basically like Espresso, for example, which is a prominent company in the space, they call it like a sequencer marketplace, right? So somebody can buy the rights of sequencing on your chain from this ecosystem if you are connected to this marketplace. And then what happens is that this block proposer proposes blocks on both of the chains. So this block says deposit the transaction onto other chain, and the other block on the other chain says take a flash loan, sell some arbitrage into the DEX, get the other tokens, pay back the loan, and deposit into this. So this atomic transaction in like milliseconds can happen to you. You can experience if there are chains which are participating in one common cluster. And it happens in Web2 world all the time. Like you have multiple banks which come into consortiums, and between those banks, if you are transferring things, these are much faster. And this is also going to happen in the Web3 space. And then you start feeling like when that kind of experience materializes, then you see, and this is where I will end my, I'll submit my case, is that when you have that level of composability across the chains, then by first principles, any application, whether it's a DEX or loan or game or anything, they would always choose to have their own chain. They will never be on a shared chain, like which is the integrated thesis, like let's say Solana side and all that all the applications should be on one single state machine, one single blockchain, so that they can compose with each other. If that composability is available across chains and you have same zone of security, my argument is all the applications will always want to choose their own app chains. Why? Because this is how Web 2 works today. When you are launching a mobile app, you don't go to some other big mobile app and say that, or Google or Gmail's mobile servers and say, can I host my app on your servers? This is exactly like this. When people are launching their app chains on shared blockchains, they are essentially saying that, okay, this is a public server, let me deploy my application here. And this used to happen when the Web 3 or Web 2 world was very, kind of new in 2001, 2, 3, when we were actually, like I was also starting as an engineer, and we used to deploy our applications to these shared servers all the time. And then some application on the one particular day will have heavy load, and then your website is down. And this is exactly what happens today. If you have a Bored Apes Mint suddenly on your chain, and you are a gaming application, and you are paying for the user's gas for better user experience, suddenly your gas fees is short by 5x. And on that day, your gas fees expense, which is $100, now it is like $500, $1,000 a day, and it can continue for a few days. Which application which wants to offer good user experience to their end users, which application would want to go through something like this? If you have an option where you can have a dedicated high service level blockchain for yourself, which is, let's say, single sequencer, so your experience is also 200, 250 millisecond, and you have dedicated capacity, and then your application can compose with any other blockchain on the other side, right? So then, like that's the argument about, and I'll finish over here, is that if that kind of composability is solved, which we are seeing that it's not even a research problem, it's an engineering problem, it's coming. When you have that, my submission is that no high-scaled application would ever want to exist on a shared blockchain, whether it's public or private. They will choose their own app chains. And the app chain world is coming. Aggregation layer is what brings it all together. Thank you, everyone.
Thank you, Sandeep. Absolutely love this vision. All right, everyone, we're going to have lunch now. It should be in both rooms, and we'll be back here in a little bit. Thank you. Also, a big thank you to all of our sponsors: Solana, Starkware, Polygon, Layer 0, Near, Shardium, IOBC, QED, CoinTracker, CEC, Eisner, Jensen, and DeFi.
Hey, 1, 2. 1, 2, 2. 1, 2.
Hey guys, we're gonna get started in about 4 minutes. So, yeah. Oh, hello? 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 Testing? Hello, hello? There we go. Thank you everyone for coming back for lunch. We have an exciting talk that is the opposite of the last one we had. By Dan Albert from Solana Foundation about why modularity isn't necessarily the next thing since sliced bread. So Dan, come, give it to you. Awesome.
All right. Thanks, everybody. Great to be here. My name is Dan Albert. I serve as Executive Director for the Solana Foundation. And I want to talk about how Solana scales at the speed of light with our integrated non-modular blockchain. Before I dive into that, I just want to give a brief history of kind of where Solana started and where we're at today as it relates to the network itself. This was Solana 5 years ago. It was me and a couple of guys in the founder's basement hand building machines to validate the first transactions. A couple months later, we had a couple of machines built. They gave me a corporate credit card and a Newegg account, slapped a bunch of machines in a rack. This is actually in a data center just a couple miles from here. These nodes are still running, glowing nicely green. And this is actually where Genesis was launched. This is where mainnet was birthed. This was August of 2019, 4.5 years ago. This is Solana Network today. Solana mainnet is running 3,300 nodes in over 400 locations in 40 countries on 6 continents. So it's been a wild ride and an incredible journey just to see the growth of the network, the physical footprint that is Solana. But what good is it? What can we do? Why did we build this? So I want to talk a bit about Solana architecture. This is going to be a little technical. I'm going to keep it hopefully at a level that isn't too boring for some folks, and talk about the global state machine that is Solana, and why we believe that global data synchronization on a single layer without sharding, without L2s, is the best way to go. And this is what we've built. So Solana was built to enable global state synchronization as fast as possible. The network and the runtime were developed together to enable continuous global streaming of data, transactions, and the propagation of those results. No latency, no downtimes, no waiting. So when messages come into the network, right, these are user transactions. You submit from your wallet. You want something to happen on the blockchain. On Solana, user transactions go directly to the block producer. There's no mempool. There's no waiting period. There's no unnecessary delays. You get your data directly to the block producer as fast as possible. Using Quick for flow control, users can submit multiple transactions in parallel. There's no need for transaction nonces, which you have on Ethereum and some other EVM ecosystems that sort of limit the parallelability even from a user standpoint. As soon as transactions arrive at the block producer, they are processed as fast as possible. The architecture is designed for streaming data with minimal delays as far as block receiving, block packing, etc. What this looks like, you've got a bunch of clients you see on the left. These are users signing things with their wallets. These are applications or bots sending transactions to the RPC node or can go directly to the leader. Quick is the transport layer. It's like UDP for flow control, UDP with flow control. This is used to prevent DDoS attacks, to prevent sort of network traffic floods at the receiver side at the leader. So we stream user messaging, we stream new transactions coming in directly to the block producer, and this is where we enter the SVM, the Solana virtual machine. The runtime was developed from scratch to be multi-threaded from day one. This allows parallel transaction execution. This is something that can't be found on ETH-L1 and a lot of the L2s is parallelism. And if you can have a multi-threaded parallel execution environment, all you have to do is add more cores and you can get greater parallelism, more transaction processing capacity. One sort of technical note on this, the way transactions are structured on Solana for our devs, transactions specify upfront when they are formed which accounts, which pieces of state in the blockchain they are going to access. What accounts do I need to read? What accounts do I need to write? This is a little bit different from the EVM model. And what this enables is knowing where these transactions need to touch in the blockchain state ahead of time allows for the block scheduler to optimize transaction flow for max parallelization. Another important thing that's actually was introduced to the network about 2 years ago is this idea of local fee markets. This is super, super important. Local fee markets, because we know which transactions are trying to touch which pieces of state, we can independently price access to a particular piece of data or a particular piece of state in the blockchain account database without impacting uncontested state. So what does this mean? If there's a hot NFT mint and everyone on Earth is trying to mint that sweet ape JPEG, fees might spike, but only on that mint contract. If you're doing your token swaps, if you're sending 5 USDC to buy a coffee, your fees are not impacted. So this really gives a lot of sort of dynamicism to the economics. You don't get global users blocked out just because one thing is happening on one part of the network. And so this really allows for a lot of different applications and use cases to coexist on Solana on the same network at the same time. Without being too academic here, transactions coming in from the network run through the block producer. This is all about parallelism and streaming data as fast as possible. Transaction packets come in from the network. They're batched. Signature verification makes sure that we are only processing valid signatures. This block here in the middle is a gross simplification. The banking stage, as it is called in the code, this is the runtime itself. This is the thing that takes transaction data and computes the output and gives you an updated account state, which it can then forward to the network. Transaction output is hashed through proof of history, which is our trustless timekeeping mechanism. So other blocks on the network can understand exactly what order transactions were processed in without having first needing to see the transactions in a mempool or agree to the structure of the block. I could spend a whole hour talking about this one. I won't. As soon as transactions are processed through the runtime, they are immediately broadcast to the rest of the network. Again, no latency here. We are not waiting. We're not queuing transactions up, building a whole block, and then sending it out. As soon as transactions are processed, they are sent to the network. This is a streaming data service, streaming transactions and the resulting changes as fast as possible. Lastly, data propagation. We send transactions in, they get packed in a block, they get sent out to the rest of the network. Local changes on the block producer are continuously forwarded to the network. And similarly, for non-block producing nodes, these pieces of blocks are received and processed as soon as they arrive. No waiting. In Solana, this is why I say it's not a blockchain, blocks are not discrete chunks of data, but rather checkpoints in time in this continuous stream of updating state, where everyone says, yep, at this hash iteration, at this time, we all agree that the state of all accounts in this sort of update stream was X, and we vote in consensus on that. But we don't build a block by selecting chunks out of a mempool, take it in, assemble this block, and then say, here's a whole block, go figure it out. Everything is streamed all the time. This is what the data propagation layer looks like. It's called Turbine on Solana. So you've got your block producer on the left. Pieces of blocks on Solana are called shreds. So shreds are forwarded to every validator on the network in groups of 200. So the first leader sends to the top 200 validators by stake weight, which in turn forward to up to 200 groups of 200 validators in sort of a pseudo-random network traffic pattern. The result being that we can get shreds containing new transactions, new blocks, to every validator up to 40,000 nodes in 2 hops. So putting this all together, what is the limitation, right? We always talk, oh, Solana's so fast, Solana's so cheap. It's true. But the real limitations are hardware and physics. Solana is designed to scale with hardware. The protocol does not have any baked-in latencies or delays or wait for this block or wait for this mempool. Transactions and data and blocks stream through the network as fast as the internet and as fast as the validators can process them. More CPU cores means more parallelism, which means more transaction capacity in a single node. Faster network bandwidth means blocks get to more nodes faster, and you get lower confirmation times across the network. Today, without more cores or without faster network bandwidth, Solana is processing about 2,000 transactions per second, steady state, right now. Fees for those 2,000 transactions per second are about 1/4 of a penny on average. Go to solanacompass.com and see for yourself, if you don't believe me. The stats are live. You can take a look. Block times are 400 milliseconds. You have 400 milliseconds to build a block, send it out to every node on Earth. Another block or two, you've got your confirmation. Fast, dirt cheap. Is it scale? More CPU cores, Moore's law still holds. Solana will continue to scale. This is, if you can't read it, this is a vertical log scale of transistors on a chip from 1970 to 2020. As long as AMD and NVIDIA and Intel continue to exist and continue to compete with one another, every year we will have faster processors, we will have more cores, whether it's smaller transistors or you do your 3D silicon wafer technology, whatever it is, we are going to continue to have faster chips to enable more parallelism for Solana to continue to scale. What about the network? Solana block times are 400 milliseconds today. How fast can it actually go? We are running up against physics here. The lower bound on how fast Solana can go is how fast can data get all the way around the planet. The Earth is about 40,000 kilometers in circumference, speed of light, 200 million meters per second through fiber, which is slower than through vacuum. You do that math, it takes 200 milliseconds at the lower bound for data to go all the way around the planet. This means that, in theory, the lowest possible block time we can have for Solana is 100 milliseconds, as data only needs to get halfway around the planet because it goes both directions. And assuming perfect routing, which doesn't exist, you'd hit every node on Earth as you go both ways around and update all of their state. So on a reality check here, and if you're a map nerd like I am, this is the internet that we're dealing with. This is a map of the undersea fiber optic cables that connect the internet from continent to continent. Latency in this system, imperfect routing in this system, and political and infrastructure investments are the sort of boundary function of how fast we can actually get data through the internet from New York to Singapore to London to Dubai and back. Today, it takes about 120 milliseconds to get data from New York to Singapore. That's about halfway around the planet. So in synchronizing global state on the blockchain, block times should map as closely to the time it takes for data to get from one place on the internet to another place on the internet. If you are sitting in New York and you are a stock trader and news comes in from Singapore that some company just released their earnings report and you want to make a trade based on that news, how long did that take to get to you? 100 milliseconds, 200 milliseconds is how fast data travels through the internet. This is how quickly blocks should process on Solana so that whether it's an ARB opportunity or a market movement can be reflected in Solana's global state as quickly as news and data travels through the internet. Practically speaking, we're not quite there yet. This is an extremely high-performance system, and it was written by imperfect humans, and as a result, we have imperfect software. The protocol limits, as I described, are what they are, and the reality is the network is only going to be as fast as the validator software that runs it. The main validator on Solana today was created by the team at Solana Labs, and people write bugs. It happens. When we launched the Solana network using this same production code, there were no smart contracts. There was no support for tokens. There was no inflationary mechanism or staking rewards on the network. You could send SOL back and forth, and you could vote on blocks, and that was about it. So every other feature and major protocol improvement that has happened on Solana network in the last 4 years has happened on production code that you got to be really careful not to break. And as a result, some things have been bolted on in ways that if you had a fresh start and you could say, well, I learned all of our lessons from Solana for 4 years of operation, let's build it from scratch. Unfortunately, the main validator team does not have that luxury. They are touching production code. So as a result, we have a few issues. These are just practical software implementation challenges that the validator teams are working on today, and just wanted to share a few, lest I get ahead of myself with speed of light. So we use Quick as the network forwarding, transaction forwarding protocol. Quick comes in over multiple ports and is subject to network jitter. This gives some non-determinism in the order in which transactions arrive at the leader, which leads to some non-determinism in when, why, and how is my transaction actually included or not. This is a little bit different than chains where you have a mempool, and there's a little bit more clarity, at least from kind of the MEV side and the block builder side, as to what transactions are available, which ones do I want to include, for what reason. And I can choose to include them, and if not, the transaction just sits there and waits for someone else to, tell it that it loves it and picks it up and puts it in a block. Second challenge, the block scheduler, we can do a lot of transactions in parallel, and we can do a lot more parallelism than we are currently doing today. This is a software challenge, it's an implementation challenge. We are streaming transactions in from a multi-gigabit fiber line as fast as possible and trying to assess them for maximum parallelism at the same time that the block scheduler assesses them for maximum revenue for the validator. This is an incredibly difficult challenge. So what has resulted is sometimes we're seeing blocks that are packed without optimal parallelism. Some transactions are run in sequence that could have been parallelized, and they kind of get missed by the scheduler. The result is that blocks are more full than they otherwise need to be, right? So it sort of reduces the practical capacity of blocks. There's some really nice scheduler updates coming in the 1.18 release, scheduled for a couple months from now. There's also at least two other scheduler implementations out there. This is not a protocol thing. A leader can choose to schedule transactions however they want. Lastly, local fee markets are great for pricing state contention and are a little bit slow to respond. The result of this sometimes being that the bidder for the highest piece of state says, oh, I'll pay you $10 if you let me get in there. If they're coming in subject to quick network jitter, like I said before, they might not even get seen by the scheduler to know that they're offering the highest fee. And so the result is there is occasional sort of economic inefficiencies in making sure that the highest bidder for a piece of state actually gets included. There's a great discussion happening. There's a change proposed, SIMD 110. All the SIMDs are similar to Ethereum's EIPs, protocol change proposals. This is hosted on the Solana Foundation GitHub repo. There's a whole bunch of these that are in active debate as to how people kind of want to help push the future of the Solana protocol forward. And it's important to note that all of these challenges, I don't want to get ahead of ourselves, but these are all implementation challenges. These are not limitations of the fundamental protocol. They're not limitations on what can really be done if you accelerate things to the speed of light and if you optimize the path that data flows through the nodes and through the network. One thing I'm really excited about that is pushing the boundaries in the implementation is FireDancer. FireDancer is a brand new validator for Solana. It's being led by a team at Jump Trading, and they are rewriting from scratch in high-performance C code the entire Solana validator codebase. This would make Solana the only chain outside of Ethereum that has multiple, fully independent multiple validators running the chain. This is an incredible step forward for the network as it relates to safety. You have multiple implementations of the runtime, and therefore the chance of a bug in one runtime being present in a bug in another that's written in a different language with a different compiler is practically zero. These are, I think, some of the smartest engineers in all of crypto, and they are heads down full-time optimizing every piece of the Solana validator that they can find. And they get the benefit of learning from the mistakes and the challenges and the technical debt that have accumulated in the last 4 years of everything that we've built. And they say, hey, without changing the protocol, without changing the hardware, here's how we would write this. Go. And this is what they're doing. FireDancer is live on testnet, an early version, right now. They're also pushing a lot of their improvements back into the original Rust validator from the Solana Labs team, so hopefully reach some kind of performance or feature parity. When I say they're pushing the boundaries, FireDancer has demonstrated 10x to 100x performance gain in some areas of the validator stack. Let me say that again. FireDancer has demonstrated 10x to 100x performance gain in some areas of the validator stack on Solana. You think Solana is fast today? I don't think anyone is bullish enough on this team. their early demo, this was last year, and this is the code that's running on testnet today. In the networking stack, now mind you, this was not a full end-to-end validator. This was just one component. They were demonstrating 1 million transactions per second on one core, processing 5 gigabits of incoming traffic. This scales up. They went up to 4 cores, processing 4 million transactions per second. The only reason the machine couldn't handle more transaction data was because they maxed out the network card. They couldn't push more data than 25 gigs because they just didn't have the networking hardware. This is super exciting. They are pushing similar levels of aggressive performance in the runtime, in the consensus algorithm, and it's just super exciting. Look forward for more updates from the FireDancer team later this year. And so just to conclude here, Solana mainnet today consists of over 3,000 nodes in 40 countries. Parallel processing and continuous data propagation enable Solana's high throughput and low latency. The protocol is designed to scale with hardware, cores, and bandwidth to synchronize global state at the speed of light. You do not need to break the chain up in order to get your speed, your composability. You can use local fee markets to separate economic activity without building your own infrastructure, so people can just focus on building their applications and products. Challenges certainly exist. Most of them are simply lack of optimizations in the software, which are all solvable and in the works. And I am super excited for FireDancer pushing the validator and the network to new heights. So, thank you very much.
Awesome, Dan, thank you. I think I remember you saying earlier when we met that the speed of light just isn't fast enough, so. Next, we've got Ben Fielding from Jensen, we've got Greg Asuri from Akash, and we've got Guy Wallet from Andreessen who are going to talk to us about AI and decentralized compute and blockchain.
Is anyone sat here? Oh, no, here. We've got special stuff. You can use that one, actually. I'll just take this one. Hopefully they don't mind. Thank you. Just great selection.
Great, good. Okay, I think I'll set off to this side. Fern.
Between two ferns?
Right, you and I are going to share a mic. Yeah.
We are between two ferns.
Two ferns sharing a mic. All right. Hello, everyone. Check, check. We're gonna let Greg take a photo. Cool. All right. This is the DPIN or decentralizing and accelerating AI panel via decentralized compute. You've got an awesome group here who I'm gonna let introduce themselves, but I want to set a teeny bit of context about what we're gonna talk about. Recent advents in AI have created a huge demand shock for decentralized compute, or just generally compute, actually, and GPU. And so that supply-demand imbalance is being addressed by decentralized compute. But in addition, there are some like emergent properties in AI that can be. So we've got an awesome panel here to talk about it. We're going to go through intros really quickly. So Greg, you're nearest to me. I'll let you start.
My name is Greg. I am the CEO founder for Overclock Labs and a core contributor to Akash Network. Akash is the world's first open supercloud. A supercloud is essentially a cloud that sits on top of private, public, hybrid, whatever clouds you want, and gives you a federated interface to access these resources in a permissionless and a decentralized manner. And a key property is an open marketplace that allows you to trade resources. This is especially great when you have to trade GPU cycles. Turns out there's a lot of, while the demand for GPUs is super high, there's a lot of other GPU, there are a lot of underutilized GPUs. Or companies upgrading their fleets from older chips to newer chips. There's a lot of GPUs out there, so a network like Akash is bringing that to the light, and we are growing very, very fast in terms of usage.
I'm Ben, the co-founder of Jensen. Jensen is a decentralized machine learning compute protocol. We essentially connect up all of the machine learning capable compute hardware in the world, so GPUs, but also TPUs, CPUs, anything that's capable of doing machine learning training tasks, and allow that to be used as a resource by anyone who needs to train a machine learning model. And we view Jensen as essentially fundamental infrastructure for the new machine intelligence web, essentially. So a protocol in the sense of TCP/IP or something like that. It sits underneath everything that we currently interact with, connects up all of the devices that are capable of doing ML training, and just allows that to smooth the usage of the compute devices that we have in the world. The future that we see for machine learning is complete ubiquity. It's going to be on every single device. Every piece of tech that we interact with as consumers won't be imperative code anymore. It'll be models, and those models need access to core resources. The one that we care the most about is compute, and so we're building the protocol to allow that to be instantaneous. So at any point in time, if a machine learning model needs to distill value in data into parameters, it can do that on literally any device, and it can burst out to happen on multiple devices when it needs to. So instead of training on a single GPU, you'll be training on maybe 1 million MacBooks or 1 billion iPhones or something like that. You as the developer or the user won't care or know that that's happening. It'll just happen as a protocol underneath everything.
Hey everyone, I'm Guy Willett. I'm an investor at A16Z Crypto. We were very fortunate to lead Ben and Jensen's last round. I tend to focus on the crypto side, but we also have a team that is very focused on the AI applications as well, and we invest at every layer of the stack, be that infrastructure or applications within crypto.
Awesome, thanks everyone. So yeah, let's dive into it. The first question, Guy, as the resident VC on the panel, could you help set a bit more context, right? There's a long history of decentralized compute in crypto, or at least as long as there's a history of crypto. Could you maybe walk us to where we are? And then the follow-up question will be tease out like where we need to build more because prior decentralized compute doesn't address the needs of AI.
Sure, yeah, so I'll give the mental models and do the thought leadership, for lack of a better word. So I think a lot of this is really based on the pioneering work that Ethereum did to try to build a decentralized world computer. And in my opinion, a lot of the work that folks like Greg and Ben are doing now is trying to scale that decentralized compute to applications that are essential to inference, to training, to kind of every layer of the stack that's currently being defined in ML. And there were a bunch of different approaches and kind of prior generations around smart contract platforms where you would either explicitly form consensus through a BFT or a Nakamoto approach, and there are a bunch of folks that are focused on ZK proving for computational validity. A lot of those approaches don't scale, and they certainly do not serve the use cases that people are really interested in today for trying to inference a GPT-4 style model or train one in a permissionless way. And so I think a lot of the work that's happening now is essentially trying to address the very pressing question of how do we decentralize AI rapidly without relying on the techniques that are a little bit less scalable and have historically worked better for smart contract platforms.
And maybe this could go to Ben or Guy, whichever. Scratch one layer deeper, like architecturally, what are the needs of an LLM model that are different than like a DApp or a blockchain? Or Greg, you look like you're ready.
I mean, so there are different aspects of LLM, right? Be it training or be it inference or fine-tuning. So fundamentally, it comes down to the right amount of GPUs with least amount of friction to the user's GPUs and overhead to using the GPUs, right? So if you go with the traditional verifiability in all aspects, it adds a layer of like complexity that affects the performance, right? And along with just chips, you need the supporting infrastructure, be it storage, be it bandwidth, be it a professional grade data center that can offer, right? A machine sitting in a home may not be able to serve a production workload unless, maybe intelligently designed with asynchronous model, but definitely for an inference type of scenario, you need that low latency access to the user, and that can only be delivered by a professionally managed data center. So that tends to be a big barrier. And one of the things Akash does is hyper granularity in terms of scheduling your workloads. So in the sense where in a smart contract machine, the system does the scheduling for you, and the user has very little say, of almost no say on where your application is running. So it's a different way, it's a different pattern of deploying, great for like deterministic approach of applications, but for when you have non-determinism and you have low latency requirements, your provider has to have that sort of like capabilities, and the system should have the granularity or to select the provider. And that's, I think, the big difference between something like Akash or a fully deterministic on-chain execution layer.
Awesome. Ben, anything to add?
Yeah, I think I'd probably just say that the different use cases within ML have different requirements. So like inference has a completely different set of requirements to training. And I think that's where something like Akash, like you can do loads of different tasks over that network, and you can do inference, you can do training, you can do things like this. But ultimately, underneath each of those tasks, there are fundamental bottlenecks that if you solve them in a thin way, you can potentially accelerate those things even more. So we focus purely on training and solving the verification problem, which in our opinion unlocks massive scale for compute. But there's plenty of other things around compute required for training models. There's like data, there's latency, as Greg mentioned, there's general usage. Like that's a kind of problem that if you are deploying machine learning models at scale, you're gonna need usage. And I think the ML world's gone through various phases of focusing on one of these specific things and thinking that's the value unlock. And we've moved through various of these with like data being the new oil for a while, and then kind of like PhD students who can build models being the kind of value, then to compute itself, if you can hoard it, that's the value. I think realistically, each of those things is required, and as a kind of community, we've gradually moved each of them up. I think the future is creating a modular system where we solve each of those problems as a separate network, and then we sit them all together. And then out of that, we get the real unlock for the future of ML, rather than kind of like iteratively reaching each one up a little bit at each time.
Okay, awesome. And so what I'm hearing, and I guess like one of the overall questions I have in the first section is, like right now, because there is a supply-demand imbalance, like anyone who can get their hands on GPUs to do work is going to shop for it and going to go where they can even get it, let alone at a better price, right? But we're going to reach a point where there's a certain scale in the market of available GPUs. Like how do we, and can we, or is that even the goal, get to a point where decentralized networks can compete with centralized, like hosted data centers like those at AWS or Google Cloud?
Yeah, I think from my perspective, decentralization improves that market. So in the long term, it makes it the most efficient way of accessing compute and the cheapest cost way for the demand side, the highest yield way for the actual owners of the devices themselves. Currently, the market's captured by middlemen. So there's particular reasons within the market why you can extract rent from a different portion of the stack. And I think what decentralization does is just eliminate those portions. It stops there being a way to extract rent from halfway up the pyramid and just allows value to flow all the way down to the end. So ultimately, it becomes the lowest price, highest scale, highest access way of distributing things like compute, but also things like data. Like all of the core resources required for ML can have this new business model essentially floated on top of them, and they can generally just open up access to that. And I think we're all aware of like the social reasons why we think we should open access to ML. Like we've seen Gemini, etc. Like the world has come to it from a social angle, and now we need to come to it from a technical angle and actually build the new incentive structures for it.
Right, so the spice must flow, right? So we're going to fix the supply chain problem at some point. And there's lots of investment going into fixing the supply chain problem, all the way from building foundries, all the way from attracting new talent, and a lot of good things. But what interestingly is we have an opportunity right now, right? The question is, well, once the supply chain is fixed, you get the economies of scale that large, hyperscalers have that, may overpower the network, right? So I think we have maybe about 2 years to really decentralize, because we have one thing the hyperscalers don't. Like Akash is the only place to get on-demand H100s right now, and there's no way you can get that H100, and that's going to be not forever, right? So I'm building a data center in my house in Texas, and with a come and take it flag in front of it, and that's going to be about 40 kilowatt solar powered. It's going to pay for the house. So I think, we have an opportunity now, and people are going to use my GPUs that are in my house because you have no other option, really. So we have a great opportunity, and we have one thing crypto is phenomenal for is incentives and gamification of usage. So how do we leverage that opportunity and how do we get maximum impact in terms of attracting the most distributed supply. And there are a lot of research. I mean, there's a recent paper by Google DeepMind, Doloco, right? It's a very incredible paper that talks about a big challenge with training is latency, and there's a lot of really good people working on solving the latency problem using different mechanics, and Ben is a lot more has a lot more expertise than me when it comes to like reducing that stuff, but it's a lot of promising work. So hyperscalers are not going to be the only ones with that massive advantage, and we have a good opportunity here.
Yeah, I think there's a particularly unique opportunity here because crypto projects often have a much harder UX, and it's more difficult to convince people in the traditional world to onboard. And because there's such constrained supply today, people are willing to make a greater leap, or to, as you were saying, Greg, use GPUs in your garage, where maybe 10 years ago, folks at a Fortune 500 company would have been a little bit more skeptical about that idea. And so I think this is kind of a unique opportunity to have the world by default run on a decentralized network as opposed to by default on a centralized network. And a theme that I think comes up time after time in crypto is that we are all, in some sense, betting on the creativity and the ingenuity of everyone around the world, and saying that we want not just a small number of companies and a small number of very smart but credentialed people to propose how society is run, or the systems that coordinate our lives. We want anyone to have the opportunity to do that. And my hope is that things like Akash and Jensen and other projects building in this space will make that the default, as opposed to something that we need to upgrade to in the future.
Yeah, that's an interesting point, and another topic I wanted to dig down on, especially for the founders, right? How do you think about permissionlessness in this category? It's an ethos of Ethereum for sure, and as a censorship resistance. But in this category, it certainly comes with challenges, not the least of which, though I don't totally understand the nuances, is export controls around certain devices like H100. So how do you think about a permissionless network versus not? And if you don't want to talk on this topic, that's fine. But how do you think the world should think about building like permissionless compute networks? And then one follow-up question on that one once we get going.
I can take this. I mean, permissionless is the foundation for composability. I mean, removing barriers of usage improves adoption to a point at a rate that closed systems cannot, right? So permissionless is foundation for Akash. Censorship resistance is foundation for Akash network. That's never going to change. But the challenge remains abuse. Abuse tend to be a problem. I mean, one thing is about policy restrictions, but another thing is about using AI for really bad things, right? Like, so how do you prevent that? Well, it really comes down to liberty, right? As much as users need no permission to use Akash, the providers also have full control and sovereignty as to who they should allow to use the network, right? If the provider doesn't want to serve a user, they can very well shut down the user. They can just stop, not shut down the user, but can stop serving the workload. And the user, as long as there's another provider that's willing to serve their workload, they should be, able to. So if there's something really bad like child pornography or something, nobody wants to host, nobody's going to host. But if there's something that falls on a different side of the political spectrum that half the country may not agree, but half of them do, yes, that'll be served, right? That's how we look at censorship resistance and moderation, right? It's self-moderation. Moderation is done by the providers and not by the protocol. And the protocol should remain free and free of moderation, free of censorship, and permissionless. That's the only way to go far. And like permission models and closed models can go fast in the near term, but open and permissionless models can go far in places where traditional software cannot. Like one of the examples I give is Akash is being used by DoD, Department of Defense, because of its open source nature and a permissionless nature. Of course, a fork of it, not the actual network, because DoD cannot use external servers, but they're using internally to consolidate their supply, and they're running their own fork. But that just tells you, and we have zero salespeople focusing on even corporate America, let alone defense, right? But that's the kind of organic adoption you get when you have really open source software, and that's the kind of stuff that is critical for massive adoption.
Yeah, I'd probably just say we have basically the same view as Greg has just described. I think foundational technology should be neutral. Like if you create the checks and balances within the foundational technology to allow somebody to disallow something, you just create an ability to control that technology, and that will be abused at some point. So you'll create the ability for power to accrue within the technology itself. We think that at the lowest level, when you're building these primitives, you need to build them to be entirely neutral. And society is going through some really interesting governance alignment questions right now around AI. We're going to have some difficult questions to answer about how we collectively govern the things that people can do with this technology that enables massive leaps forward in various things. Those can be leaps forward in bad things and good things. And obviously society has an Overton window that moves around. I think at different points we'll need to do different governance actions, but they should all be done through social governance mechanisms and through arguably the mechanisms we already have to govern applications themselves. But the technologies underneath just need to be completely neutral. They should be usable by anyone at any time. And then when somebody uses those things to do some bad in the world, we go straight to the application itself. So if somebody builds an application to do something that we all agree is actually shouldn't happen, it's the application that's at fault. It's not the technology underneath. We've been through this battle before with encryption. We all probably agree that encryption shouldn't have backdoors in it just because there's bad things you can do with it. It's the same for ML. It's the same for compute. It's the same for data networks. These things shouldn't be backdoored because those will be exploited by people to accrue power. And then we've lost the real value we can have from decentralized technologies, which is to just level the playing field completely and level up society as a whole rather than a small portion of it. It's why the Gemini stuff, I think, has resonated so strongly with people, because you see the bias of a certain group being shown to everybody very, very clearly. And we have very few choices around models that we can use right now. So people are forced to use these models with biases that they don't agree with. Realistically, every ML model is biased. Like every technology we build is biased. Like they're all biased machines. We're biased machines. But what we need to do is build technology that allows all of those biases to come to the front, and then people can choose which biases they use. So it requires neutrality at the absolute bottom layer.
Okay, you answered. Oh, sorry, go for it, guy.
I think Ben said it very well. Go ahead, Stephen.
Yeah, I had a follow-up question, but you also answered that. It's like, where does the red button go? Like AGI takes off, we need a red button. GPUs seem like the right place for the red button. Maybe we don't need a red button. I assume you disagree with the premise.
Well, so Akash in Sanskrit means the sky, right? It's where the clouds are formed. Akash net, if you translate that to Skynet, that was not by design. It was pure coincidence, right? Like those of you old enough to remember what Skynet is, it's essentially the AI that kills us all. So I'll be more concerned about self-replicating machines more than government and policy shutting us down. And incentives are one of those things that if you perfect them to a point where machines themselves can create incentives to further attract more supply, what's going to stop, right? Like what's going to stop like an AI to trade Akash token and maximize its gains and use that to purchase compute. You can do all kinds of things, right? So the way I think of it is, I think proof of personhood could be a potential solution in the future, and because Akash is a proof of stake network, it's managed by human beings, at least as far as I know, and humans have a vote in the system, although there's no way to know if it's a human behind the vote or not. And ultimately, the stakeholders of the network will eventually determine what kind of access and who to allow access to. But that's the beauty of open systems. Let people decide. And we don't know what the solution is going to be, but I believe in humanity.
I think that's the big point, right? You believe in humanity and you believe in these structures that you've built that have agency right at the lowest level. So like you said, Greg, like if a compute supplier, if somebody's putting GPUs online and they see something that they don't want to do, there's a computational task that comes to them and they say, I don't want to do that. They don't need to do that. And that's how society can control these things in the future. It doesn't need a big red button in the middle. It needs people to do in the moment what they think is the right thing to do. And actually that's a better reflection of the whole of society than having a small group with a red button that decides on behalf of society. And it doesn't require us to have this kind of like governance, kind of democratic voting system, because it's actually just the users of the network are the suppliers of the network, and they vote by just withdrawing their supply or not doing the task that they would otherwise be incentivized to do. So I think it's a much truer reflection of our collective thoughts as a society to just give people the control rather than saying they have kind of proxy control via voting for a small group who will then slam this red button when either something bad happens or something that group disagrees with happens.
Yeah, so I'll speak for myself personally here, but I think the big red button question is often like, what if things move too quickly? And I think the inverse of that question is also worth asking of what if we don't move quickly enough? The world has a lot of challenges, and I think drastically increasing the amount of intelligence that can be applied to those challenges, I believe would be a very strong net positive. And so usually people, we'll have the slow takeoff, fast takeoff debate, which is probably out of scope here, but I am very much on the side of, what if we don't move forward and continue to build great new things that create a better world for humanity? And that's the question I would hope that most people come away asking instead of, being a little bit more fearful.
Awesome. Good answer to a silly question, all of you. Okay, so we're getting here on time. I sent you all a lot of questions, and this was the last one. You're all very busy, so I'm not sure if you read to this point in the prep questions. But we'll start with Guy. What was your favorite GPU, and why?
I did not read to this question. I actually don't even know what it would be called, but I had like a first-gen MacBook Pro that I used to play Rome Total War on, and whatever that GPU would have been was my favorite.
Sweet.
Probably a similar answer. I don't even know what it was anymore. I can't remember. It wasn't even PCI. It was some other slot that doesn't exist anymore. Some ancient thing that I think somebody found in a second-hand shop to put in the PC because I thought it would allow me to play games. I don't think it actually even did. But to me, it represented that access to the gaming world as I don't even know how old I was, very young child. So similar answer.
4090, hands down.
4090. Oh, you're a modern guy.
It's
modern.
It's versatile. It's beautiful. It works really well. You can play games on it, and you can train AI or not train, at least infer. It works really well. If you know how to optimize your pipeline, you can do a lot of damage in 4090. Surprisingly, 4090 has been like popping up like a lot now. People want more 4090s than A100s because a lot of the papers are mentioning 4090s. I think 4090s is going to be one of those what do you call, under the radar that's going to pop up and become the most important GPUs. I have a bunch of 4090s at home that are making about $250 a month.
Chilling the bags there.
I'm chilling my own bags,
Awesome.
4090 NFT drop now.
Well, thanks, guys. Mine, I cheated. I looked up. Half-Life came out, and I bought a Radeon 9700, and it made Half-Life absolutely dope. But I cheated and looked it up. Awesome. Well, I really appreciate the discussion. This is great. Everyone, thanks to our panel, and we will see you at the next one.
Wonderful.
Thank you. Thanks.
All right, guys, if you want to stay, we've got exhibits that's also in a similar space of decentralized AI compute. And Juan Lee, they're one of our Stanford teams, and we're excited about how they're also kind of optimizing and accelerating compute in the space. I think he's setting it up. Just bear with us. Take a moment to breathe. I'm going to turn the air on. All right, here we go. Thank you, guys. Thanks, Wanzu.
All right, thank you, Gil. I know it's been a long day, so I'll do my best to keep you entertained and grab your attention. So, as we all know, the demand for compute has just exploded in the past couple of years. And with the complexity of AI models expected to double every 3 months, this exponential growth in demand is showing no signs of abatement. And I'm sure you've all seen in the news that Sam Altman is raising some $5 to $7 trillion to reshape the chip manufacturing industry to mitigate this shortage problem. And if you've been following markets, NVIDIA, of course, has been the most visible beneficiary of this new reality, and their market capitalization reached over $2 trillion. Now, with all of that said, if we take a step back and consider all the different GPUs that are currently in possession, the story becomes a bit nuanced. So there are 2,200 independent data centers in the US, and the utilization rate of GPUs is actually less than 20%. And then there are 30 million GPUs in mining rigs with less than 40% utilization. And then when you get to the mass market with 250 million chips, less than 12% are being used. And we note that among the underutilized GPUs, for every data center grade chip, there are 99 consumer grade chips. And then within that small slither, that slice of data center grade chips, only 1% are of the highest quality commercial grade H100s. And many of you know that for AI training that's driving much of this demand for compute has a strict preference for H100s. And there's a very good reason for this. The consumer grade chips, they only offer weak computing power. They have slow communication, and they're plagued with high failure rates. So they fail to pass the minimum requirements set by the enterprise users looking for practical applications, speed, and high reliability. So at Exhibits, we're trying to tackle this problem and propose a solution. And we do this by first aggregating idle GPUs from multiple sources into a single platform. Second, by accelerating weak GPUs for AI workloads and hoping to convert consumer-grade chips into valuable assets in the compute ecosystem. And third, by stabilizing GPU clusters to provide constantly reliable service for enterprise-level use cases and for millions of users. Now, of the 3 missions, we've spent the bulk of our research and development, investments, and intellectual capital in developing the acceleration and stabilization. And this, we're trying to build as our core value proposition and to really set ourselves apart from the competition. So our technology architecture consists of 3 major parts. The first is the automated LLM configuration that optimally matches GPUs to LLM inference services. And second part is GPU acceleration using adaptive sparsity predictor, GPU-CPU hybrid execution, and impact-based neuron placement. And I'll go over this more in detail in the following slide. And the third part is elastic resource scheduling that aims to minimize compute capacity slack in the system. So an important observation of large language models is that the 95% of trained neurons are often inactive for inference. So there's research currently underway where scientists are developing simplified models with a fraction of the parameters to approximate the capabilities of large language models. And for us, we use an offline split to initially separate and select the active neurons in a static environment, and we fine-tune the subset using an online predictor based on user-provided information. And so here we have a transformer model, and zooming in on the two fully connected layers, you can see the weight matrices with the highlighted rows and columns corresponding to the active neurons. And then after two linear transformations, neurons 9, 7, and 5 are stored in the GPU memory and the rest into CPU. So this hybridized execution allows us to dramatically reduce the compute load placed on GPUs. Then to illustrate how we manage compute resource, here we have a distribution of 4 user-prompted tasks over 5 different compute nodes in time. And here's the picture on the left is following parallel computation. So each row represents a compute node, and the columns are discrete time steps. Now, when these user tasks have low correlations in time, the general shape of this distribution tends to be quite stable. And that allows us to impose a prediction model with the aim of redistributing the compute kernels to minimize the area of bubbles. So bubble is this white zone where they represent unutilized compute capacity. Okay. So you see task 1, it takes 19 time steps to complete under parallel computation, and that we reduce it down to 16 steps. So there are 3 modules that accelerate and stabilize our compute system. First is the configuration recommendation module that defines the policy function that maps each LLM inference service to a GPU. The second module is the performance detection module, and that ensures stability, minimum service quality, and controls the scaling of up and down of resources assigned to a particular task in the system. And the third module is the deployment execution module, and that dynamically makes adjustments to the policy function in response to the changing conditions in the performance metrics so that the entire system is optimized in every step in time. And the common denominator across the three modules is that we're able to impose a prediction model that forecasts how the different variables in the system are distributed over time so that we can perform constrained optimizations continuously to maximize the efficiency of compute utilization. So what does all of this mean empirically in real life? And how do they show up? So we took an NVIDIA RTX 4090 chip. So someone in the panel mentioned that just before me. And we compared it against an A100 in relative performance. So we measure performance along average tokens processed per second. And we see that a normal 4090 that's unaccelerated performs at 6%. So what does that mean in economic terms? It means that even with a fraction of the price of a $20,000 A100 chip, on a performance-adjusted basis, this chip is actually 67% more expensive. Now, why is that? Well, because you're paying $2,000 to get $1,200 worth of compute. Okay. Now, when we run it through our acceleration algorithm, we see a drastic jump in performance up to 72%, and that translates now to having the 4090 chips being 86% cheaper in today's prices. And so that effectively flips the value proposition, and now the consumer-grade chips are economically viable. Now, so what does that mean in AI model testing? Well, now we can train models with twice as many parameters, and for inference, go up to 175 billion, which is notable because that's the number of parameters of a ChatGPT 3.0. And in terms of stability, we achieve a very impressive 99.986% uptime, which is comparable or exceeds that of a tier 3 data center. here's a short case study. So Nebula Block is one of our current customers. And they're an AI and cloud computing systems integration company. And Nebula was spending close to $191,000 a month with AWS. And when they onboarded with us, we were able to cut down their cost by 70% while shortening their time or increasing their performance by 30%. So this picture in the bottom right you see is their monthly spend with us since they onboarded in October last year. And what you see immediately is this consistent increase in spending month after month, which we see as a validation of the high quality product and service that we deliver to all our clients. Here is a snapshot of the console that's available to our users, so those who demand and need access to compute. Can we play the clip? Following Gemini's demo, we decided to just record what you can see on a clip. But I promise it's working and you can access it. And when you're on board with us, this is what you will see. I think that's it. Yep. Can we stop and go back to the slides? Okay. So a short clip of our console in action. And then so we have a screenshot of the client environment in operation. We call Deep Scope Automated Management Platform. And our customers are able to perform automated LLM configuration and deployment. So the modules that I spoke of, they're able to access and control that. Network and InfiniBand management for communication and latency management, performance observation and optimization, and the elastic computing and failure recovery. This is a picture of our community DevNet, which was launched earlier this year. So this would be the console and interface available on the supply side for those of you, including retail users with GPUs, that you like to contribute toward our network. And everyone here is welcome to join, apply to be whitelisted, and you can become a part. And why don't we also just briefly play a clip of that, if possible. Okay, I think that's good. Yep. Sorry, the switching back and forth between video clips and PDFs wasn't what the host had prepared for. So right now, we have over 65 chips in our network that includes H100s and consumer-grade chips like 4090. And they're distributed all over North America and Europe. And it's typically quite difficult for anyone to really secure supplies of this magnitude. But our executives have been part of major Bitcoin mining operations like Bitmain. And they have had secured really valuable relationships over time. And with our expertise, we're fortunate to forge these strategic partnerships. Our team, the CEO is Zach, who has a PhD in computer science from Princeton, and he has over 10 years experience working in cloud computing and blockchain. And we were fortunate to be incubated at Harvard and now part of Stanford, also Berkeley's acceleration program, and had a chance to work with these famed institutional brands. So please follow us along our journey and keep updated on our progress at exhibits.ai. Thank you.
Thanks so much, Juan. And yeah, I mean, we're incredibly excited. Like, if you can accelerate and optimize consumer chips, then that means like true decentralization for AI compute is possible. Because right now, there just aren't that many commercial and enterprise chips available. Next, excited to announce and present Eli Ben Sasson of Starkware. They've obviously had a lot going on, and he's going to share a bit with you in the coming minutes.
Hello everyone. So the topic of my talk is going to be how Starknet is going to reach 10,000 TPS. But also, I would like to address why would we want to reach 10,000 TPS in terms of demand and what will happen when we have that capacity, and also along the way. So first I want to discuss the how, and then we'll discuss the why. So a brief history of proving zero-knowledge technology started in 1985, and major points in the adoption of zero-knowledge technology have been Zcash. I was fortunate to be a co-founder of that. Today, most of the scaling going on layer 2s is done through Starks, which I co-invented in 2018, and Starkware has been the first to productize through StarkX in 2020, and recently Starknet. And by now, Starks are pretty widely adopted. Now, already in terms of capacity and demand, over the years that we've been scaling Ethereum using our first generation prover, which is called Stone, we've already seen pretty high peaks. For instance, we had the peak in user operation steps has reached 187. And the thing about Starknet is that you can pack into one transaction many different user operations. So we already saw pretty high demand and, of course, capacity. And over the years with StarkX, we've saved over $1 billion in gas fees. By now, with the prices of Ethereum, it's more than $1.5 billion in gas fees and rising. So there's already pretty impressive scaling. Another thing you should know about Starknet, it is, and this is the thing that causes me the most pride, is that it has the developer ecosystem that is fastest and most growing, and also the largest among all L2s. So if you're not yet part of Starknet, you should consider joining. Now, let's go back to the question at hand, which is we want to scale StarkNet to reach 10,000 TPS. And when I say TPS, I'm going to talk about standard ERC20 transfers. And I want to, we're not there yet. So I want to discuss what are the bottlenecks and what are not the bottlenecks. Now, surprisingly, the proving is not the bottleneck. What do I mean by that? A few months ago, we did some stress testing on our proving stack just to get ready for things like provisions, which happened last week and was the largest event of its kind, the largest airdrop of its kind, 1.3 million addresses, which went seamlessly with no glitches, and the whole system worked very well. So as we were testing the system towards it, we beefed it up to 1,000 to 2,000 TPS for several hours in terms of proving capacity, and the system can withstand that. Now, that's Stone. That's the current generation prover that has been in operation for roughly 4 years. So it's like the Boeing 747 that you use to haul a lot of weight and is battle tested. Stu, that we just announced yesterday, open sourced, and I'll share some details about that, it's probably going to be something like 100 times faster. So in terms of reaching ability to prove and process 10,000 TPS, we're very close to it. So this is not the bottleneck. Where is the bottleneck? And so again, I want to impress this on you. Proving is not the bottleneck. The bottleneck is elsewhere. It's in more conventional stuff. Where is it? So today we can operate at a range of between 90 and 200 TPS, depending for transfers, depending on how exactly the transfers are written in code. And probably by the end of the year, with the performance improvements that we're working on, we're going to reach something like between 200 and 500 on this side of the stack that includes the sequencer and everything that comes before the provers start working. So the bottleneck lies somewhere there before the proving commences. And I want to share with you some thoughts on how we can improve things there. Before doing so, let me mention again that a little bit, brag about the next generation proving technology that we just, so the math breakthroughs behind it were unveiled a week ago in a beautiful paper called Circle Starks, that is joint work between Polygon and Starkware. And the white paper has been out there for a full week. Yesterday, we released the open source of the first version of the prover. The notable things called Stu. If you're looking and asking yourself why this geeky name, so Stone stands for Stark 1, and it's the first prover that we've been using, and Stu stands for the second version. And of course, there's going to be Strez, Squat Row. I don't know about 5, like how we're going to 5. We'll figure that when we get there. So it's going to work over this very small field that can fit in a 32-bit register called the Mersenne 31 or M31 field. It's going to have a much more improved virtual machine. It's going to be operating with the Circle Start, that I'll say a few words about it, and it's going to have a lot of other bells and whistles, such as the GKR lookup and mixed degree trace. There's going to be a lot more information about it tomorrow, shared. Towards the end of the talk, I'll give you a link. There are going to be a few talks about it, both by our engineering team sitting there. After the talk, you can come to Shachar and Andrew and ask them all about it. And Shachar is going to give a talk tomorrow, as well as Ulrich, one of the co-authors of the Circle Stark breakthrough. So consider attending it. Now, so the Mersenne 31, M31 field is the field that is defined by the prime 2 to the 31 minus 1. So it's a Mersenne prime. And it has really great performance. It fits inside one register, every field element. It allows, these smaller field elements allow for better granularity for arithmetization, for those of you who are in the ZK research and building circuit technology. And you have pretty nice CPU and GPU operation because of the structure of the field. Come tomorrow and listen to Shachal's talk and you'll hear more about this. Where does Circle Stark come from? It turns out that to do Starks efficiently, you really want to be operating over a group, and hopefully a cyclic group that has size 2 to the k for pretty large k. Now the problem is that M31 doesn't have such a multiplicative group. So it happens. The degree to extension of it does have, but then you're going to move to 64 or 62-bit field words, and that's less efficient than 32-bit words. So to solve that, one solution could be to work over elliptic curve groups, and there's an abundance of sizes, so you can find one size that fits your needs. This was also work that was published by Starkware a couple of years ago, but that's still pretty expensive. The better and new solution in this breakthrough uses a much simpler curve, the good old circle that we all know from, I guess from kindergarten, that goes like this. So all points that are at distance or whose, the sum of squares of coordinate equals 1. So when you talk about regular Starks as the ones that are used in stone, the group that you're using is a set of numbers. You can think of them as lying on some line. Elliptic curves look a little bit like this. And here's another picture which I think you'll agree is much more pleasant. So that's the circle group. Some elements, so we are talking about modular arithmetic, so things are always taken, modulo the Mersenne prime. And so, for instance, the point 2 to the 15, 2 to the 15 happens to be a point on this circle. The magics of finite field. Back to our bottlenecks. So this was a little detour, basically praising Stu, and I hope I got some of you intrigued that you'll want to hear more from Ulrich and from Shachar tomorrow, or just read the papers. But now I want to go back to the bottlenecks and unpack why is it that even though proving capacity can probably in 2 years reach something like 100,000 or more TPS, why is it that we have, where are the bottlenecks and how can we go about trying to unclog them? So there are 5 different areas where things could get pretty crowded if you're talking about 10,000 transactions per second. The first place is the entry point, the peer-to-peer network and mempool. Then you have the full nodes that are basically tracking everything that is happening. You have data availability, what happens with all of the updates to the network coming from these 10,000 transactions per second. You have the block explorers that are supposed to save the set of transactions over time. And then you have the sequencer, who is actually flooded with this fire hose of transactions and needs to sequence them and process each one of them and update state accordingly. And remember, all of this comes before the proof. If the sequencer has ended and given output this like nice big block with 10,000 transactions or even more, 100,000 if it's a 10-second time frame, the proving technology, well, not today, but certainly in 1 to 2 years, can easily gobble that up and produce proofs that would fit comfortably into Ethereum with very low gas cost. So all of the problem lies in these things. So let's unpack each one of these and see where we might see problems. So, and I'll jump to the end and say the sequencer is really the only one where you should anticipate some serious problems that can be resolved. So if you think about the mempool and the networking, it's not that bad because if you do it's roughly 4 addresses per one transaction to describe it. The recipient, the payer, a signature, the sum being sent. And at 10,000 TPS, that's 1.3 megabyte per second. It's not such a horrendous amount of information flowing around, right? Commonly, internet links are today in the hundreds of megabytes per second. So this is not going to be the bottleneck. Okay, so that thing's clear. What about the full node? So the full node is the thing that updates states and also verifies a proof. And the main thing to know about validity rollups is that full nodes have it sweet and easy. Why? Because you don't need to go through these transactions and check that they are valid. The proof does this for you. You only need to get the state diff, update your database after you verify the proof. But the proof is extremely succinct, and very quick to verify. So the way a full node works, it receives a state update, it receives a Stark proof, it verifies the proof, and now it knows that everything is fine. So now state updates are much, much, much smaller than the number of transactions. Why? Because if you're operating at 10,000 transactions per second, I mean, let's suppose that a lot of people are buying their cups of coffee, so probably a lot of these things are going to the same addresses or coming from same addresses, and this means that the updates are going to be, these are not pairwise distinct pairs of addresses. They are pretty clogged together, and this is at least what we also see empirically in the trading systems, for instance, that we support today with StarkX. So folks like Paradex and DYDX and a bunch of the most scaled solutions today that are self-custodial are actually operating on the StarkX stack. So we see that that's not a problem. So this is not going to be an issue. Now, what about data availability? So if you go with full roll-up mode, well, this is going to be a problem. If you want everything on layer 1 of Ethereum or even inside blobs, that's probably going to be pretty blobous blob that you're going to need to use. So not sure that's what you want to do. But what you can do is you can use Volition with a lean and mean data availability solution, and you, of course, can use compression. Now, the nice thing is that, again, if you think about the data rates, they're not that big, and updating databases with the equivalent of something that is far less than, let's say 1 megabyte per second is something that is very commonly done and doable. So that's not going to be an issue either. I mean, assuming you have a data availability solution, but there's an abundance of them already existing. Okay. So what about block explorers? I mean, we're increasing with the complexity. So we said that 1.3 megabyte per second is what is communicated, but this turns out to be, if I got the math right, and I'm not very good at math, but folks help me. So it's 120 gigabytes per day, which is a lot, and that turns out to be 43 terabytes per year. Now, what do you do with this stuff? Well, if you today were to go to your bank and ask for data about transactions, probably you would get it back 6 months or a year, and beyond that you would have to wait for a few days, right, for them to take it from some disk. So something similar, I mean, 43 terabytes is a large amount, but this is for block explorers. You can accumulate this for a few years, and then of course discard or put on some bigger disks. You can put older stuff. So again, it's going to be costly, but block explorers, hopefully they'll have good business doing this, and again, they can. So the sequencer is really the toughest problem, because the sequencer, as the name implies, turns out to be sequential. So there needs to be this processor that now processes one transaction after the other for 10,000 of them, checking the signatures, going to the state and database, checking that there are enough funds, and so on and so forth. So the answer to this, and it's a magic wand that of course would need a lot of expanding, this is parallelization. But another thing that also could be done is, in terms of parallelization, you could also do things like post-processing and settlement, where you see, for instance, that you could have like many transactions that actually contradict each other, appearing where each one of them is individually valid. You now have double spends, but as long as that there's a fixed ordering on the transactions, and these are simple transfers, so you can sort things out. Okay, so now, another thing that gives us room for hope is that conventional systems, right, if you look at Visa, Alipay, WeChat Pay, these things, they today operate at TPS that is much higher than 10,000. At peak, they reach hundreds of thousands. Now, and one last thing is that this falls only on the sequencers. And in order to be a sequencer, you're already going to need to stake a lot of Stark tokens and be committed to it, so you'll probably be buying a pretty beefy machine. And again, in the context of validity rollups, because you have proofs, everyone else can verify your integrity without checking everything that you're doing, so you can actually get away with having larger operators operate in the network. Okay, so This is a tough problem, but within hopefully 2 years we can somehow solve it. So we talked about the how, but let's talk about why. Why would we want to reach 10,000 transactions per second and beyond? And we can get inspiration from the history of the internet. So until the late 1990s, there was very little usage of the internet. Why? So here's a quote from Wikipedia. I'll just read it out. The dramatic expansion of the capacity of the internet, thanks to all kinds of technology like fiber optics and other things like that, had a revolutionary impact on culture, commerce, and technology. This made possible the rise of near-instant communication by electronic mail, instant messaging, voice over IP, telephone calls, video chat, and the World Wide Web with its discussion forums, etc., etc. So what is the summary here? You had something that looked very promising, but until it had scale, you didn't actually see not even an inkling of the kind of applications that will arise. So why am I saying this? Because StarkNet, I think the same thing will happen. And maybe 10,000 separate transactions would still take us a couple of years, maybe even 3 years. But if you're looking just at sheer compute on StarkNet, you can already do some pretty marvelous stuff that's going to be utilized this year already, and by a lot of the amazing applications building on us. So remember that we can support the largest transactions in terms of user operations contained one transaction had 682 user operations, and the peak UOPS that we had was near 200, and this already happened. So you're going to see a lot of layer 3s and complex logic, and wait, I want to talk about complex logic. So you're going to see things like on-chain gaming happening with a lot more logic, utilizing already the compute that is unleashed already today on StarkNet. So what I want to say is maybe for individual transactions, high rate, we're still 2 to 3 years away. But in terms of sheer computation power for single transactions that take a lot of computation steps, this will be a thing already this year. So Influence is basically, I think, either already launched or waiting for EAP 4844 to come out there and do its thing. On-chain game, probably going to be one of the most interesting ones. Do try it out. So summing everything up, how are you going to do it? We're going to do it through engineering, which is how we did everything we did so far. The sequencer is the main bottleneck, and probably the solution is something along parallelization. And why? It's not so much about TPS, but about compute. Compute is already pretty huge today, and I encourage all of you to try and utilize it. You want to hear more? Join us tomorrow for the StarkNet meetup. I'll leave you with this. Scan the QR code and join StarkNet. Thank you very much.
Thanks again. How's everyone feeling? Bring back. Can we bring back the QR code quickly? That's how you know you're popular, when people want a QR code instead of you. Here we go. QR code is up. Going once. Going twice. Going 1/2. I'm just waiting for this guy. All right, looks like we're good. We can move on. All right. Let's see. All right, people are shuffling in and out. Good, good. Next up, we have our next speaker. This will be Ryan Kao from Modulus Labs. Modulus Labs, like many of the projects you've heard from, is a graduate, or a completer at least, of the Stanford Blockchain Accelerator, led by Stanford alumni. I'll let them tell you what they're working on, since I would butcher it. But we're all very lucky to have Ryan come present. Ryan, come on up. So good to see you. All right, break a leg.
Okay, all right, let's see. Cool, we got laser, that's pretty good. And, let's see, we're waiting for some tech stuff. Okay, well, I guess as the slides get pulled up. Hello, hi everyone. I'm Ryan, I'm the co-founder, or I'm one of the co-founders and the CTO of Modulus Labs, and we work on ZKML at scale. So get ready for some future of AI shenanigans that are about to happen. All right. slides, question mark?
I had a thing I needed to do anyway, but we have a minute. Whenever I go to crypto conferences, my wife, she thinks I'm just going on vacation, so why don't you and I take a selfie, Ryan, to show her that we're actually
sounds good
at a conference. Okay, 1, 2, everybody else smile, 2, 3. Okay, and then 1 just with me, just in case. Okay, sweet, thanks everyone.
Alrighty. Oh, I see, it's a PDF viewer, okay. Yeah, do you know if y'all can open that in a like a presentation form factor, if that makes sense? All right, sorry about the technical difficulties, everyone. Thank you for your patience. Okay, sounds good. Let me see if the clicker is working. Nice. And, oh, okay, the back button does not work. Okay, well, no worries. Okay, hello everyone. I'm Ryan. I'm, as I've said, the CTO and co-founder of Modulus Labs, and I'm here to talk to y'all about an interesting little concept that we've been thinking about called commitments with qualia. So it's a pretty cool little statement. So the TLDR is that today I'll be telling you all about, first off, the situation. So what is going on in AI land? I'm going to throw you into a real life situation, and I want you to emotionally react to this. That is the whole point. We're then going to talk about kind of the problem with AI and what is going on. We're then going to talk about how to potentially kind of fix some of this stuff. So hint, hint, the issue is going to be, of course, robustness, explainability, kind of like the classic AI challenges. And finally, we're going to talk about how we should actually get there, how far it is, and why we at Modulus specifically have hope that we can get there. Okay, all of that was very abstract, so let's get into it. So what is the situation? All right. So let's say that you are visiting the doctor's office, and this is your primary care physician. I generated this using Midjourney or something like that. But the point is that your physician comes up to you and says, hey, I have news and I have bad news. So the news is that I looked over all of your kind of medical scans and things like that. And the bad news is that you do have cancer. And so I'm going to have to diagnose you. And also I'm going to recommend that you start chemotherapy immediately so that the cancer doesn't get worse. Okay, this is a pretty kind of devastating thing to hear about. You're going to have to kind of consult with your friends and family. You're going to want to talk a lot more to your PCP about this. But let's say that it's not your human PCP who's doing this. Let's say that it's ChatGPT, or better yet, let's give them some credit. Let's say it's GPT-5 Medical who's doing this, right? So you see this interface, and you've been chatting with this chatbot, whatever it is, and it has told you that you have cancer and that you need to go do chemo. So I have a question for y'all. How many of you would actually start chemo after this?
He's on your phone.
All right, we got a couple AI believers. That's good, that's good. I'm glad.
Last I checked.
As you should. Now, if you're anything like me, you might be asking yourself, oh, that doesn't feel quite right? Like, I should probably consult with a human. And so the question that I would like to pose is, what's the difference, right? What's the difference between this ChatGPT interface thing and the human physician, even if the AI model might be doing better than physicians in so many cases? Well, here are a couple differences that I can think of. So for one, I have no idea what GPT-5 Doctor was fine-tuned on or even trained on, right? Like, I have no idea what the data set is. Also, is GPT-5 Doctor even a certified medical professional, right? Like, I know the degrees that like my doctor has, but I have no idea what GPT-5 Doctor is doing. Also, are the reasons for this diagnosis that my doctor could explain to me, like, can ChatGPT-5 or can GPT-5 Doctor explain those reasons in a way which is actually sound in terms of medical reasoning? And finally, is it even the right version of GPT-5 Doctor which is running, right? How do I know I didn't get like a bad version of GPT-2 that's just like out here posing as a doctor? So there's so many kind of trust issues with this situation. And yeah, it's all just hidden behind this nice ChatGPT interface. Okay, so what's the problem with AI? Well, as we've kind of alluded to, there are basically quite a few issues with this situation, but maybe just to take a quick detour in terms of how I like to think about AI, this has been pretty helpful, but basically, I like to think of AI as basically just creating algorithms implicitly using large amounts of data, right? So in other words, normally, if I asked you to code a Python program, for example, which takes in an image of a dog or cat and then spits out whether it's supposed to be a dog or a cat, it would actually be pretty tricky to do this, right? Like, you would need to do like edge detection. You would try and figure out like, oh, do cats have like pointed ears and do dogs have floppy ears? Like, it would actually be pretty hard for you to do this. So in AI land, what we do is we say, okay, well, we're not smart enough to figure that out. So instead, we're going to just have this algorithm, have tons and tons of examples of cat and dog images, and just throw them at this model, have this basically learning algorithm until it's just good at recognizing those things, right? And so the end state of AI, as we are starting to see, is that basically AI allows us to kind of scale the recognition and the generation abilities of humans. So in other words, think about like the human professional and like all the training that they need to go through and all the stuff that they're able to do that we want to pay them salaries for. Now suddenly you can run this, but on computers, and scale it in these huge data centers like thousands or millions of times. So there's a couple other kind of like key things about AI, which I think are pretty important. One is that AI is kind of fundamentally very valuable, right? Because it's very hard to come up with these things ourselves. The data is very valuable. Additionally, AI results are becoming more and more sensitive, right? So sure, now things are like DALL-E, it's like, oh great, I generated my DALL-E image, that's so cute, like whatever. Or like Sora, it's like, cool, I generated this like random like a 1-minute video or whatever. But the point is that when AI is being used to give folks diagnoses, to like litigate these legal cases, to consult on things that are worth millions and millions of dollars, suddenly it's not really a laughing matter, right? You want to trust the model that you're actually running. The other thing about AI, though, is that kind of these security techniques that we normally use don't really work on AI. And by security techniques, I really mean zero-knowledge proofs. We'll get to that in a little bit, but fundamentally, AI is just very computationally expensive, and that makes it very hard to basically run these quality control things on them. Cool. So the TLDR is that AI currently is what I like to call unknowable. In other words, I don't know anything about it, right? I don't know if it's biased. I don't know if it's robust to adversarial attacks. Like, I don't even know if the AI model is the right one that's running. Additionally, AI is really unaccountable. In other words, even when I get a result from an AI model, I can't attribute it back to the model, right? There's no like link between the model and the actual like result that it's producing. And so why should we live in a world like this? Like, this is not a great society. Okay, so what's missing? Well, first off, this is just kind of my list. Obviously, you can think of your own. But the point is that, first off, we're missing qualification, right? We need that degree. We're also missing kind of like the idea of explainability. Like, we want to know the logic behind these things. We're also missing kind of a guarantee of soberness, right? Like, you know that your doctor has like slept okay and that they're not drunk or high or whatever. And in this case, you want to know that no one has tampered with your AI model. And finally, you want accountability. You know who gave you the diagnosis, and you want to be able to potentially sue them for malpractice if needed. Okay, so now we're going to take all of that framing, all of that framework, we're going to put it aside real quick, and we're going to delve really quickly into the world of ZK proofs and zero-knowledge machine learning. So here we go. This is the solution. Okay, so real quick, at a very, very high level, a zero-knowledge proof is just a proof of correct computation. And so what that means is that if you and I agree on some function that I'm supposed to be running, then at the end of it, once I give you the result of this function, again, this can be a computer program, it can be a game, it can be an AI model, the point is that you can verify the proof that I'm sending you and know that I've done it correctly. So this is what we call compute integrity. Additionally, ZK proofs give us this idea of privacy in which you don't actually need to reveal some of the inputs to the computation that you're running. So in this case, if it's an AI model, you don't need to reveal the model weights. And so this happens to be very important, especially if you're trying to protect your own IP. Now, ZKML is literally just zero-knowledge proofs applied to machine learning algorithms, right? You just see machine learning algorithms as basically just a form of computation, and you just say, great, I'm just going to verify this computation using a ZK proof. The one thing that I feel like folks tend to miss with ZKML is this idea behind polynomial commitments. So real quick, the TLDR behind a polynomial commitment is that you basically have a bunch of data. And what you want to do is you want to use this, view this data basically as a polynomial, and then effectively hash the polynomial, but in a way to where you can evaluate it later at basically a single point. and there is some proof process that's necessary for this. But the point is that this commitment now allows us to basically put out there like just a pin for, sorry about the mic thing, but it basically allows us to just put out there like a pin for like every AI model and like every basically combination of model weights there is, right? So in other words, traditionally, ZKP says, I did this computation on these inputs and I got this result.
Is that a hot mic? Yeah, that's a good question. I think they turn it down, but I should probably hand it to AV.
Alrighty, got some chitter chatter going on. Anyway, sorry about that, yeah. But the TLDR is that, like, traditionally we say, look, I did this computation correctly and I got this result, right? But in the case of ZKML, I would actually challenge you to think about it a little differently. Instead of saying, I did this computation correctly, I would really challenge you to think of the model commitment as almost a model resume in some sense. In other words, we have this basically thing out there which definitively represents the model, and now every single claim, every single statement that we want to make about the model, including a statement such as, it's not robust, it's past the MCAT, all of those things can now be layered on top of this basically commitment. So for example, the name of the model, right, GPT-5 medical, but also we might want qualifications. Qualifications such as, oh, I got a 522 on the MCAT, or I got a 260 on the step 2. I had to look up the range of the step 2, so yeah, it's pretty good, I think. Additionally, you might also want to, for example, have explainability. You might want to know, like, sorry, that's the last one, yeah. But yeah, point is, additionally, you might want to have basically a history of like diagnoses, right? So other folks who have been diagnosed with this model previously can basically layer their statements now on top of the model and say, hey, look, in aggregate, of all the 1,310 ontology diagnoses that this model has made previously, it's gotten 1,260 of them correct. And so I should trust this model more because it's done so many correct diagnoses. And finally, maybe you want some explainability. So where is the source for basically the symptoms to diagnosis coming from, right? And maybe it's coming from this like nice textbook of medicine, which again, I also just Googled, so I have no idea if this is credible or not. But yeah, the point is that all of these things are what we call commitments with qualia. So in other words, you have a commitment which basically pins the model down, and then each of those statements that you just saw, those can all be formulated as statements of computation. In other words, you can basically create a ZK snark or a zero knowledge proof of all of those things and just attest it to the model. And the point behind the ZK snark and the commitment is that the only way that these snarks or these statements can be correct is if the commitment verifies them. And that is why the commitment is so fundamentally important to all of this. It is the thing that grounds all of these statements and says that all of these statements have to be done over the same model. And so we just feel like this is very, very powerful. Other statements you can prove, for example, this model is robust against adversarial attacks of X nature. So if I want like a fast sign gradient method or something like that, it's robust to that. It gets 98% on that data set. Conversely, you might want to say something negative about the model. So you might say, look, provably, this model generates a watermarked image. So clearly there's some shady shenanigans going on with the training, but the point is that when you feed it a latent seed within like some subspace, some vector subspace, it generates a watermarked image. And so this model might not be so good, could be grounds for suing, right? Okay. So the TLDR is that zero-knowledge proofs basically allow us to endow models with qualia, so all these kind of properties, and also provenance. In other words, when you get a result from this model, now you can also trace it back to the commitment to that model. Okay. So that is kind of the I guess, like the snark stuff. Okay. So how do we actually get there, and why should we have hope? Okay, here we go. So in terms of this quality control for models, actually this has already been happening a little bit in kind of the Web 2 space. In other words, there are these centralized kind of trusted authorities. So if you think about, I think last year, Scale had this like partnership with basically the government in which they said, look, we will do model labeling for you, right? Like we will attest to the fact that these models are robust, secure, whatever. But we don't actually want that. We don't want folks like Scale to just be able to kind of like label these models arbitrarily and not tell the rest of us how they're testing them. Or it's just like oh, just trust me, bro. Like I got it, right? So instead, what we really want is to do this via math, via practical ZKML, right? Like this is really the way to do this. And we want all these things to settle on chain because that is the most neutral kind of settlement layer, right? Put the commitments on chain, layer all of the qualia on top of those commitments, and everyone gets to verify every single statement. Okay, so are we there yet? Well, No, because if we were, I probably wouldn't be talking to you about this. Let's just take an example. So there's this model called GPT-2XL. It has 1.5 billion parameters. Just for fun, we at the modules team decided to basically snark this in a what we call a generic proving system, and it was atrocious. So on a generic ZK prover, I'm not going to point fingers, but I will name names. It's Halo 2. The total prove time was 322,000 seconds. That is over 80 hours of proving on a 128 core machine with 1 terabyte of RAM. This makes no sense. There are also some metrics for other things you might need to do in Halo 2. For example, store over 30 terabytes of this like prover key thing. Yeah, it just doesn't make any sense. Also, all of this is without recursion. We needed to break GPT-2 up into basically a bunch of blocks, and then we need to break each of the decoder blocks into 3 separate sub-blocks and prove each separate sub-block. So we ended up with like 144 different snarks, and we need to recurse, so on and so forth. Yeah, in other words, this is just like the bare lower bound for that. Okay, so now I'm going to introduce y'all real quick to the concept of kind of like specialized versus generic provers and just take a look at the overhead. So sorry for the jank graph, I just drew this last night. But the TLDR is we have kind of like the technique, so what we're doing on the x-axis, and then we have the overhead. In other words, how much longer does it take to prove than it takes to compute the same thing on the y-axis. As we'll see, even though it's a log scale, there is a big, giant thing with the gap in between. Yeah, and the TLDR is that Halo 2 gets something on the order of basically 300,000x overhead. So for every second of compute you do, it takes 300,000 seconds to prove that same compute. Now, if we're going to talk about the specialized regime, actually, we at Modulus launched, or rather, I guess we've been building this prover system called Remainder. We wrote a paper on it that we released on Monday. And for a certain class of AI models, we actually see just 180x overhead. So the difference between these two is that Remainder uses a proving system called GKR. If you're interested, you can talk to me about it afterwards. But the TLDR is that GKR is just much, much, much better at machine learning algorithms than something like Halo 2. There are other sort of data points from the literature. There's this 2021 paper called ZKCNN. It also used a form of GKR to basically do verifiable inference. I think 90x is actually not giving enough credit. It does better than that. Also, in Justin Thaler's 2013 paper, he did basically a couple of experiments on proving basically what we call the distinct problem, in which you take a stream of elements and you count how many distinct elements there are, as well as basically a native matrix multiplication basically protocol, and we see respectively 10x and 6x kind of overheads for this. So I'm just going to draw the trend line for you. Yeah, obviously you could have interpolated that. And the question is like, okay, where do we need to go, right? And so I think we really need to go to basically this 10x mark. And the reason for this is that currently it takes Llama 7 billion about basically 0.1 seconds to do inference on a single token. And so currently, again, Modulus has about 200x. But the point is that if we get to this target overhead of 10x, then we basically get 1 second per token of provable inference outputs. And really, we can do this commitments with quality at scale, right? All of these models can now have all of these attestations over them, and you know what you're getting. And you're basically looking almost another like person in the eye and saying, great, I know all of your credentials. I know what you're on about. Let's do this. Okay, thank you so much for coming. This is our Twitter.
All right, thank you, Ryan. Well done, sir. And I won't take the QR codes down before everyone's had a chance to get them. I'm looking at you, Matt. Okay. Are you doing Q&A?
Yeah, we can do Q&A, but the TLDR is that the left-hand side QR code is for the Modulus Early Access program. So we have Remainder, and we want basically folks to come and basically contribute and to learn about GKR. We're so excited. We will teach you all the math from the ground up. We will also teach you all the coding from the ground up. It will be a good time. We're only going to take like 10 or 12 folks. It's going to be later this year. We will personally teach you. So please join if you're interested.
What a treat. I would love to be taught by you.
Thank you, Steve.
But I'm definitely not qualified. Okay. Actually, I'm realizing that I was going to do Q&A, but we're actually at time, and now is a good time for a break since we haven't taken one in the afternoon. So everybody, you are released. Please be back. Please be back at 4:10 for Zach Williamson from Aztec. All right. Have a nice break. Test, test, test. All right, everybody, if you're coming in for the next talk, please move on in and grab a seat. Thank you. We've still got a few more minutes, but I figured I'd just nag for the next 4 minutes. Yeah, we've got 4 minutes. Thank you very, very much, yeah. Oh, never mind. I'm on whatever the Mac old standard is, but here, I'll give this to you before you lose it. Thank you. Oh, it's just a Mac plug versus a USB-C, or like an old iPhone plug. It's okay. Thank you. I really appreciate it. Test, test. All right, if you're coming on in, please file down, find a seat, make some room by the door. We'll get started in just a minute or two here. Come on in, find a seat. Okay, we are at T-minus 1 minute. Please take a seat. Please take a seat. All right, how is everyone doing? I'll lean on the front row again. Matt, how are you doing? Are you enjoying yourself? Okay, good to hear it. You all are in for a treat. Next up, we have Zach Williamson, co-founder and CEO of Aztec. Let's have a go.
You. Hey. Oh, thanks everyone. Yeah. Hi everyone. I'm Zach. Won't repeat what you just said. But yeah, so Aztec is a privacy-first smart contract-capable layer 2 for Ethereum, and we've been in the works for several years now. Had to figure out a few technologies along the way, things like Plonk. But what I want to talk about now is effectively talking about how one even enables composable privacy and a smart contract network when everything has to be represented through ZK snarks, and all of these high-level engineering abstractions that developers are used to have to be completely re-replicated from scratch using zero-knowledge solutions. So, do I have a clicker? Do-be-do. Yeah. So, I'm going to go through the cryptography, then the architecture. So first of all, what do I mean by private smart contracts? So there's several layers to privacy. You have user anonymity, so you don't know who's sending a transaction. You then have private state variables, so the smart contract that you're calling, all of its state is encrypted. Not only is it encrypted, but it's undetectable whether that state has been modified by a transaction. then you have this concept of private function execution, where the actual logic of your function is hidden. And this ties in with private contract code, where if you're observing blockchain transactions, you don't even know what contracts are being called by the user, and you don't know who the user is, and you don't know the state that's been changed as a result of that transaction. But you do know that whatever's happened, it's followed the rules. So there was a smart contract that has been deployed, there is code associated with it, and that code has been correctly executed. So yeah, somebody did something to some state of some function of some contract. That's what we mean by privacy. So the real deal, the full Monty. So first, before talking about the cryptography, what I want to talk about is what we want our cryptography to achieve, because that greatly affects the technologies and proving systems that we use, because we have very different requirements to more like traditional transparent ZK technologies. So one main thing is we want this concept of public-private composability. So private state is owned by individual users or groups of users with decryption keys, but a lot of decentralized protocols require the concept of shared state. So for example, the total supply of liquidity within a liquidity pool. So the way we enable this is an asset contract has private functions and public functions. The public functions modify a regular account-based state. It can be shared. Private functions modify a more Zcash style UTXO nullifier set arrangement. But instead of these UTXO notes representing like values, they represent arbitrary state that can be interpreted by the smart contracts according to whatever arbitrary means. And the other important thing is that we want contracts to be able to call other contracts, so the composable part, so that you can have the same kind of incentives and network effects as Ethereum, where if I deploy a smart contract, that then becomes a piece of infrastructure that any other protocol or smart contracts can use. And this is rather challenging because, as you probably can tell, these functions are going to be converted into snark circuits. So what do you mean about what does it mean for a function to call another function when these are just snark circuits? How does a circuit call a circuit? That doesn't make any sense. So we have to make it make sense. And the way that we do this is with this relatively newfangled concept of an incrementally verifiable computation scheme. A bit of a mouthful. But this is effectively just an iteration on the concept of recursion, basically being able to verify a proof of knowledge within a snark circuit. So circuits, verifying circuits, verifying circuits. And IVC is a more formal way of describing this, where you basically have an evolving computation. So you have, in our case, each function call is a step in the IVC scheme. What happens is that at each step, one is using some kind of recursion system or something a little bit more advanced, which I'll get into, to sequentially evaluate the series of transactions. So we have some unique requirements for our technology because of the nature of what we're doing. Our proofs have to be client-side because, well, they involve secrets. There are workarounds. You could use trust execution environments, or you could use multi-party computations, but we want our network to not rely on out-of-band network participants as a base model. So we want to be able to prove this stuff client-side, which means very little memory and very little computation. If there is an ASTIC DApp that's being represented as a website, that likely means that the proofs are not just being constructed locally on potato hardware, but they're being constructed inside a web browser execution environment, which basically means you're running WASM. And WASM code is about 5 times slower to execute than native code when you're working with number field theory, prime field arithmetic. So this all adds up to basically, we have vast limitations on the complexity of the computations that we can perform, yet we must handle complex computations. And we can't just throw hardware at the problem. And so this is the Aztec incremental verifiable computation scheme. I can't zoom in, and I'm guessing nobody here has superhuman vision, so I'll just try to describe at a high level what's going on here. So we have this concept of a kernel circuit, so we very much adopted this nomenclature from the Zexi paper from way back in the day, where what does a kernel circuit do? Well, it takes in a function call, executes the function call, effectively verifies the proof of correctness, and performs consistency checks between any previous kernel circuits that have been called. The idea here is that you have a function call stack represented within the kernel circuit that describes all of the functions to execute. So the idea is in the first step, your function call stack will likely just have one function on it. What the kernel circuit will do is it'll pop that function off the function call stack. That will then, a proof representing that function will then be like verified or accumulated or folded. I'll get into that in a bit. The public inputs of that function call will then be analyzed in the kernel circuit. Consistency checks will be performed. And if necessary, additional function calls will be pushed onto the function call stack, because that's what happens when functions call other functions. The idea is that as a result of that, in the function's public inputs, there's going to be a bunch of inputs reserved for pushing extra, emitting extra function calls. And so this process happens iteratively. So each kernel circuit will recursively aggregate the kernel circuit at the previous step. This is what we mean by IVC. And this entire process continues indefinitely until the function call stack is empty. And then that proof is then given to some third-party rollup prover to include into a rollup block. So there are a few things to notice about this. One of them is, hoo boy, that's a lot of recursive steps for a client-side prover to perform. That's a lot of recursion. So each F that's being fed into K, that's recursion. Each K that's fed into another K, that's recursion. Or in our case, folding. Either way, it's a lot to do. And we're doing this all client-side with limited resources. So that was a key problem that Aztec had to overcome for our architecture to work. And in our view, this kind of architecture is basically the only practical way to provide the kind of smart contract semantics that regular developers are going to expect and be familiar with, that won't require them to understand, like advanced cryptography or handling state trees in strange and unfamiliar ways. So, Goblin. I haven't talked about Goblin Plug. So, we use the proto-galaxy folding scheme to accumulate all of these various kernel circuits and function circuits. It's just a more efficient way of doing recursion. That's the way I see it, at least. Formally, it's quite different. But effectively, what it does is it means that we can fold all of these circuits into an accumulator, where, because we're using elliptic curve cryptography, I'll get onto why we're doing that in a bit. The act of validating that folding within a kernel circuit, it's very efficient, apart from the fact that we have to do these things called non-native elliptic curve operations, non-native group operations. Effectively, because we're using elliptic curves, the prime field that we're working over inside a circuit is not the same as the prime field you need to work over to perform elliptic curve arithmetic to verify or fold a proof of a circuit. This is it's an old problem with many solutions of varying quality, and Goblin is our attempt at a coherent solution that is efficient for our needs. Effectively, what Goblin does is it's a form of delegated computation. The idea is that if you need to perform one of these expensive operations in your circuit, you don't. You instead populate a lookup table with the instruction, and in that lookup table is a claim to the result of that instruction. So the idea is you're basically growing a commitment to a table of instructions to be performed over this unpleasant non-native elliptic curve. And then at the very end of the IVC scheme, we have this thing called a translator circuit, which translates this statement about these instructions from your initial elliptic curve to a so-called cycle curve, the type of curve that you would use in a Halo type system, which is that transformation is relatively efficient. And then once you have that, you can then evaluate all of these expensive operations over the elliptic curve that is actually native to those operations, so they become very cheap. Effectively, the abstraction layer that it creates is that it effectively makes all these expensive non-native elliptic curve operations cheap native elliptic curve operations, which means that the folding protocol becomes very, very efficient to evaluate inside a SNARK circuit, which means that we can do all of that expensive, painful IVC client-side. I'll show you some benchmarks in a bit about that. So yeah, it's an accelerating scheme. It's relatively new. We have a we have a HackMD that describes it, and we'll have a proper paper out, hopefully in the next couple of months. So this is kind of our lead applied cryptographer, Cody, put together this goblinized proto-galaxy IVC scheme, where basically these Fs, they're function calls, we have these kernel circuits, and we have this relatively complicated merge and folding scheme system, which means that the individual circuits on the left-hand side of that diagram are relatively low complexity, cheap to evaluate, and these elliptic curve operations, they go into this transcript, this operations queue, that we then process externally via this Goblin-Plonk protocol to make them efficiently evaluated. Right. Well, that's a lot of nonsense and a lot of words. But to try and summarize it, we've had to choose a cryptography tech stack which satisfies some unique requirements. We have very little memory consumption. We have to perform recursion exceptionally quickly with extremely limited resources. We're talking less than like a gigabyte of RAM. And so for that, we really need a folding scheme. Folding schemes are the absolute fastest ways of evaluating recursive compositions. And folding schemes have to work over elliptic curves because they require linearly homomorphic commitments. And then we use Goblin-Plonk to eliminate the remaining expensive part of these folding schemes. And the actual SNARK protocol that we're folding, that all these proofs are happening over, is something we call HONK, which is a variant of ultra hyper Plonk, I believe. So it's Plonk, the original like Plonkish type arithmetization with a log derivative lookup protocol, and then we, instead of doing quotient testing, we use sum checks to remove the need for fast Fourier transforms, which crosses down the memory, and a bunch of custom gates. So this is a linear time proving system with very good constants and very low memory consumption, particularly when you also add in the fact that recursion in the form of folding is very cheap. It means that it's much more practical to break up large computations into smaller ones so that the overall memory consumption of your device stays low, say a gigabyte. So here's some benchmarks. Now these are very outdated. So these are basically, this is what we did before we went on optimization passes. So they're about at least 5 times slower than what we think we'll get them to once we've actually, focused on making our code fast instead of just making sure it works and is, relatively modular. So what we're measuring here is effectively our estimation of what a moderate complexity ASIC transaction is going to require, which means we have 6 circuits of 128,000 constraints that each represent a function call, and then we have 6 kernel circuits of 128,000 constraints that represent the logic and algorithms that will be required to validate that these function calls have been performed correctly and perform required things like state reads, state updates, consistency checks. So overall, we're talking, 12 times 2 to the 17. So this is a lot of constraints for a phone or for WASM. And this also includes all the incremental verifiable computation schemes, the Goblin-Plonk stuff. And so this all takes about 4 minutes in WASM. So this is not native CPU. This is in WebAssembly. We're confident we can get it down to 1 minute for our initial launch of the ASIC network, and I'm actually hopeful we can get it down to 30 seconds. There's lots of scope to optimize this. As I said, we've been focusing more on coherence and visibility of our code above optimizations. But yep, these are the numbers that we have so far. So in the last 5 minutes, I want to talk through the architecture of the ASIC protocol. So I've talked about the cryptography. Okay, so we have this rough IVC scheme concept. We have kernel circuits. We have public and private functions. But this is all, a far cry from a private smart contract network. So how do we take these ingredients and actually cook something with them? There we go. So this is our architecture. So my name has been Zach. Thank you very much. So our architecture lead, Mike, this is his baby, his grand design, and I just wanted to show it off because I think it's impressive. But yeah, there's a lot going on here. So this is going to be a very high-level description. First of all, what makes up a user's transaction? So I mentioned before we have this kernel circuit proof that they're going to have. the kernel proof is kind of ready to be consumed by a rollup if the call stack, function call stack is empty, because that means, oh, there's no more private things to do. We have a list of the private state variables that need to be added into the encrypted state tree, and the list of nullifiers to add to the nullifier set. We also have a list of public functions to execute, because client-side, we only do the private stuff. We just offload the public stuff to a third party. And also a bunch of the world state that's used to compute the kernel proof. Fair amount of information. And this is the rough transaction flow. So the idea is, on your local device, you start out with this kernel proof. You send it off to a sequencer network to be processed. The sequencers effectively act as block builders. We're going to be using this proposer builder separation, so there'll be the steady state will be much like Ethereum, where you have these block proposers suggesting blocks to builders, but and then those sequencers will farm out the proofs to be constructed to a proven network, and then that hits the rollup contract on Ethereum. So we need to build some private abstractions, and so we have a unique language to handle this all in, because Solidity is an EVM language. The EVM is not privacy compatible. It doesn't have any concept of private state, private functions. And so we wrote our own language, Noir, so that we could provide the contract semantics that we needed to developers whilst ensuring that they could still write their programs efficiently. And we based it on Rust. So it's got very, very similar properties, very similar syntax. They should look very familiar to anyone exploring the Noir language. And so all of the private state is encrypted as these UTXO notes, much like Zcash, except that there's more stuff here. So instead of just a value, you have the address of the contract that produced the note. You have this nonce to ensure non-uniqueness. And then the data that's represented in the note, as well as this storage slot. So like Ethereum, like Solidity, you can have a contract can have multiple storage variables, so they're all assigned slots. And the idea is that the kernel circuit is the one enforcing the contract address in that hash. So your smart contract can't cheat. This ensures that state generated by each contract is unique and does not overlap with one another. And again, we use this concept of nullifiers to ensure private state updates are genuinely unlinkable by observers. The idea is your UTXO tree, when you want to destroy a note, you don't actually mark the note as destroyed. You encrypt the note using a different encryption algorithm and add that to a nullifier set. And the existence of that note in the nullifier set indicates the note has been destroyed. And so you can then prove a note is still alive and hasn't been destroyed by proving the non-existence of its nullifier in the nullifier set. So yeah, this was originally, I believe, pioneered by the zero-coin protocol. And so as I said before, these notes live as storage slots, and these are some of the abstractions that we are providing developers with. So the idea is that they don't have to deal with any of this weird Merkle tree stuff. They just call, they grab the variable they want to mess around with out of storage. They can either remove UTXOs or they can add them. So we haven't completely hidden away the UTXO abstraction because we felt like any attempt to abstract that away would be incomplete and would probably just lead to developers either creating insecure code or not able to produce the kind of code that they would, algorithms they would like to. So private transactions, I'm almost running out of time, so I will try to be fast. Private transactions can kick off public effects, so they can emit public events, they can call public functions. The reason why this can happen is because the private and public functions are kind of executed out of order. And by that I mean a user's private functions are executed first, and then after that the public functions are executed, which means that a private transaction can unilaterally call the public function, but that public function can't have any return parameters, which is an interesting issue, but we have some abstractions to work around that. And similarly, you can call a bunch of events, emit a bunch of events if you desire. And yeah, so the idea here is we have two state trees, the private one, UTXO-based, and an account-based state tree that public functions modify, so that you can provide things like DeFi and like the whole spectrum of applications you expect on Ethereum, but you can selectively encrypt and hide information, for example, things like user identities. And you can also create very powerful account abstraction contracts because you can do things like sign in with Google, sign in with Apple ID, and that whole process goes hidden from the blockchain. But it means that you can have a contract that is controlled by your Apple ID account. which makes things like account recovery an absolute breeze. And then finally, once you have all of these proofs, we have a kind of a tree-based rollup structure where we want to be able to break down our rollup block into a large number of independent snark circuits so that we can farm out a lot of independent chunks of work to the prover network so we can benefit from mass parallelism. And then those proofs are aggregated recursively to form a tree. So assuming you have enough parallel resources, the time required to construct the block proof roughly scales with the log of the block size, which means you can make massive blocks very quickly. And so I believe that is it. Thank you for listening, and thank you for Adam and Cody for some of these slides, which I stole from their earlier presentations. And yeah, go follow us at aztec.network and noirlang.org and play around with what we built. I think you'll be very surprised by where we are.
A heartfelt thank you. That was an exciting update. All right. Thanks again. Big round of applause. Our next panel should be here imminently. Come on in. Hello. I'll let you do all the introductions, okay? Okay, sounds good. Yeah, okay, great. The microphones are all on the table up there, and I'll go get a chair. One more chair, I'll go get it.
Thank you.
Yeah, I'll just like stand over you guys. No, I think we can bring another chair.
Oh, yeah, I think that would be better for you.
Yeah, be like, okay, listen. Thank you. Of course.
All right, break a leg, everybody.
Let's be careful with water.
Great. Should we get started? Cool. Hello, everyone. I'm Kelsey McGuire. I'm the CGO of Shardium. It's an auto-scaling blockchain. And I'm here with Charles and Derek. So could you guys give a quick intro? Yeah, GM. Or GG afternoon. About who you are and what your project does?
Sure. I'm Charles Guillemet. I'm CTO at Ledger. I think everyone knows Ledger, right? Who owns a Ledger in the room? Okay, so everyone knows Ledger. My background is cryptography and security, and I joined Ledger in 2017. I discovered Bitcoin in 2011. A friend of mine was talking about Bitcoin like every day, so at some point I decided to have a look at it. And I studied the cryptography, the decentralized consensus, all the complex things. And I remember I told him, your thing is amazing, it's really interesting, but I don't see the use case, it's not useful. So when I joined Ledger in 2017, he made fun of me, asking me if I finally understood. And I think I got it. And what I really like in Bitcoin and in blockchain technology is the permissionless aspect. And this is why I think self-custody is important. This is what we are doing at Ledger, self-custody with security.
Awesome. Hey folks, GM again. I'm Derek. I'm the CTO at Vault Connect. And yeah, maybe a question for you in the room. Who thinks that crypto UX currently is really awesome?
No hands?
Who of you runs their own full node? Right on, Charles. Yeah, so basically, I'm a Web 2 bro. I did some open source in crypto before I joined Vault Connect roughly 2 years ago. And I joined because I saw the opportunity that we can actually like build decent UX and through that seize the prophecies of blockchain. And I think we are sort of at the precipice of creating SDKs and tools where application developers can come in and actually build delightful applications and like bring a couple of users. And yeah, so the question is, can we achieve that this year? And then when can we get to 1 billion daily active users? Is it going to be in 2030 or maybe in 2026? So yeah, I think right now is a really exciting time.
Awesome. Thanks for the intros, guys. So we've seen a lot more focus recently on UX in Web3, thank goodness, which is really exciting. So I'd love to hear from you guys about some of the most interesting, exciting things you've seen recently and why they're happening now.
In terms of UX, you mean?
Yes.
Yeah. So yeah, I agree with Derek. Like the UX for blockchain is quite terrible. We can see that all of this has been made by geek for geeks, and this is the case. And if we want to consider a wide mass adoption and so on, we need to fix this UX problem because I don't expect my mother to understand what is zero-knowledge proof or how cryptography works or how bridges work, and that she needs to take her Ethereum to bridge them on a layer 2 or another. So this is really something that we need to think about. Make sure that the user interface and the user experience in general is really simpler. Abstract all of this complexity. I'm very excited by the new cycle that is about to start. During the last cycle, we really had a scalability issue with blockchains. There was not so much dApps, but even a very simple dApp such as OpenSea, it's a simple dApp. When it went live, it simply broke Ethereum just because Ethereum doesn't scale. And since then, we built the infrastructure, we built the L2 that allows this scalability, and now we have this infra. We are looking forward to seeing what dApps we will build on top of this infrastructure, but the UX component will be really key. Again, we can't expect people to understand the underlying technology, the fact that they need to bridge assets and so on. All of this should be abstracted to users, I think.
Yeah, and over the years, even when people think the technology is really cool and exciting, I've just not met very many people who will stand to be inconvenienced even one extra step when it comes to interacting with any new system or application. But Derek, would love to hear your thoughts on that as well. Like, why are some of these advancements happening now? Is there a particular one, whether it's abstraction or something else that you think is really interesting right now?
Yeah, thanks, Kelsey. Yeah, I think less clicks is more, obviously, and convenience always wins. So a couple of exciting things that happened recently, everybody here in the room knows that, but to maybe reiterate. First thing is, scaling actually is a UX thing, so Shardium. So scaling means transaction fees and bandwidth. So to me, that's a UX problem. Like as an end user, I want cheap transaction fees. So I'll claim that we have a solution for that. So that problem is solved. So next is, I don't wanna know what gas is. Well, actually, through scaling, we made some problems worse. So as an end user, you need to learn what gas is, and now you need to have gas token, and now you need to have gas token on not just Ethereum, but on 40 different L2s. So actually, we made the problem worse. But now, obviously, with ERC 437, which Quick Shill was launched the Ethereum Foundation launched it at the WalletCon conference exactly 1 year ago here in Denver. So with that, the end user doesn't have to learn what gas is anymore, and the end user also doesn't have to have gas token anymore. So obviously, we're seeing the uptick there now with EIP 3074. That also for old accounts, for externally owned accounts, like for basically existing users, you can now also sponsor transactions. I think Polygon is the first chain that's going to launch that. A bunch of other L2s are going to do it, maybe L1 in next year with the next fork that we expect. And so then the developer's story is going to be good because as a dApp, as Uniswap, as all the cool apps that maybe some of you are building, I can sponsor transactions for 100% of users. Like as an app, I want to support 100% of users, and now I can sponsor gas for 100% of users, and also with 3074 and 4337, I can batch 100% of transactions. So in your game, if you want to change 30 Sims token for, I don't know, a new avatar, and then you can now do that in one transactions or in crypto Tinder if you, yeah, I think you get the point. So that's another thing maybe. Another thing is mobile first. So there's now mobile first SDKs that Wallet Connect provides, like in all programming languages. So we're seeing like this uptick. Also, there's 1 year ago, if you wanted to build a consumer app and you wanted to raise money, the VC will tell you your low IQ. And now there's a bunch of VCs out there that will probably give you money. So that's also exciting. And yeah, last thing I'll say is obviously there's now an onboarding path for end users. Like I actually recently using Peanut.to, which is a P2P payments app that I really like. I used to work at Venmo, so I know the P2P payment space. And so I sent my mom some crypto. She's never used crypto before. She was able to claim that onto her email wallet. And I asked her to send it to my dad, and she was actually able to do that. And like she didn't even know it was crypto, so I think that's cool. Yeah, and actually one more really last thing. And Charles has a blog post on that. What's also exciting right now, folks have to have so much anxiety around how do I store my keys. Like even though I can have a device for self-custody, I actually don't want to bother about that. I want to maybe like on-ramp with email, and then later I decide, hey, dang, I have like serious money on this thing now. So, but I want to use this day to day. So like obviously with recovery things, Safe has great stuff there. So yeah, really many exciting things. The challenge is to like now plug everything together, build the right standards, and we really don't have a year to wait. It really has to happen now. And like Charles and I were doing this Hack Week together shortly, and yeah, a lot of industry partners who can pull strings will be there. So I hope we'll get it through. So yeah, this was a long monologue.
You're teasing a lot. So yes, I think the idea around account abstraction is very, very powerful. The EOA, it was a good idea. It's very simple. You just generate your pair of key, and then you have an account. We inherit this from Bitcoin, and this is very powerful. But as soon as you want to implement complex logic around this, it's simply not possible. The blockchain do not provide you the tools to do that. And that's why account abstraction is an interesting idea, because you can implement as complex logic as you want. And with that, you can implement like easy onboarding, where the user don't even know that there was a blockchain behind. So I think for an onboarding new user, it's an interesting idea. The combination between passkeys and account abstraction is a good idea, and plenty of people have implemented stuff around that. And by the way, at Ledger we have built a verification of the P256 curve, the one that is used by passkeys, and our implementation is really good in terms of fees. So it's a public good, and plenty of implementation of account abstraction are using it. And so with this concept, you can really ease the experience for the user using their account abstracted account. Nonetheless, as soon as you need to have more security, you can understand very quickly that a passkey is in your phone to secure your high-value item is probably not sufficient. And with account abstraction, you can imagine some experience where you can define that you can spend up to $100 USD per day with your phone. And if you want to spend more, probably you will need to use your Ledger device. And if you want to spend this very valuable for you NFT, same, you will use your Ledger device. This is something that you can do with account abstraction. Also, for the recovery part, you can implement really interesting experiences. There was also something I'd like to highlight. Sometimes people say, oh, now there is account abstraction, there is no need for seed anymore, we have solved the problem of secret. I think it's really bad marketing, because with account abstraction, you still need to authenticate yourself. Obviously, you don't need to do EOA type of signature, but at the end, you will need to prove that you are yourself, and you must not lose those credentials. So this is something that needs to be taken into account, and it does not solve the security problem directly, because sometimes this is some bad marketing I heard about account abstraction.
Yeah, that makes a lot of sense. I think we have a ways to go when it comes to sometimes setting the right types of expectations when it comes to these exciting new advancements, as well as just really where people can access and learn about the technology in a more productive way. I think that another one for you, Derek, to start with is, do you think Web 2 feature parity is enough, or is this just a little piece of the puzzle as we're moving forward with this?
Yeah, my naive romantic thing is we're gonna get like better experiences than with Web 2.
That would be ideal.
But currently we're still far away from Web 2 experiences. There's no way. Currently all signing experiences, all crypto experiences are synchronous, which means like I actually click a button on my ledger to sign, and that's not how payments works in the internet. Like there's subscription payments, and I don't. In Web 2, when I use a game, I don't always have to click a button in order to do something. Maybe it's like asynchronous, and so that's why I'm really excited about what the community is now calling permissions. And so permissions is going to allow you better synchronous signing experiences with less anxiety, where you can, similar to what Charles said, say, okay, this app can only spend up to $100, and then you can use that, gate it with a passkey. It's important to do this via permissions, because there you can do it without gas and without drama, and you can lose the, I'm German, so I don't like drama, and you can do it without gas. And now you can also do these async experiences, so you can say, okay, I allow this newspaper to charge me $30 every 30 days. So that's important for feature parity. And then what's beyond feature parity, of course, is I can are like some of these identity use cases, for instance. Like obviously, for me, it was very rough back in the day. I had all my reputation on MySpace, and then MySpace wasn't cool anymore. And I had to bootstrap my reputation somewhere else. And so that's not great user experience. Also, all the creators that are being censored on Instagram, and all this kind of stuff. So I think we should have better experiences for them. So to me, it's obvious, and we just need to fix the UX so that the builders can actually come, and such that the creators will use the platforms where they have this freedom and whatnot.
Yeah, I think users always take the path of less friction, and we can try to explain why blockchain technology is great, why self-sovereignty is important, and so on. But I think for onboarding users, first the experience will be key, and then when we onboard users with a very great experience, at least at parity with Web 2, then we can explain why self-custody, self-sovereignty is something that matters. But I don't think we will create this mass adoption with these ideas of self-sovereignty and permissionless.
Yeah, so we are making progress. At least it's more of a focus now, like we touched on. And we talked about this a little bit already, but we're still facing some really key challenges here. When it comes to user experience, and from my perspective also, there's a big reputational challenge when it comes to this new technology. I think when people can use it sort of seamlessly in the background, it's fine because they don't really realize what's happening. But I don't know about you guys, but I've seen a lot of TV shows and movies right now where it's like Web3 blockchain is almost the bad guy and the scary thing. So from your perspectives on the UX side of things, are there any other really key challenges that you have in mind that we're facing as we think about onboarding this next big group of users outside of that reputational challenge that we face as well?
So I can talk about what we are doing at Ledger around this UX problem. So security is really the promise of Ledger, and then from this never compromise with security, then we are trying to improve UX, and there are a few points that really needs to be improved. One of them is the fact that when you sign something, you need to understand what you sign. Signing hexadecimal is not acceptable from a security standpoint first, but also for the user. When my mother sees an hexadecimal address on the Ledger device, she thinks there is an error. She thinks there is something wrong. So we need to fix all of this. No hexadecimal. The user needs to be able to understand what he is doing. Also, we have worked on creating some recovery process. You probably have heard about this. It created some drama in the ecosystem, but at the end, what we want to do is really to improve UX. Again, when I think about my mother, and I explain her what are these 24 words, she needs to write them down on a piece of paper. She needs to hide this piece of paper. No one must have access to them. If ever she loses it and she loses her device, her funds are gone. So it's
stressful.
Yeah, it's stressful. So this is really for this kind of user that we wanted to create this product that is called Ledger Recover. And we can see that there is some resistance in the ecosystem about this kind of feature. So we also need to figure about that and to think that the mass adoption will be possible if we think for the newcomers that are not geeks like us, and this is the point of focus that we have in mind. Also, we are working on new devices with a wider screen, with a touch screen, and so on. So again, to improve the UX while never compromising with security.
Oh, thanks for that. And this one's for Derek. So how have you evolved the positioning of Wallet Connect? And are you thinking of a wallet as a service model, or where are you guys heading with that?
Yeah, thank you. We have right now we are the most popular app SDK out there, and our app SDK has an onboarding wallet, like a wallet as a service email type wallet, so that's launched. Please go check it out. Let me know if it's nice. It also has a fee-less on-ramp, so 0% fees to on-ramp into USDC with that thing, so that's cool, and good UX.
The important thing.
And yeah, it's the same OX address on all apps, so no fragmentation, and also we have a graduation flow. We're the only ones who do that. So currently that's a private key export. Soon it's going to be a signer rotation. So we want to graduate the user from no coiner into coiner, basically gradual transition. So yeah, I'm pretty excited about that, and I think soon there's brain-off experiences that have Web 2-like feature parity or better.
Yeah, that is really exciting. And I want to get back into Ledger a little bit more now too. Like, how do you see, you touched on it a little bit, but how do you see hardware wallets fitting into this broader mass adoption push?
So again, when you own assets, when you own crypto, like the security part is something really important. When you think about onboarding newcomers with perks on a website, that has not a lot of value. Probably you don't need a ledger to do that. Like simply having your keys in the browser with an abstracted wallet that you don't even know there is a wallet, it's completely okay. But as soon as you need to protect your value, then hardware wallets become important. And what we are trying to do is to when as much as we can the friction you have when coming from the fact that you have another device. So this is directly some friction. So we want to remove this friction. So we are improving the experience that we have on our current devices, and we are thinking about new experiences in the future where something like your phone and something like the devices that we sell could be combined in the same devices. I don't announce anything. I'm just talking about the type of research that we are doing these days, because putting your keys in your phone doesn't work from a security standpoint. But if we think about that, and if we are trying to improve the security level of something like your phone, we could consider experiences where you have best of both worlds, the very good experience that you can have with your smartphone, and the level of security from Ledger.
I want to add some thoughts. So I think right now, hardware wallets can cover some user stories, but it's pretty limited. Like a user story might be, okay, I have this kind of Bitcoin stuff and I want to store it somewhere. But it doesn't solve for use cases for like, okay, I have like some serious NFTs or whatever. But I actually want to disclose that I have them. I want to show on Crypto Tinder that I have like the coolest, assuming there's women in crypto. Until then, I think Crypto Tinder is a bit difficult. Yeah, so I can disclose my reputation there, and right now there's no good user story for doing that because I don't want to connect my ledger to like this fun app because I might get scammed, and also maybe this wallet I'm just using it. And like now I'm adding more funds to it, so it sort of turns into my serious money wallet, and I have different requirements. So I think with the permissions, which is now a thing, that solves the first problem of, hey, I have all this reputation, I want to show it in every app, and I don't want to have anxiety that I'm going to get scammed. So permissions is going to solve that, and then I think the smart accounts should be like a massive demand push for Ledger, because now I can do stories like, okay, I have this account, if up to $1,000 I use my passkey, and that's what Charles mentioned earlier, up to $1,000 passkey, 20,000.
I said 100.
$50,000, my mom, I need an extra signature for my mom, multi-sig, $150, I need my mom and my ledger, and then when we're talking serious money, then maybe the bank also needs to sign or something. So this should be, yeah, there's so many more user stories coming now where I really want to have a ledger. So yeah, should be exciting times for Ledger.
Definitely.
Yeah, it sounds like super exciting times. As far as the ability to impress ladies with NFTs, still to be determined, but I think that's about it for our time, guys. But could you all
Thanks, Kelsey.
like close out and let people know where they can find you? Any sort of final call to action before we're off the stage?
You can find me on Twitter. You can look for my name, and there are around 20 impersonators. I'm one of them.
You're in there somewhere.
In terms of call to action, we are working on the clear signing initiatives in order to make sure that every single interaction that you will do on your device with Ethereum first, at least, you will be able to clear sign them. So no hash, no input data anymore, like just something, an intent that you are about to, that you can understand what you are about to consent. And for that, we need the help of wallets to integrate our SDK and the metadata file. And we also need some help from dApps in order for us to curate this metadata file that allows the device to parse the transaction properly.
Great. And Derek?
Also want to know how I can follow you, Kelsey, but I'm CyberDRK on Twitter. And my ask for you is, yeah, go build awesome apps. Let us know if our SDKs are awesome or how they can be improved. And yeah, I forgot my last point. But yeah, thanks so much for listening.
Yeah, we can jump back to it. And I'm Kelsey. Go to shardium.org to learn a little more there. I'm a big kind of just lurker on Twitter, but if you want to come check that out, it's at Hey Maguire. So thank you all so much. Do you remember? Are you good?
I don't.
Okay, cool. Well, come find him after and he might remember. But thank you all so much for joining us today. We'll see you around.
Thank you.
All right, thank you so much. That was awesome. Derek, I want to know where you got the shirt.
Really? India?
He said India, in case anyone's wondering.
Yeah, if anyone was wondering. Thank you
If you
so
could,
much.
if you could drop off those mics, the AV, except for one.
Should we leave these
I'll
here?
take
Okay,
one, and if you
cool.
could take the rest to the AV, I would deeply
Okay.
appreciate it.
Awesome.
Thank you so much. Really appreciate it, all of you.
Thank you so much.
Thank you so much, especially. Okay, awesome. Okay. Okay, there we go. That was wonderful. I'm really excited for some of the state they described in terms of usability. We have our next speaker coming up momentarily. I'll wait till I see the whites of his eyes before I introduce him. I see his deck. Sorry, guys. Hey, Krish, come on up. Oh my God, I have to apologize. Rookie move, sorry y'all. All right, I hope you all enjoyed the quick break. It is my honor to introduce Krish. He's from Oxpass. He's got some exciting revelations about his product. It's in the same vein around usability and security, so I will leave it to you.
Awesome. Thanks, Stephen. It's 0xpass or OXPass, by the way. Well, hey everyone, I'm Krish, one of the co-founders of OXPass, and we're the builders behind Passport Protocol. And Passport Protocol is a distributed and programmable key management network. And we're building it as a network that has the ability to scale to onboard the next billion users into crypto. And I'll walk you through this. Wait. Okay. Okay, so this is not an old concept. I think we all realize this. You know, mainstream users have modern UX expectations. This has been a topic of debate for the last 2 years. People want social accounts. They don't want to sign every single transaction. They want transactions without having to pay for gas and so on. And there have been many approaches to solving this problem. Account abstraction, embedded wallets, wallet as service providers, a ton of different wallets, hardware wallets, etc. Even decentralized social is, I'd say, a tangential way of approaching this problem. How do we onboard users into crypto? But I feel like it's, in some way, at the core of all of this is the private key. Because account abstraction, all of these revolve still around the private key, and we've seemed to have forgotten that. And there's 3 things that dictate what happens with the private key. The first thing is the custody model. Who owns the private key? Is it the user? Is it someone else? Is it shared between the user and a third party? How is this key stored? And what are the resulting UX implications of that? And historically, right, there have been 3 different models of custody. There's been the self-custody model, where the user themselves holds the entire key. And then there's been the shared custody model, where the key is split between the user and a third party. This is what we're pretty familiar with. Like if you looked at Web3 auth, Privy, etc., that's the approach that they all take. And then there's delegated custody. Historically, this has been the most centralized option of all of these 3, where you rely on a third-party centralized custodian to keep track of the user's key. And when developers are deciding between all of these, whether you have to, let's say you're building an account abstraction product, you're building smart accounts into your dApp, somebody still has to manage the signer for that smart account. And when you're deciding between these three custody models, you're probably looking at these three factors. The first thing is flexibility. How flexible is this option? Like, can I bring my own auth systems? Can I just bring something like Firebase? Can I use Clerk? Do I have to rely on a third-party auth system? Do I have to rely on a third-party provider? How much control does the user have? Does the user entirely control the keys? Is there a third party involved? And then performance and scalability is a huge concern as well. Does this scale to millions and millions of users, especially as crypto moves into this wave of consumer apps? So going through delegated custody first, that's historically the most centralized one. You have a third-party custodian that keeps track of the key entirely. One of the biggest advantages with that is this is truly seedless, right? Because the user doesn't have to keep track of anything. And if you're a mainstream user, you don't want to keep track of anything. And the second thing is that the key is entirely programmable. Because I can come in as a developer and say, I want email as my primary auth, I want passkeys as my secondary auth mechanism, and if they all fail, I still want to use Google OAuth. I can kind of customize my auth rules as I please. And programmability also extends to the transactions piece. I can come in and say, I can program the key to sign when, for example, ETH is above 3,000, then I'll just automatically swap to USD or things like that. It also helps onboard users with social accounts. But then again, the biggest problem is that there's no user control. You're relying on a third party to essentially play God. You're placing too much trust in that centralized player. Self-custody, we all know this, the gold standard of complete ownership, rely on a MetaMask, I own the entire key, but then again, there's a risk of loss and it can't really scale for mainstream use cases. Then shared custody was actually created to solve this problem. And we're pretty familiar with all of these. It's what you're looking at in all of these new consumer dApps. There's partial but explicit ownership because the key is now split between a third party and the user. And traditionally, that's two shares that lie with the user and one share that lies with the third party. This is good because now I can onboard with my social accounts, but again, this limits flexibility because now you've lost out on the programmability piece. Now developers cannot come in and say, these are the auth providers that I want to use. They don't have full control over that. And again, this is not truly seedless because the user still has to keep track of a recovery or a device share. They just don't happen to know it. So it doesn't really solve the core problem of not having to keep track of the private key. It almost just hides it in some way. And we actually spent our first 8 months connecting to all of these different key management solutions through this simple UI component that you see. It's a wallet adapter. That was our very first product. Developers could just plug in our UI component and connect to all these third-party providers and just help users on board. And then we realized there's a huge problem with how key management is happening. There's nothing out there that's flexible yet non-custodial. And so we asked ourselves this question: how can we build a key management solution that's programmable, the most UX forward, and yet non-custodial? And so that's when we ended up with Password Protocol. It's a distributed, programmable, and MPC-based key management network. And this was only possible because of two inflection points. Number one, MPC algorithms themselves, but also secure enclaves. And this is how this works. So unlike the traditional Shamir secret sharing or MPC model, the private key is split into shares that are entirely distributed among nodes in our network. And every key share is encrypted through secure enclaves that each of these nodes run. And in addition, MPC algorithms make sure that the private key never comes together in whole. So this way, the key lies entirely within the network, and yet it's still non-custodial because the nodes themselves can't access the key shares, and the MPC algorithm makes sure that the key never comes together as a whole. And we also have a flexible permissioning infrastructure layer surrounding this, wherein developers can come and customize rules around how authentication and recovery happens. So I can come in and say, I want passkeys to be my primary auth, I want email, or I want to create my own backend, and I can kind of mix and match between all of these different authentication methods. So in this model, the user can actually talk to the network directly, and every single auth method, every single user verification happens through enclaves as well. So the network actually can't play God. There's no way for the network to interfere with any of these requests. And we actually can remove the third party from auth as well. So if you're a user, you can talk to Passport Protocol directly with passkeys or OAuth, and we'll spin up a key for you. Or you can also rely on a third-party developer. And again, as I said, you can mix and match these methods. OK, time for a quick demo, if any of you guys are interested. We actually launched our testnet just today. And it's currently the fastest distributed key management network. So this is passkeys on Passport Protocol. And it should take 1 to 1.5 seconds to do keygen and sessions. So give it a shot. I'll keep this on here for like a minute or so. So if I had to walk through this flow, what happens here is you as the user talk to the Passport network directly. There is no intermediary. And Passport creates the challenge for you. And we actually spin up a wallet without you having to keep track of any key shares yourself. And your private key actually lies entirely within Passport Protocol and in a way that only you can control. OK, you can also check it out at another time. It's demo.0xpass.io if you want to check it out later. But as I said, this is the fastest right now. And again, one big unlock of this is programmatic signing. It is now literally possible to program when and how these keys actually sign transactions. So developers can come in and literally write JavaScript code that executes within the network that specifies when and how transactions take place. This is big because as a developer, I can come in and say, I can say things like, when the ETH price is, let's say, as the previous example, when it's about 3,000, go and make a swap. Or I can chain events together. I can rely on APIs from the real world to execute transactions. All of these will be pre-approved by users. And again, none of this leverages smart accounts. All of this is off-chain within our MPC network. All of these will be pre-approved by the user. And they actually run in a completely non-custodial manner. And the network decides when to approve and reject a transaction, depending upon what the program does. And again, this is our lambdas in action. I don't know if I can click on this. We can't click on it, can we? Yeah, it's OK if we can't click on it. I'll explain. But essentially, what happens in here is, OK. Yeah, if you can just run that, if you can just full screen that video. Can you tap on the video? Is that possible? OK, so what's happening in this video is we have a Passport wallet that only signs a transaction when someone enters the number 8. And so if you enter the number 1 or 2 or whatever, the transactions never sign. And all of these conditions are executed within the network. And so this is essentially programmability in action. And everything happens between 1 to 3 seconds. So again, this is the fastest implementation out there right now. Yeah, we can go back to the slides. Thanks. Just waiting. we're not going to click on a link again. That was the last link to click. Okay, awesome. So that was programmatic signing in action. Again, implications of Passport. What is now possible that previously wasn't? Number one, the programmability piece. For the first time, the private key is programmable fully in a non-custodial manner. Onboarding is truly seedless because the user doesn't have to keep track of a recovery or device share. And again, everything is non-custodial, including authentication and verification, which happens through enclaves on our network. It's interesting because we're actually seeing 3 different use cases with Passport right now. The first one, obviously, MPC wallets. We have people building wallets on top of us. So we don't directly build wallets themselves. We're really the underlying wallet infrastructure. And then we have a lot of account abstraction use cases, people using us to manage their smart account signers. And finally, we actually have wallet as a service providers also building on us, essentially using us as an encryption layer to encrypt one of their key shares. There have been other approaches to this, but the reason that we are different is because we are the ones that are focused most on performance. And the way we do this is we're starting off as a permission network. It's a closed network, completely off-chain, and that way we can actually optimize for performance in a way that other players really can't. Again, traditional approaches to building out these MPC networks, right? The node handles everything, usually. That's auth, verification, communication, also keeping the key share itself. And that's because they're really trying to optimize to be a very open and permissionless ecosystem, kind of like your blockchains are. But this also means that if you're a user or a client, you're a developer, every single time you make a request to the network, you have to talk to every single node that's presented in the network. And there's so much communication happening between these networks, between these nodes and the client, that it really clogs up performance. And also, the key shares are distributed among a high volume of nodes. Imagine a network where there's like 30 of these nodes, and 20 of them need to come together to sign a transaction. That's a lot of time. That's a lot of work. So we've actually invented a new approach to this. We're calling it the halides approach, where we separate the nodes from another element called the orchestrator. Within Passport, the nodes only handle the key share and nothing else. Everything else is handled by another layer that we call the orchestrator layer. So the authentication, verification, communication between the nodes is handled by this secondary layer. And secondly, we actually cluster different nodes together. We take a key share, we split it into chunks, and we actually create clusters out of them called halides. And so the implication of this is that the client no longer has to talk to all of the nodes. The client talks to an orchestrator. The orchestrator handles everything when it comes to auth, verification, and communication. And the halides make sure that the threshold is always 2 of 3 in a way. And so this essentially helps us build something that's the most performant as an off-chain network. That was pretty much it. Passport's testnet is actually now live, so if any of you guys are interested in using us or partnering with us, you can go to 0xpass.io and sign up. And that's also my Telegram, so if you just scan that and you want to talk to our team, feel free to scan it and I'll respond. That's pretty much it. Thank you. Yeah, open to questions if there are any.
Thank you so much. That was awesome.
Thank you.
All right, another big round of applause for Krish. All right, so we just have maybe a 2-minute little pause here as our next speaker makes his way to the speaker room. So, oh, there he is. Sorry, I didn't see you there. Ilya. I expected you in the wings over here. Well, thank you so much. This is Ilya, founder of Near. Here we go.
All right. Thank you. Ooh. Hopefully everybody's still awake. I know it's a little bit, the snooze zone of the time. You're getting ready for drinks, getting ready for those happy hours. And I have a clicker. Cool. So I'll talk about chain abstraction, like what it is, why do we need it, what cool things you can build with it. So let's get into it. So my main thesis is the dApps you all guys are building are not real. They're not really applications, they're just front ends for smart contracts. Right now, you're forcing the user to figure out how to actually do stuff, how to fund their accounts, how to find your application, figure out if the smart contract your front end is connecting to is the real smart contract or you're being hacked in the middle of it. You figure out kind of a lot of things that like normal users don't really have ability to do, and obviously all the things people just talked about, key management, seed phrases, all of those pieces. That's not experience we want and can have if we want to bring billion users. So we have a kind of highly fragmented world, and with every chain launching, we're fragmenting it more, right? And it's really exciting to have more and more functionality, more and more people building, but everybody's now launching a separate chain, and you have kind of more and more fragmentation. You're launching an app on a specific roll-up, on a specific layer 1, you're fragmenting your target audience. You don't have a way to address audience across the whole Web3. The liquidity is fragmented. The developer experience is now like, I need to figure out where I'm building, not based on what I'm building, not based on experience I want to receive, but based on where I hope I can acquire users. And as a user, you have no way to find applications, right? Like you have no way to know if the website you're visiting is really a front end for smart contract you hope to use. Now, as a user, I have a dozen different wallet providers. Each wallet provider, I have like 20 accounts on EVM, I have 100 accounts on Near, and like that is unsustainable between the privacy, between the chains, between like different apps. Like it's just a nightmare. And at the end, people just want to use cool apps. They want to get earn and participate and really have this new economic opportunity that we're creating by kind of interconnecting this global economy. So how about we defragment and aggregate things, and instead of having like a wallet in every chain and like account, dozens of accounts in every chain, we'll just have one account, one wallet, and we'll interact with all chains. So that's kind of the core idea of chain abstraction. Like you as user don't need to think about which chain you're on, what gas token is there, which bridge is actually going there, what are we swapping, like what's going on. You just have one account, you connect to an app, you use it, you don't care which chain it's on. And as an app developer, you now can launch anywhere because users will be able to use you. That's the idea. And we want to create a movement out of it. This is not just Near, pushing this. We want to create a whole group of people building towards this vision, right? We just had Chain Abstraction Day. We had a ton of people from EVM ecosystem, from Cosmos ecosystem. We're trying to bring more folks from other areas, roll-ups, intents, all kinds of stuff. And the idea is that all of these pieces, right, we have, modularity with a ton of people building stuff. We have, folks who are building intents and execution from everything from 1inch to, Uniswap backs. We have orchestration, aggregation, all of those cool words. At the end, they all serving this idea of chain abstraction. They all are how we're achieving it, and chain abstraction is a what. And so, in a way, we're all working toward one direction. And so the idea is like to kind of put a word on it, be able to explain it to users. So like what I'm working on, well, I'm really routing this transaction flow when builder like proposer separation is being executed. It's like, no, I'm trying to make sure that as a user you can just use stuff and it's chain abstraction. So that's the idea. I'm encouraging everyone to use that. And so as Near, we started with kind of core principle that we wanted to deliver really kind of user experience that is better than Web 2. We wanted to deliver something that you as a user are able to access this global, kind of financial system, global permission system, ownership system, and don't need to bother with kind of keys, accounts, gas fees, etc. And we focused on obviously building layer 1 and kind of focused on experience there. But over past about year, we started figuring out how to bring the same experience to the whole Web3. So instead of just having that on Near layer 1, we're now accessing all rollups, all layer 1s, and really offering this across. And so there's a whole stack of kind of different aggregations and abstractions and that we have. Obviously, it starts with super scalable layer 1 that's powered by sharding. We have near data availability for rollups. We have fast finality to route data and kind of value really quickly with eigenlayer. And we have ZK Wasm that allows to aggregate security and unify it. So this is a security aggregation stack, and there's like a bunch of people working across the whole ecosystem, and we collaborated with them. The other piece is, that was mentioned around kind of how do we do kind of delegated signing. And so we're actually using this to not just allow you to sign on one chain, but actually have addresses on every chain, right? So now with near account, you're able to go sign up and have access and transact on every chain in the Web3 ecosystem, right? And you can have multiple addresses. And what's interesting is if we add like a little bit of ZK there, you actually can have addresses that are not associated to each other. So you, as a user, don't need to like create new address every time you want to send somebody money. All of this is done for you. You just have one account that you're transacting with, and you can interact through one wallet. So that's kind of core idea of account aggregation. There's a lot of tech, relayers, intents, MPC, all of that packaged up. But at the end, just one account, connect, use. And similarly, as if you're building smart contracts that want to be multi-chain, this is the same for smart contracts because on near accounts and smart contracts are the same thing. So you can have your smart contracts actually transact on other chains as if it was an account. Finally, yeah, so chain signatures, this is kind of the core idea of multi-party computation with where the validators can rotate and the same key, like this set of validators can sign for the same key even as new ones join and leave. And you can use this as from a smart contract, you can use this from the wallet. And so you can actually send a message saying, hey, I want to sign something on behalf of this near account on chain, on like Bitcoin. It'll generate you an address and sign with it, and relayers will relay the transaction. Now, that's not it. That's not everything. There is other missing pieces. So one of them is decentralized front ends. So we have the security unification. We have account aggregation. And now we package all of this up into a single app, single experience. So you don't need to go and like find where the applications are. You don't need to kind of think, is that application had just been hacked and I'm actually sending all my money to somebody else. So we have an example app called DabDab. It actually has 150 different smart contracts from 14 different layer 2s, all aggregated into one interface. You can transact, like mine airdrops, swap, lands, and kind of do all kinds of DeFi, all from one gateway, which fully powered by decentralized front ends. Every single piece of front end code that you see that renders you the front end is actually stored on chain. And so you can verify that what you're interacting with, like this swap, is actually doing exactly what you want. Obviously, not everybody will do, but this allows to have this level of protection. And so all of these layers allow to have this new chain abstracted experience. Now, Near is a home for top consumer apps, right? We have kind of a number of applications that have millions of monthly active users. We have some of the wallets that have, Hot just reached, I think, 1 million daily active users. And this allows to now all of these users to actually access all of the Web3. Pretty much we're opening up all of these users to not just sit on Near, but actually have access to every single other chain, from Bitcoin to Ethereum, from layer 2s to Solana, from Cosmos chains to XRP and ADA, whatever. And so that's kind of core idea. This is really the novel way to open up, to onboard users, and really enable them to transact across all Web3. Now, it seems a little bit abstract, right? And so how about some more examples? So really cool things you can do, right, is you can build smart contracts that are interacting with other chains. And you will say, well, there are bridges, right? You can actually bridge assets. The thing with bridges, they're very complex to maintain and deploy. They have, they become really a honeypot for somebody to hack. And so instead here, you can actually have a smart contract on Near that submits transactions on Bitcoin, right? Or has an address which can receive something on EVM or on Solana. And so you can have things like somebody deposits, for example, an NFT on Ethereum and receives Bitcoin into their address on Bitcoin through a smart contract on Near. You can have a Near account that has associated addresses on Bitcoin that owns ordinals, on Solana that owns their NFTs, and you can sell that account itself with all of these assets attached to it to somebody else at 1 second block time, at, fraction of a cent transaction fee. So you can transact whole bundles of value without really needing to settle on those chains, and then you can still withdraw it there. You can turn Bitcoin ordinals into NFT on Near, sell, transact it, and then unwrap it back and receive it on a different Bitcoin address. You can do all of those different kind of use cases, and there's more in the dev chat people are discussing. So I'm inviting for developers to join that. So, don't be a fragmented Web3. Lots of wallets, funds are stuck withdrawing from optimistic rollups. You need to understand where your tokens are, which, is that rollup using which gas token? And so really kind of join this chain abstraction movement. I'm inviting everyone. Now, I just want to finish on one idea. Chain abstraction is kind of what moves us forward with Web3, right? We have kind of established the value of Web3, but it's still there's a lot of conversations that just happen around how hard it is to use and kind of how limiting it is. Near has pioneered a lot of the account abstraction and really simplifying onboarding. That's why we have most users in Web3 right now. But that's been kind of one side of the equation. The other side of the equation, though, is we have more and more kind of unique experiences that are not just built by people, but anybody can be a creator, can create new experiences, new applications now, new games, new content. And even more, you want it to be personalized, you want it to be done on with your context and your data. And this is the idea of user-owned AI. This is about not just decentralizing AI in the sense that we're running a blockchain, but decentralizing in the sense that you run it on your local device. And so if you combine these two pieces, you have a fully self-sovereign operating system that runs on your device, that knows things about you but doesn't leak that data to anybody else, that is able to interact with other parties, that are able to send and transact kind of on your behalf, and is able to even participate in governance and maybe in some data marketplaces. And all of that is preserving the kind of benefits of self-sovereignty that we're trying to bring with Web3. So if you're interested to learn more, I'm giving a talk tomorrow at EthDenver main stage at 4:45. And so I'm inviting everyone to join more. I'll kind of cover self-sovereignty and how we really need it in age of AI. Thank you. And I'm inviting everyone to assemble the abstractors.
Thank you. All right. Thank you so much. Really appreciate it. That's great.
Sure, yeah.
All right, everyone. We are on hold for just a few minutes here, so feel free to check your telegrams, and I'll let you know when we kick off. Do we have everyone in the room, Gil? Okay. Up next, we have a really exciting panel. It's actually 3 of my favorite people to hear from. Gil, I talk to every day and love everything he has to say. David Hoffman from Bankless is in my ear for basically every workout I do at 5:30 a.m. And then Joey I met recently, and he drops great knowledge. So we're holding for our 3rd guest, I think. Okay. So we should kick off soon.
So sorry to interrupt, guys, but we're still finding the other half. Is Joey here now? Joey's right there. Fantastic, great. Yeah. So we're grabbing another piece of this panel. Be ready to rock soon. All right. Cool. Sorry, that last one a little early, like 5 minutes ago. Yeah. Not ideal.
Well, why don't you?
We're gonna start momentarily. Promise a good session.
Two or
No, there's
three.
Four of us.
Yeah.
Awesome. I think we need one mic as well.
Okay.
All right. All the speakers are in-house. We're just moving them in location. Normally I'd tell a joke, but I've been at this since 7 a.m. and you don't want to hear my jokes. I should have like some good blockchain jokes. I mean, I could try. If you guys were here earlier, Michael gave a joke that he had to explain that fell flat.
He's German.
That's true. Germans are not known for their sense of humor. Many things, not. That's not a blockchain joke. That's a German joke. We're supposed to be inclusive. Anyone have a good blockchain joke? Yes. How does a compute machine call his father? Okay, how? Dada. I like it. I like it. That's a bad joke. I love it. I used to have a T-shirt that says, there are 10 types of people in this world, those that know binary and those that don't. All right, Joey, why don't we get you on up here? Come join us. I think we got David from Bankless right here. My brother is a stand-up comedian. I am not. I just like to hear the sound of my own voice. Hey. Good to meet you. We've got 2 out of 3. And the third has probably gotten pulled from behind us. There he is. All right, let me distribute the microphones.
Thanks, sir.
There you go. It's going to be a fun one. We get to talk about all the topics that I like and have debates on with my partners.
I'm ready to go. Oh, wait, we're getting spicy, or are we being amicable?
No.
Right.
We don't do amicable on these. Spice all the way. All right, so I'm excited. We have an awesome panel here. I'm Gil Rosen, help run the Blockchain Accelerator, run BAS over here, teach a course on blockchain with Kuhn and Steven. Hope you guys have enjoyed your day. Also help run Blockchain Builders Fund. And here with us we have Nikhil Viswanathan from Alchemy. I don't think he needs an introduction.
Thanks for having me.
Definitely. Joey Groth from Founders Fund. And David Hoffman from Bankless. This is an awesome and diverse crew of investor, media, builder who has an insight into builders. So with that, let's get into this. All right. Question number 1. Do you think that we're moving to a place where here we are. Yeah, do you think in blockchain we're shifting to a place where there is more of a focus on fundamental value and adoption and utility, or is this next cycle, as the price of Bitcoin seems to imply we're in, going to be driven again by memetics and hype and Ponzinomics to some degree?
Who wants to go first?
Go for it.
All right. As much as I would like to say that this next cycle is going to be a fundamentals-driven cycle, it doesn't matter how true and strong and powerful your fundamentals are, retail and speculation will always come and overpower that. We can always get further out over our ski tips. And so there are plenty of reasons to be very bullish on crypto, and I think if you're an investor in the space, we all have to be fluent in what that means. And then we attract a next concentric circle out of new crypto incomers who don't understand crypto, who aren't fluent in blockchain, who are just here to speculate on the newest hype of that phase. and they will completely drown out all fundamentals for the next 2 to 4 years. And then fundamentals takes over again. And so there's always this pendulum between fundamentals and hype. And when we are in a bull market, we are not in the world of investing in fundamentals anymore. And that is the phase of time that we are entering into, is my opinion.
Yeah, I think that's absolutely correct. Like, as a simple benchmark for this, like I bought some Dogecoin 2 weeks ago and it's up 77%. And so like if you look at stuff that has fundamentals, you know, it's not up that much.
Fundamentals are bearish in bull markets.
Yeah, I think you know, in the bear market, you kind of start to see people separate the wheat from the chaff, but that's not going to happen in the current environment. But you know, if you're building a company, obviously that's what matters long run. And so you can't lose sight of that as like an investor. If you're investing in early stage projects, that still matters a lot. It's the number one thing. But you know, in the short run in the public markets, it's going to be very frothy, I think, over the next year.
My thoughts are, I think it actually doesn't matter. And the reason is, when you look at, I think the answer, or the question that I'm hearing behind the question is, how are we progressing towards long-term adoption of Web3 as a technology for the world? And I think I would view them as two separate events, rather than trying to see if a cycle is driven by hype or what in speculation, or it's driven by the technology. I think the important metric you're trying to see is, if you're trying to make money, you're trying to see, is it hyped? And if you're trying to figure out if the technology is going to be here for the long term and how far we are along that projection, the important thing is actually just looking at the technology adoption and the actual real world adoption. And I think trying to say it's driven by hype or it's not driven by hype is actually the wrong question, and really just focusing on where we along that technology adoption curve is what's important.
Awesome. And I mean, to your guys' point, if we look at Web 2, there obviously is a lot of hype and bubbles, whether it's in the real estate industry, whether it's in, GameStop and the like. So it's not like that doesn't exist. I think to some degree, and we'll get into this a little bit more, the question is for a lot of builders here, what should they be looking at and thinking to build in is kind of one side of it. And the other is, have we ever been in a place until now where there really was a lot of fundamental value outside of payments? And I'll dive into that in a second. Curious to hear what your thoughts are. I guess, like, as we look, like, going along this vein, where do you think this next adoption is going to be? Kind of, where are people going to be building? Should they be building? Is this more in the deep in and RWA space, which we're kind of seeing a 17, 18-like resurgence in some ways, except now it's possible that this is viable and real? Is it more the restaking kind of ecosystem, which feels a little bit like DeFi summer in some ways, or DeFi in general? Is it going to be gaming and social, AI, Bitcoin narrative? Curious what you guys are seeing or excited on, or what you're seeing people build on.
If you guys let the media go first, the media guy go first, I'm going to take it every single time.
All right, I'll go first. I think one really important thing to realize is, one thing that we see in our data is that there will always be whatever is trending on crypto Twitter, or the DeFi summer, or NFT hype, or whatever it is. But the really interesting thing that we notice is, it's not like in DeFi summer, like DeFi is going up and everything else is crashing. That's what's capturing the zeitgeist. But we're generally, any kind of excitement around crypto rises the tide across all industries. And one of the things that we've seen, a couple examples to say, it's not just restaking or DPIN or whatever's the flavor of the month, or data availability, right? Is a couple examples. So, like, one, we are working with, make sure this is like not NDA'd. We are working with Shell, and they're doing a supply chain to track all of their real world assets, like kind of physical equipment moving around the world, which is like a really cool use case of blockchain, right? Another one, I talked to the CEO of, be a little careful on this one, CEO of one of the top 2 social media apps in the world that all of you have on your phone, half of you are probably using right now. And he was saying, hey, we're super excited about Web3. They had paused their Web3 stuff for part of last year, but they said, we're super excited about Web3 for doing things, several things. One, redoing NFTs on our platform. Another one, they want to do loyalty passes for creators across different websites. Another one's, they want to like tokenize creators and let you invest in an influencer, right? Which is a really cool concept. So the point here is, like, one of the cool things about Biancomi is, like, we get to see broad usage and building across the space, regardless of kind of what's the zeitgeist at the moment. Obviously, the DeFi summer, the DeFi stuff did have more attention, but it doesn't mean that there's none across the board.
Yeah. I think sort of all those things are interesting. The one area that I think is not too interesting in crypto, at least to date, in my view, is like the decentralized social media stuff. I just don't think it's 0 to 1 enough. But outside of that sector, there's a lot of interesting stuff happening. I'm a huge fan of what's happening in the DeFi space. I've always been really excited about that kind of subsector of crypto. It's kind of basically the largest market in the world.
It was your first love.
Yep. It's also just like really good. Like if you're borrowing, on like Compound or Maker or Aave, it's a way better experience than borrowing from a centralized lender. And today a lot of this stuff is speculation. It's trading other cryptocurrencies, but very long run. I mean, you have the CEO of BlackRock talking about this. Long run, I think most financial transactions will take place on blockchains. It's not going to happen next year. It's probably not even going to happen next decade. But that's sort of where the arc of history is bending here, in my view. Over the shorter run, I am actually still excited for prediction markets. I think poly markets actually got a lot of traction recently. Maybe this is actually now kind of the right time for that. The tech stack and UI UX and stuff has gotten to a point where it's actually feasible. So I think there's a lot of interesting stuff happening this year.
Actually, on that note of prediction markets, I remember a tweet from you, Joey, like forever ago, like 2018, 2019, where you were talking about it was a combo of lack of stable coins and there was the volatility in ETH and the latency of transactions was one of the big reasons why prediction markets were being held back. And I remember I like stored that in my brain, and it's been like lingering there ever since. And now all of a sudden we have like cheap fees and stable coins, and now all of a sudden like prediction markets can actually have like the foundation to be built on. This guy's tweets, I keep them in my brain. I want to like split your question into two. One is like you were talking about like what is the growth sectors of this industry. Another way to frame that is like, what will this cycle be remembered by? I think unequivocally this cycle will be remembered by AI crypto overlap. And that is going to be like the 60 IQ, very simple, let's smash these two particles together and see what happens. It doesn't have to make sense, but these things are going to pump. I heard a take at the AI conference, the AI day on Monday that I really, really liked, which is the true innovations in AI crypto will come from very narrow integrations of one by the other, as in like AI products will focus on AI and then they'll use crypto very narrowly to fit the last piece of the puzzle to make something work, and then vice versa, right? So crypto projects will use AI very narrowly to like make something work, and then the meme ones, the ones that are gonna probably pump the most and then also crash the most, are gonna be the ones that try and do the 50-50 split to really catch on the narrative. But we have insane growth in AI. AI is going to move very quickly. Tokens as a liquidity event are going to actually satisfy that demand for speculation coming from retail as this hype cycle, both in crypto and outside of crypto, manifest. And so these two industries are very fast-paced, and AI won't be able to express its financial interests in the TradFi space because you have to go through all the hoops and hurdles to get liquidity and an IPO. So these two things are very like naturally fit for each other, even though we don't know what the hell is actually real here. But nonetheless, that's not going to stop anyone from speculation. And so that will be what I think this cycle is remembered by. And then there's like a handful of very strong categories to actually talk about real fundamentals. You've mentioned some of them, like the Bitcoin renaissance and actually seeing Bitcoin expressivity happen, eigenlayer restaking and how that's like unlocking the new software as a service model. But I think when we look back on 2024 and 2025, it's going to be the AI hype coin mania. That's how we're going to think of it.
I think I agree with you, especially on the hype coin mania. I look at AI and the popularity of AI like in the Web 2 space, and I think it's still taking some time for AI to permeate like every industry. And we see people using like RAG approaches in GPT to kind of plug it into their workflows. But I think it's going to take some time for that to proliferate. I actually agree. I think AI is going to break the world, and blockchain will hopefully fix it. Is my quick take. Yeah. I think we have some time for that, but in the meantime, you're right. We're going to have a lot of hype projects that are combining the two. Interestingly enough, by the way, Joey, I think the app that I use the most is like Warp and Farcaster. Interesting. Mainly because I think like TikTok and Instagram are ruining my life, and I hate being manipulated. So this idea of not having AI models manipulate me. All right, well, let's go to the next one. David, you touched on something interesting. Curious, what do you guys really think about Bitcoin and everything that is happening in the Bitcoin ecosystem currently?
I can go on this one. So Joe and I were actually just in Dubai at, I think this is the first like actual Bitcoin conference we went to Satoshi Roundtable. I will say it was like absolutely fascinating for a lot of reasons, and I'll skip the full details of it. But first off, I actually think there's and for those of you who are in the ETH world who may not be familiar, there's actually been a few kind of key technology innovations in Bitcoin, which have effectively enabled Bitcoin to be programmable. The big one being like BitVM, and what you saw with ordinals kind of take advantage of that and launching, getting a lot of attention. And they had a significant percentage of all ETH DeFi volume on ordinals. So it wasn't like this kind of tiny thing. And what we saw is there's about 20 Bitcoin L2 that are going to be launching in the next 6 to 12 months. I'm actually really excited. There I was like the ETH maxi. I think we have at Alchemy have like a very agnostic view of chains, and we're not like Bitcoin maxis or ETH maxis or whatever. By the nature of our business, we're very heavily like almost all in ETH. But so I was there at the conference being like, I don't know if you guys even have a shot at anything. ETH is like so dominant. But while we're here, I will say that the one thing they do have is like massive liquidity. And if they are able to figure out some kind of technology like that is good enough to make that experience great, and all these funds, all these like normies who have Bitcoin now can do something with it, I think that's actually really exciting. And I really don't think this is kind of ETH versus Bitcoin thing. I think it's how do we bring Web3 and these technologies to the entire world. So I think it's super exciting to see over the next 6 to 12 months.
Yeah, I think it's interesting to see kind of development finally pick up around Bitcoin. I think if you look at kind of the zeitgeist of Bitcoin development, I think it was 2015, maybe 2016, something like that. Blockstream was created, and it was this VC-funded thing to make Bitcoin, really accelerate and have all these kind of new improvements. And then it basically went nowhere. It's sort of like basically designed by committee. And no one wanted to actually improve anything. And then if you look at kind of what's happened now, it's much more community driven. No one really has faith in Blockstream to actually make anything happen, which is good, because now there's this really kind of grassroots group of people building on top of Bitcoin, which is actually quite cool to see. On the Bitcoin layer 2 thing, we haven't made an investment there yet. I think it sort of reminds me of the ETH layer 2 space and the ETH scalability space. I probably looked at 60 or 70 companies before investing in Arbitrum, and I think the winning Bitcoin layer 2 maybe hasn't even been founded yet. The reason behind that is I think a lot of the people doing this right now, they're kind of following the hype, and they don't really have like a 100x better technical solution to it. There's still kind of a lot of issues behind making it actually work at scale and not just be kind of a clunky, super slow thing. But I think it's possible, which is pretty cool to see, and I'm excited to see what happens there. I think there'll probably be some research breakthroughs over the next year or two that could actually lead to something meaningful.
I think the big lesson that I'm pulling away from this resurgence in Bitcoin building is like people are building EVM layer 2s on Bitcoin in kind of like this compromise fashion. Even the BitVM is a one-of-n trust model, which is strictly inferior than it would be on Ethereum. But yet, nonetheless, people are doing it and people are investing in it. I think there's a number of notable things to pay attention to is that like with Bitcoin expressivity comes VC investment, comes hype, and it comes just with alignment of like capitalist interests, which is always going to be healthy for an ecosystem. So like you're going to see a natural draw that way. But even when we do have like strictly inferior layer 2 integrations with Bitcoin, nonetheless there's demand. Nonetheless there are builders. And like why is that? Like why are we so interested in building on Bitcoin even though when an actual like virtual machine on Ethereum can produce stronger security assumptions? To me, it goes back to the value of BTC as money. If you are some like early CryptoPunk NFT equivalent on Bitcoin, like you are the CryptoPunks of Bitcoin, you're going to get liquidity just because exactly what Nikhil is saying, the liquidity of BTC, the asset, is so strong that it just feeds right into its own local ecosystem.
And there's nothing to do with it right now.
And that's nothing. Yeah, right. There's just a latent demand. That's exactly right. And like the things that we saw get absolutely destroyed in 2022 was Celsius, Bitcoin productivity through Celsius, Bitcoin productivity through BlockFi. Right, and so like now, and back in those days, layer 2s from the Bitcoin perspective, which tend to be much more conservative, were still very nascent technology. But in the year of 2024, layer 2s, which they are almost truly copy and pasting onto Bitcoin from Ethereum, are actually pretty robust technologies and are ready for prime time. And so the era of Bitcoin productivity, I think, is upon us in a way that we've never actually been able to see it before.
I like that, yeah. I think of blockchain as a combination of like network effects and technology merging, and in Bitcoin you just have huge network effects from the as you mentioned, the liquidity there. Next, all right, so we've got some individual questions. Nikhil, you have insight into everything people are building.
God mode.
Insight means alpha, right?
You should love it. It's fun, man. What are the biggest challenges that you think devs are facing today and that you kind of see in the ecosystem?
Okay, I think there's 3 categories of challenges. One is core infrastructure and tooling. You know, I like to think that we've had a small part in making that easier to build. There's this kind of cycle where developers build apps, and those apps are useful, so users come, so more developers come, and so on and so forth. Kind of that bottom part of the cycle of actually building things. I would say on a scale of, if you think about building a physical building, and you have where the caveman with sticks and pointed sticks and mud to automated robots that build skyscrapers, we're probably in the phase where you take the fire stick and you rub it like this, and then you make fire. So it's more advanced than just like a little stick, but we're still in like stick era. So we still have a very long way to go, and I think that's what we at Alchemy that's a huge focus of ours. I'll tell you the second big piece of developer for developers is user interfaces and making that really easy to use. And that's something we've also put a lot of effort into. We just announced our kind of embedded wallet solution yesterday, and the idea there is make seamless UXs, because right now there's no way your guys' parents, or maybe some of your parents, but your parents are going to remember like seed phrases and gnosis, safe multi-sigs and like all this kind of stuff. So you need to make that really easy to do. And then I think the third thing is user acquisition, and that ultimately comes from making apps easy to build, having good UX. And I think the thing that people don't realize, and I think this is Joey's point earlier, is you have to have, my kind of way of explaining this is, if you ever have to say the word blockchain or decentralization when explaining your product, it is not valuable, because it needs to be so valuable that the benefit stands for itself, not based on the technology, right? You don't go to the restaurant and say, oh, well, I have this like computing device and I use the internet to pay for it. It's like, no, I just use like Uber and Apple Pay, right? And I think that we are still in that age of like, once we find truly, I think this is the trifecta of easy to build, easy to use, and actual real utility, that third piece of acquiring users will come.
Awesome.
I think you said that was my question.
Yeah, that was your question. Right. Joey, what are the biggest challenges that you see your founders have facing?
What was the question?
The biggest challenges you see your founders facing.
Oh, I think every company's different, so there's not like a concise answer to that one. But I would say in general, one of the hardest things with building a company is hiring. It's hard to find the right people. It's hard to not hire too fast, but also not hire too slow. I think another challenge that every company faces with is how do you actually get the message of what you're building out there in a concise way that people understand, and that's very, like Nikhil did a very good job of this with Alchemy, and I think it's actually really hard to do in crypto, because in the reason why being so good at describing what you do is important is it matters to everyone. It matters to potential hires, it matters to potential business development partners, it matters to users. It matters to traders who are going to buy your token if it's a token project, and so that piece is really important, like brand and marketing, and then let's see what else. Yeah, I think those are kind of the main things. Like people face challenges with hiring, and then they face kind of branding challenges. Outside of that, everything else is kind of random and varies a lot across company.
Yeah, I think we see that a lot as well. It's especially now competing with AI and trying to getting good developers excited about the space. I think hopefully this cycle brings more excitement, especially if we combine the two buzzwords together. And then I think earlier we were saying blockchain is technology meets network effects and go to market. But we see the same thing. It's like a lot of the folks that are coming out of our ecosystem, super sharp, great at tech, like there's a learning curve in figuring out how do you actually like bootstrap network effects and go to market. And I'm gonna go back to that in a little bit.
Another problem is kind of lack of sleep lines under your eyes. See mine, Joey doesn't have any, so if you're a founder, get ready to sign up for that.
Yes, amen. And David, last but not least, curious, like as you speak to like thought leaders on a daily, weekly basis, what do you see as some of like the biggest challenges and risks in the space?
Well, the challenges and risks are probably always because we have, like, in speculation is just inherent in this industry. And so building as a founder, especially as a first-time founder, when you are just cutting your teeth, like chewing glass, trying to make it, both trying to make it inside of the short-term cycle while also trying to make it inside of the long-term cycle is a very delicate thing to balance. Especially when just like, as a first-time founder, you don't know what it means to just like think in the long-term time horizons, especially if you're inside of a single cycle and you need to pivot very, very fast. Product market fit is yet to be discovered in crypto, which means that like that we have even less information about like how to build a successful company. We have plenty of information to how to build successful infrastructure. And even that is like, even the successful infrastructure that has been deemed success because of high market cap is not necessarily the actual successful infrastructure that's going to stand the test of time over like 10 to 20 years. Signal is hard. I would say to come to an actual final conclusion for your answer, like finding signal in the crypto space is some of the hardest things to do. Because it's a moving target, and also when people come in and they come into the industry and trying to learn it is typically also when noise is the highest and signal is the lowest. This is why I think anyone who has been in crypto, who's been a builder in crypto, always appreciates bear markets. I remember about one cycle ago now, right before new people came in, I was having the time of my life thinking like, oh my God, this is gonna be great. This is gonna be awesome. We're on the bull market. This is gonna be fantastic. Me and all my friends are we're gonna make it this cycle. And then I didn't realize how bad my mental health was about to be for the next like 2 years. And I think that kind of can whiplash a lot of people, including myself. And then all of a sudden, anyone who's been in crypto for more than one cycle is like, I prefer the bear markets.
Agreed.
Yeah. And so like going through that, like it's kind of like a character development story, except you start as a baby. Every new entrant comes into the crypto world, just like learning the rules brand new again. We have a different way of talking. We have a different way of socializing. It's like a different culture. Navigating all of that is very, very hard. And like I said, it's a moving target, so it kind of changes every 4 years anyways.
Yeah, I think that moving target part, like you hit the nail on the head there. Like you're building for other crypto founders very often, especially in the infrastructure space, and like they don't know what they're building yet, and like that's a moving target. It's also interesting, like a year ago, a lot of the things that we're seeing today weren't even feasible to be built. So I think the only non-moving target is this kind of like RWA DPIN space, but we probably weren't ready to build for that space up until now. And I guess that takes me to the next question then, which is, we're entering a bull cycle, I think. Like
we are.
We are. What infrastructure or narratives do you think have brought us here, whether they're from a tech advancement perspective or not? I mean, there's obviously like Bitcoin, the halving, ETFs, etc. And then specifically on the infra, do you feel like there are any gaps that are still out there for us to be a more mature, like outside of tooling, more mature sector?
Yeah, I can go. Something that's kind of weird this cycle. Last cycle we had DeFi Summer, kind of defined 2020, and that was like a bull market we made that ourselves. Like that was an internal endogenous bull market where we created wealth because Compound was valuable, Uniswap was valuable, Aave was valuable, Maker was valuable. We were connecting some of these things together. We invented governance tokens, and that was kind of the liquidity event that started all the speculation. And that was us. Like that was not external capital. That was not external retail individuals coming to play. And then the NFT mania took over, and that was like the new thing, right? So that was like the unpredictable thing. Like when I was thinking about like what was going to go mainstream in 2019, 2020, it's like, oh yeah, it's DeFi. It's just strictly a better financial system. Turns out like consumers speculating on JPEGs was actually the reason why crypto was going to go mainstream, and that was not predicted. We have a lot of just very real innovations moving forward one cycle this time, but I don't think we've had some of that same like DeFi summer endogenous bull market that we had this last time that we have this time. Like Solana has kind of had like a microcosm of that, but it hasn't permeated throughout the entire crypto bull market. I guess the thing that we've earned, strictly earned, is like the ETFs. That is like something that the industry has earned, and now we are reaping the rewards of that. But that's like the fundamentals. And so like the NFT equivalent for this cycle, like it's the unpredictable thing, right? It's like we don't know the thing what's going to come externally and define it. Like maybe it's AI. And yeah, like that's the thing I'm still kind of like circling on, like kind of keeping an eye on. Like that part of the cycle where things get like unpredictable and extremely frothy is still like to be determined.
Joey?
Yeah, I mean, I think from like a price action standpoint, I think sort of what in my read of what happened is, you know, September, October, there was kind of a, not as low as the FTX low, but there was sort of a local low. Bitcoin hit like, you know, just under 25K. And, you know, I think at that point, there weren't really that many marginal sellers. But at the same time, there weren't a ton of people who could deploy a ton of capital into like Bitcoin and ETH during that period. And then when the ETF narrative kind of started to pick up, I think what happened is, you know, since 2017, I remember people saying, you know, oh, the institutions are going to come and buy crypto. And now that nobody's really talking about it, I mean, they're saying the ETFs here, but I think they are actually buying it from an institutional standpoint. You know, I think hedge funds basically front ran the Bitcoin ETF trade. And then, you know, when the ETF launched, there's just been, you know, massive inflows. If you add up GBTC and the other ETFs, it's basically roughly half of gold, which is wild to think about and probably higher than almost any of us kind of thought would happen this quickly. And so I think that's what's driven it so far. And then I agree with David that the kind of next phase over the next year or so, which I think will be sort of more of the mania phase, that'll probably be driven by some, you know, other narrative that's not the ETFs. I think AI is probably going to be the narrative, just because you can't really buy AI stuff in public markets anywhere. You can't buy OpenAI. On, you know, U.S. equity stock exchanges, you could buy NVIDIA, but it's already way up. All the other public AI stocks are mostly not good. You can buy some stuff that's sort of a proxy play, like you know, Palantir's out there, but for the most part, there's not a lot of public market AI plays. And so if you're a retail person who is afraid of, like, you know, what happens if AI comes and basically just generates a bunch of wealth and I don't get any of it, what's the way I hedge against that? Well, I'll buy like whatever the crypto AI thing is that I can buy that's much quote unquote cheaper than Bitcoin and ETH, and that will kind of drive this huge, in my view, speculative fervor that we haven't really seen yet, but I do think is coming over the next year.
Call it AI shitcoins.
I was about to say, the only cheap way to still get into AI, blockchain.
One thing that I thought was really interesting recently, and this is recorded, so I can't say everything, but I can say partially, had one of the commissioners of the CFTC over for dinner at my place 2 weeks ago. And it was really, so at Alchemy, we're kind of an infrastructure company, so we've generally been not involved in regulation. We don't handle money directly. You know, it's changing now with wallet infrastructure. But one of the things that we were talking about was America versus the rest of the world in terms of crypto adoption, and also like the relative global strength of the US as a technology powerhouse, which, you know, the computer, the internet industries really drove a lot of America's wealth creation and dominance as a superpower over the last 20, 30 years. And you look at crypto being kind of built around the world because the US has not gotten their act together in terms of regulatory clarity. One of the really interesting things that I think will fuel this bull market to go even longer, hopefully longer, is we will see two things that will hugely influence U.S. regulatory climate. The first one is the election at the end of the year. And basically, what we heard from the CFTC chairperson was that almost certainly Gensler's going to be out. Definitely if Trump wins, probably if Biden wins, almost certainly if Biden wins. And there's a lot of like nuance, and I'm happy to explain afterwards why, but that is a really interesting thing. The second thing, kind of nuance in that, is he actually doesn't really care about crypto one way or the other. This person had worked directly with him for a long time. His whole goal around this is he wants to be Treasury Secretary. The people who help kind of moderate these nominations are people like Elizabeth Warren and other people who have their own like their own agenda of why they don't like crypto. So it's like really him just kind of executing these people's orders, and I think that will be a huge unlock against kind of this barrier that is holding back the crypto industry in the United States this year. Today. The second part of it is, I think the ETFs will have a much stronger influence on regulatory climate than we realize, because it's one thing for this like an average American to hear, oh, this SBF guy with crazy hair scammed people and went to jail. Like, do we want that in our country? Versus their friends made money buying Bitcoin through their, Charles Schwab, and now I can't do it because my freaking senator said thinks this is dumb. Like, when it becomes a personal problem for average people, I grew up in Texas. When it gets a personal problem for people in Lubbock, Texas, that will influence regulation, because the only thing that the government people care about is getting reelected, right? So I think that those two factors will have a radical shift, hopefully in the Bitcoin, the crypto macro market. But as someone who lives in the United States and has benefited so much from this country, hopefully also will help us make us more competitive as a country globally in crypto.
I like it. Yeah.
Wait, can I keep going on that, Nikhil? I want to unpack this a little bit, because this actually doesn't square the whole idea of Gary Gensler moving on. So I want to find truth here, because I got coffee with Hester Peirce this morning. She was here at EthDenver. Hester's term ends 2025. Gary Gensler's term ends 2026. Hester wants out, because imagine working in that environment. Gary Gensler wants to be Treasury Secretary, as you said, but a lot of other people also want to be Treasury Secretary as well. And so her analysis is that if Gary Gensler doesn't get the job, which is less likely because of how many eyeballs are on that job, then Gary Gensler stays as SEC Commissioner, because he just wants to be in a position of power. He's one of these statists who enjoys that. And so unless Trump gets elected and kicks him out, any Democrat that comes in is probably just going to let it be. That's my analysis of the current situation.
So there's a bit more nuance. Is this televised?
No.
Suddenly I'm going to be audited tomorrow on my taxes.
No.
The short... All right. This is also when we do these private dinners, I try not to talk about this stuff publicly. The short answer is, if it's Trump, he's going to come clean house. If it's Biden, there's three outcomes which can happen. One, or actually there's really two outcomes, but there's one influence on it. One is that generally people like to come in, during these transitions, they like to come in, they have all these political favors that they need because people have helped them get elected. They want to kind of swap stuff around because it's it lets them kind of do favors for people. And it's a little bit more nuanced to that, but let me just stop there. And then the second option is, if he gets another job that is better than
one more rung up the ladder.
Yes, or something that's parallel, or he goes back in academia or something like that. That's also a very acceptable thing. The only scenario. Oh, and then the real reason behind this is he is. She said this person said he is very, very smart, and actually very smart, which is interesting because we think of him as dumb, but he's actually very smart, and he used to be at the CFTC, and he ran the same playbook of grabbing power, grabbed crazy power. This I'm saying way too much on camera. This commissioner basically said, the CFTC and the SEC is kind of pretty unconstitutional, actually, right? So when they come after you, the SEC serves you and says, we're going to sue you. Then they are also the judge and they are also the jury. So in a case when they go after, I think Richard's starting to say this. So at QuantStamp, they got sued by the SEC, and they basically came after them. And he said it was ridiculous. He said they came after him, and they're like, okay, this is a security. You guys are scamming investors. You need to pay $30 million. And then they were like, no, that you come sue us. And they were like, okay. They came back 6 months later, okay, pay us $10 million. And they were like, no, we're not doing it. We're not doing anything wrong. All our stuff we've done right. We're a utility token, all this stuff. And then they came back and said, okay, pay $6 million. 6 months later, okay. And then they were like, no. And then they just kind of negotiated it down. And the point here is that, and this is actually exactly what the commissioner said. The SEC is not really trying to protect consumers. It's not trying to do what is good for the country. This is all politics, and it's effectively shaking down these kind of companies to be a kind of example to other companies in the space to push this political agenda. So the last part that's really important on this is TLDR, she said he has pissed off way too many people on both sides of the house, and that's actually the big problem. So if Democrats come in, he's still probably out because he's pissed off too many people.
Nice.
In the power grab.
Can we like crowdfund a token that'll get him a good job that's not SEC commissioner
literally.
that doesn't touch crypto? Gary token. This was awesome. We've gone a little bit over.
If I disappear tomorrow, like, come find me.
Thanks, Akil.
Guys, this was awesome. Thank you so much. Really appreciate it. Exciting times ahead. And guys, thank you all for coming. This has been an amazing day. Please stay. We have dinner, we have drinks, we have music, but more importantly, we have like everyone here has been absolutely awesome. So thanks again, and have a good evening.
Thanks for having us.